Hi Ramesh, hi Sri.
Good morning, sir.
Hi, good morning.
Yeah, so we will start, sir, around 8:50, sir.
8:50. Okay. Do you have everything you need from us in terms of the video and so on?
No, sir, we have received all the things.
You have received everything. Okay. Okay.
Yeah.
So I think the only thing I
Okay.
wanted to check with you was we sent one continuous video that plays for about 2 hours 40 minutes. So we are trying to
Yes,
think
yes,
of
yes.
how to arrange the
Yeah.
question and
Greetings from the organizers of VLSI Design Conference 2021. Right. So I, on my personal behalf, and on behalf of my general co-chair, Gaurav Trivedi, and organizing co-chairs, Preet Yadav and Devesh Dwivedi, welcome you all to the 34th edition of IEEE International Conference on VLSI Design and 20th International Conference on Embedded Systems. This is the first time, perhaps in the history of the conference, that we had to go online because of the current pandemic situation. And this is true all across the world, in a sense. So, a learning experience for all of us, including all the organizing committee members, for bringing out a good show just on the online mode for the next 5 days. We start today's session with the tutorial sessions. And within the tutorial sessions, which are marked for 2 days, we have about 7 tutorials lined up during those 7 days. I think my tutorial co-chair, Professor Sri Parameswaran, will be delving more into that. So let me introduce to you the tutorial chair for this conference, Professor Sri Parameswaran. It's a pleasure to introduce Sri to all of you. Sri Parameswaran is a professor in the School of Computer Science and Engineering in the University of New South Wales. He was in the role of acting head of the school at the University of New South Wales from 2019 to 2020. He served as the program director for computer engineering. His research interests are in system-level synthesis, low-power systems, high-level systems, and network on chip. He also served as the editor-in-chief of IEEE Embedded System Letters from 2016 to 2019. He serves or has served on the editorial board of IEEE transactions on CAD, ACM transactions on ACM transactions on embedded computing systems, Eurosip Journal on Embedded Systems, and Design Automation of Embedded Systems. He has served on the program committees of DAC, DATE, and ICCAD, and Codex ISS, and also on cases. Sri Parameswaran received his B Engineering degree from Monash University and his PhD from the University of Queensland. It's a pleasure to welcome Sri. Sri, I hand over the proceedings to you now. Thank you. Sri, you are not audible. Can you please unmute?
Can you hear me now?
Yes.
I'm sorry.
Absolutely.
So first of all, thank you very much to all the organizers, and thank you for helping us organize this under these trying conditions. I'd also like to thank my co-chairs, Professor Anand Bulusu and Professor Janaki Raman from IIT Roorkee and IIT Madras. And I would, of course, like to thank all the tutorial speakers and the people who are attending these tutorials. We have, as mentioned earlier, we have 7 tutorials today and tomorrow. The very first one is going to be presented very soon. And in the interest of time, I won't go into it in too much detail. You can go into the web pages and see all the bios of the speakers. But very quickly, this morning's talk will be open source analog layout automation with machine learning. And the speakers are Dr. Stephen Burns, Professor Ramesh Harjani, Professor Jiang Hu, Professor Sachin Sapatnekar, Dr. Arvind Sharma, and Dr. Sona Yildiz. Now, all of these people are very eminent in their field, some of whom I have known for probably more than 25 years. And I think we will have an amazing morning of talks. Please bear with us. Different people are coming from different time zones, so there might be small glitches and small delays, but I think we are set to go. So over to you, over to the organizers to play the video to start the tutorial.
Layout automation with machine learning. My name is Sachin Sapatnekar. I'm a professor at the University of Minnesota. You can see the campus of the University of Minnesota in the background. You can imagine this is not a live shot because in February, there's a little more white stuff behind us. In this talk, we'll be talking about analog layout automation with specific reference to the Align layout system that we are developing. This is a joint effort between the University of Minnesota, Intel Labs, and Texas A&M universities. We have 6 presenters today, and the presenters are listed over here. Steve Burns is a senior principal engineer at Intel Labs. Ramesh Harjani is an experienced analog designer and an early pioneer in analog layout automation at the University of Minnesota. Jiang Hu is a professor at Texas A&M University and an expert in physical design. I'm Sachin Sapatnekar. Arvind Sharma is a postdoctoral researcher who's been working intensively in driving the Align project. And Sona Yildiz is a research scientist at Intel Labs who's looking at a number of algorithmic issues as well as interfaces with designers on the Align project. In this tutorial, we'll be presenting various parts of Align, which is the project that we've been working on for several years. We are very excited about this project, and it has now reached the point where we've deployed it. We are now in version 1.0, which is available on GitHub. And we've been able to synthesize the layouts for a number of designs of a wide variety of circuits. The presentation will consist of several parts. In the first part, Professor Ramesh Harjani will discuss the motivation and background for analog layout automation, as well as some history. In the next part, we'll provide some introduction to the overall overview of Align, and we'll talk about various segments of the project from there on. We'll start first with how we recognize the circuit, how we create hierarchical structures that will be used to drive layout. I will be presenting that part. The next part, we'll talk about how we start generating layout from the lowest level leaf cells, which we call primitives. So these are small structures with a small number of schematic transistors, and we build parameterized layouts for these. In the part that follows that, we look at how we take these smaller cells and compose them into larger structures. So we have a hierarchical representation of the circuit. We now compose the layout of the circuit block by block, going up the hierarchy until we have the layout of the entire circuit. And in doing that, we have to meet all of the constraints that are required by the analog designer, both in terms of things like symmetry, as well as in terms of performance. After that, we'll have a discussion on the software aspects of the project. Dr. Steve Burns will present an overview of how you can run a large open source project of this sort with multiple contributors from multiple sites and multiple backgrounds, because we are academics as well as industry folks. So how did we come together and come up with a coherent system for this? After that, we look at some design test cases, starting with the presentation of some Intel test cases by Dr. Sona Yildiz. And we'll end it up by talking about some demos, showing some demos of circuits that were designed on the university side. I hope you enjoy this tutorial. We'll begin with the main part of this tutorial now. The first part is presented by Professor Ramesh Harjani, who'll present some background and motivation for the problem. He'll talk about why analog layout automation is important. He'll talk about some of the issues that we need to be thinking about, and he'll overview some of the past work in this area. Over to Professor Harjani.
Hello, my name is Ramesh Harjani. I'm a faculty at the University of Minnesota. And today I'm going to talk about analog design automation and a quick introduction to it. In particular, I'm going to talk about a quick introduction to analog design. I'll talk about how analog and mixed signal design circuits are everywhere. And I'll talk a little bit about the difference between analog and digital circuits and some unique properties of analog circuits. Then I'll motivate the reason of why we're working on analog layout automation and how it helps the actual process of doing layout, but also improves the quality of designs that circuit designers are going to produce. Then I'll provide a really quick nonlinear history of analog layout automation. And in particular, I'm going to break it out into procedural methods and optimization methods. And then I'll leave it over to Professor Sachin Sapatnekar. So if you look at analog circuits, they're everywhere. And here's an example of robotics. Anytime there has to be some sensing, some viewing, we have analog and mixed signal circuits in here. In the case of wireless, we understand RF and analog circuits are going to be everywhere with wireless infrastructure. On the right-hand side, we're looking at wireline, the backplane of things, the signals that go from different parts of from a chip to another part of the board, or from board to board in different places. These are all analog circuit signals. If you're looking at cars, radars, sensors, a lot of things within the cars and automation and driverless systems. And then if you're looking at smart cities and things in the future, health, public safety, all of these things require analog and mixed signal circuits. And if you look at things that you would traditionally have thought of as being purely digital, for example, I'm looking at an iPhone 12, and here's a blow-up done by iFixit.com. And they've looked at the actual boards that exist within the iPhone 11. And you can see the number of digital there are a lot of chips in here, and only 3 of these chips are fully digital. And I should even say that parts of these digital parts have a little bit of analog in them, but the rest are clearly mixed signal circuits: RF transceiver, PMIC, power management units, accelerometers, so forth. Okay, so let's take a look at what I just mentioned may have been a pure digital circuit. For example, the CPU in your laptop, like an Intel CPU, I'm using the 45 nanometer Nehalem CPU that has 4 cores. And most of these CPUs are a full system on a chip and have multiple units. They have a cache, they have IOs. And let's take a look at where analog circuits are likely to show up. For example, anytime you connect to the outer world, you have DLLs and PLLs. When you're connecting between cores, you're probably going to have some forms of PLLs or DLLs. You're likely to have thermal sensors and even high-speed I/O. And we'll see an example of a high-speed I/O wireline that is a mixed signal circuit. Now, the other thing about analog and digital circuits is about the issue of precision. Or first thing, let's talk about a digital adder. A 4-bit digital adder is shown on the left-hand side, and it uses lots of transistors. And this particular design is actually a simplified version because it uses T-gates. On the right-hand side shows you the same adder using 2 transistors and 1 resistor. Now, the reason for this is that digital circuits, the transistors are basically used as on-off switches. In analog circuits, we utilize more functionality of each transistor. And because we use more functionality of each transistor, more things become important. Parasitics become important, device matching becomes important, cross-coupling between lines matter, supply noise matters. And what I was coming down to is the idea of precision. In a digital circuit, you're trying to decide whether the signal is a 0 or 1, and you're switching from 0 to VDD, probably, let's say, a 1-volt VDD. In the case of an analog circuit, you have an overdrive voltage, about 100 millivolts, which is VGS minus VT. and you're basically changing that to look at different signals at the input. So your sensitivity by itself, the precision that you require is, if we assume VDD is 1 volt, 10 times more for an analog circuit. In this particular example, we're going to talk about parasitics. And in this political slide, I'm going to talk about capacitance. So, and I'm going to give you one particular performance metric. The performance metric for the circuit is CMRR, common mode rejection ratio. And let's talk about why CMRR may be important. If you look at a cell phone, an LTE phone, the minimum sensitivity, or the smallest signal it can decipher, is a minus 102 dBm. And this corresponds to about 2.3 microvolts peak in a 50 ohm antenna system. Now, typically your cell phone has a lot of digital circuits on it as well. They're switching maybe at 1 volt. So we're trying to decipher signals that are about 1 million times smaller using analog circuits. And I've done some calculations, and I've left you the equations on the left-hand side, where CMRR is basically differential mode gain divided by common mode gain. And on the right-hand side, I'm going to show you an example. In this particular example, I'm using a very simple op-amp. It's a 5T OTA. And what I'm going to do is, the red dotted line, inside the red dotted line, I have some parasitic C1. I'm going to change the parasitic and look at the AC performance, or the common mode gain. I'm only going to look at the common mode gain and assume that the differential mode gain doesn't change, but the common mode gain is what I'm looking at. And I'm going to change that parasitic capacitance from 0 to 50 femtofarads. And what we see here is at 1 megahertz, the common mode gain increases by 30 dB, or the common mode rejection ratio decreases by 30 dB. So these parasitics have a huge impact on the performance of analog circuits. Here's another example. In this case, I'm going to look at the same 5T transistor pair that we talked about, but this time I'm going to look at the resistances R1 and R2 shown on the right-hand side figure there, circled in red. This is the parasitic resistance between connecting the source of M1 to the source of M2 with the current source on the bottom. And if we go through analysis, we can see that the effective GM, the effective transconductance of M1 transistors, M1 and M2, can be written as the GM of the actual transistors divided by 1 plus the GM times RS, where RS is the parasitic resistance that we just talked about. And I'm going to switch that resistance between 0 and 250 ohms. And if you recall, when we're connecting between these transistors, we typically use metal lines. We're going from some diffusion to a metal line and then back to the diffusion layer again. And there are vias in here. And each via is maybe about 20 ohms or so. So I'm putting a large resistance value of 250 ohms, but it's only a slight exaggeration. So using this, I've simulated on the right-hand side the unity gain frequency, again, an AC simulation. Without any resistance, the unity gain frequency was 70.5 megahertz. When I added this 250 ohm resistance, the unity gain frequency dropped to 44.5 megahertz, a huge drop in the unity gain frequency. And this problem is exaggerated in FinFET technologies because in FinFETs, a lot of the metals are unidirectional. That means even if you want to connect between transistors M1 and M2, you may actually have to go through a couple of metal layers. And if you do that, you end up adding more vias and more resistance. Additionally, the wires themselves are very thin, which adds to the resistance properties. So the other thing about analog circuits is that device matching is very important. And in general, analog does not rely on the absolute value of any device. This is because of PVT, because of process temperature and voltage variation. All the parameters of a device varies, the VT, the mobility, and so forth. So what analog designs rely on is the matching between components. For example, on the left-hand side, we are seeing a differential pair, M1 and M2. We rely on the fact that these two transistors can be made to match fairly well, maybe up to 1 part in 100 or even better. Now, to make that possible, when we lay it out, layout is very important. And when we lay it out, there are going to be gradients in the oxide thickness and the doping. So what we do is we break up these transistors M1 and M2 into 2 halves. And we design it such that half of M1 is in the top left corner and half of M1 is in the bottom right corner. Likewise, for M2, we break it up in half. which means that any linear gradient, if we assume that these devices are small and gradients are going to be linear, then they cancel each other from any direction. Additionally, when we were designing a circuit, for example, let's say we're doing the current emitter on the right-hand side, where we have transistors MA and MB. We want MB to carry 4 times the amount of current of MA, which means that we would have to make the device MB 4 times larger. So one way of laying out is shown on the left, the wrong way, where we make the device M2 to be 4 times larger. What we should actually do is make it 4 units of the left-hand transistor. And I put the references to this. You can see similar examples in other books as well. Now I'm going to switch a little bit and talk about why we are doing the Align project. So if you look at a mixed signal design, this is an automotive design done, and I've taken this out of my advisor's slides, Rob Rutenbar from Carnegie Mellon. It's a commercial mixed signal ASIC. You can see that the digital is actually much larger than the analog, but if you look at the design effort, the analog actually takes more of the design effort in designing the circuit and so forth. So analog design often becomes the bottleneck. So we want to speed this process up. Here's another picture of why we want to use Align. So let's say we have a mixed signal SOC, and this is taken out of some references from Mentor. So even though the analog may be a small portion of the digital, in terms of the design risk, this analog may be 75% of the design risk of failure. So as shown on the bottom right, 70% of respins of mixed signal circuits are caused by the analog failing. So for a digital designer, a Verilog designer, a Verilog coder writes the code and comes up with the architecture. Then there is somebody else who does the physical design, and this is always consistently the same. Typically, the physical designer is completely different from the Verilog coder. In analog design, this may or may not be the true, but is often in companies, the circuit designer is an engineer, and what they do is they hack the transistors and creatively create a circuit. They hand this over to a layout designer who may or may not be an engineer, but typically has a lot of experience doing layouts. They're creating new rectangles and new layouts, and they do this very creatively. A good layout designer is a huge asset to any company. So this picture shows you what happens when you go from a typical mixed signal IC design process. You start at the system level, you verify it, architecture, verify it, cell, verify it, and so forth, until you get to the very bottom. And then there's typically a lot of iterations that goes on in a mixed signal circuit, a lot more than in the digital circuits. We're going to be focused on the 2 things I've highlighted, the cell layout and the system layout. And in particular, we're going to emphasize the cell layout process here as well. Now, if you think about what I just talked about, is the optimization, layout, and optimization cycle. Traditionally, this is what happens, what is shown in this picture. We have a circuit optimization. The circuit designer does this, comes up with the topology, does the sizing of the transistors, typically handed over to a layout designer or a physical layout designer. Normally manual. They do cell generation, placement, routing, and this may take days to weeks. It then comes back to the designer. The designer is going to extract it, the layout, look at if the performance meets specs, and then re-optimize it. And then the layout designer does one more crack at doing the layout. Typically, this is limited to 1 or 2 iterations, primarily because it's very expensive in terms of time to do the iteration. Now, what we're trying to do is we're trying to make the automatic layout very, very fast, maybe a couple of hours. What that allows us to do is that it allows the circuit designer to see and optimize the design much quicker and do another automatic layout. It may even increase the number of times he iterates to get to a more optimal design. So not only do we get a automated layout at the end, but the layout is likely to become of a higher performance because it's done quicker. So the entire purpose of Align is to do efficient, automated, high-quality layout synthesis. I'm now going to do a quick nonlinear history of analog layout automation, and we can basically break it up into 2 kinds of methods that I use. One is a procedure-based method, where we generate layouts based on a pre-designed templates of some, and I use a procedural approach for this. This tends to be more circuit specific, typically uses a lot of designer input and setup. And if the coding is done well, it can be reused for different technology. The optimization-based techniques, what we do is we formulate the problem as a constrained optimization problem. And then the quality of the layout of some form of symmetry and some things are put into that to be the objective functions. It requires some minimal amount of setup and may not, and it's most likely not topology specific. We often use simulated annealing or some other stochastic-based algorithms to accomplish this. However, given that it is a stochastic method, it is hard to guarantee the quality of the tape out, the quality of the final layout, and whether it's good enough for tape out. And in general, once again, because it's stochastic, once you do repeat the process, you may not get the same answers. So let's talk about procedural analog layout automation, often used to generate modules of fixed topologies. So the one thing I wanted to point out here is that if you look at digital circuits, you have AND gates, OR gates, and multiple kinds of gates. Typically, the sizes of all of these gates are very similar, except for maybe scaling them up for making the drive strength larger. In analog circuits, the same devices, for example, in a differential pair, could vary by orders of magnitude. And depending on where it is used, this is something that you don't normally see in digital, but you see in analog. Using the procedural techniques, the kinds of quality of the layouts that you generate are fairly good. And because this is essentially recoding the analog layout designer's expertise into a parameterizable code. Some early examples of this layout generators include stuff out of in switch capacitor circuits, voltage references and op-amps, SAR ADCs, and so forth. And there's some newer examples, like, for example, BAG2 out of Berkeley. I'm going to talk about a few of these examples. So this is IDAC and ILIAC. IDAC was the circuit designer and ILIAC was the layout designer. This is out of CSCM, and if you don't know who CSCM is Mark de Grauw used to lead this effort when I was doing my PhD work. And they are the electronics end of the switch watch companies. So you take a layout, you create modules, and then you do some module generation as you show on the top right-hand side. You have modules for capacitors, transistors, MOS current emitters, lateral bipolar devices, and so forth. As an example, let's look at the voltage reference shown on the left-hand side. This one uses a couple of lateral bipolar devices and MOS devices. Again, just want to remind you where this comes from. CSCM is the watch manufacturers that are working at very low power analog circuits. And on the right-hand side, you see the layout for the same reference shown on the left-hand side. And you can see the large capacitors and also the large resistors shown on the bottom side of this. Now, this is a picture showing of the BAG2 work being done out of the University of Berkeley. Professor Elad Alon, Professor Bora Nikolic, and others are involved with it, and a number of students. So you're basically doing some coding, and you're trying to make it as independent of the actual coding to do the layout, but you're making independent of the technology. And they have shown that this can be done. And they have ported it to different technology. For example, in TSMC, they've used 28 nanometer, 16, GF, 45, 22, SD28, and so forth. An example is shown on the bottom left. This example shows the same 5G transistors we've been talking about earlier, but this is a fully differential version. The actual schematic is shown on the left, but rather than enter it as a schematic, you enter it as code. And then you write the code to generate this layout directly from there. You know that the differential pair should match, you know the two top transistors should match, you know the bottom should have low parasitics and so forth, and you write the code to do that generated. So you have macro code that generates the actual devices and so forth, the modules. Now, they have been fairly successful with this. This is back to, again, this is a 4-tap DFE-based SerDes receiver front end. If you remember when we talked about the microprocessor in your computer, that the IOs have a lot of analog. And here's an example of the analog that exists for the receiver side of the SerDes receiver. So you can see it's got a continuous time equalizer in front, and then some digital and so forth that you're doing in the back end. So the receiver front end is shown on the left figure here. It's got the receiver data path, the CTLA up front. Now, because it's modularized, you can make it into a 4-tap DFE as shown in the center, or you can make it into a 6-tap DFE with almost very little amount of recoding. So that's a very big advantage of this technique. However, it's kind of focused on this particular design itself. Now, this is some work out of Carnegie Mellon. My advisor, Rob Rutenbar, he had a number of students working on layout synthesis. Some of the tools that came out of there are Acacia, Koan, and Anagram. And in all of those cases, what you do is you recognize some macro cells, you perform some placement, and once you have the placement, you actually have some macro cell generators before you use the placement, and then you route them. And you may actually do some post-processing for compaction. And here's an example in the center, which shows some automatic layout generated from Anagram. And the top left shows you without any placement or optimization. The B shows you with placement optimized. C shows you with both placement and routing optimized. And the D shows you a handcrafted design. And you can see the handcrafted design and the automatic layout that has been optimized is actually quite good. These designs were actually quite sophisticated. Here's an example. They kept track of things like crosstalk, and if you look at the middle layout that I just pulled up, here there is no crosstalk avoidance added into the trade-offs or in the optimization. And in the right and the bottom is shown what happens if you do crosstalk avoidance. You can see that the two lines actually go out to avoid crosstalk between them. I'm now going to hand this over to Professor Sachin Sapatnekar with a brief introduction to analog circuit design. Thank you very much.
Thank you, Ramesh. I'll begin by first talking about analog layout in advanced technologies and some of the things that complicate design when you're working in FinFET-like technologies. So in any advanced technology, layout becomes a key bottleneck. And in fact, earlier it used to be that layout was an art form for analog design. Analog layouts were beautiful, but now it's become a chore, and that's because things have become so much more complicated. In particular, what has happened here is that if you look at the schematic versus post-layout simulation and silicon, there's an increasing gap. This graph over here shows you the schematic versus post-layout simulation results, and you can see that the errors, if you look at the max and the average, are stunningly large. They can be over 100%. This means that you need a number of design iterations in order to meet your specifications, and this is time-consuming, and it results in over-budgeting. So you've already seen that multiple iterations can be overcome if we can perform analog layout in an automated and fast manner. Moreover, now we have in FinFET technologies many more complex design rules because of multiple patterning. Some of them actually are kind of Boolean rules. So for instance, in this picture, one scenario could be that if I have these vias over here of class B, then I cannot have all of these vias over here because I may have some via density rules. So this means that instead of having simple spacing rules, now there are Boolean rules that have to be dealt with. There are more restricted design rules because of pins. And so people spend a lot more time in design rule closure. And this is a longer ramp up for layout engineers. This is a chart from Qualcomm, and it shows the relative layout as you go from one technology to the next. And the metric shows that layout effort is increasing. And in fact, if you look at the physical verification component of that, you can see that as you go from 28 to 7 nanometers, DRC closure becomes a much more significant part of the effort than LVS closure. So as a result of this, things become more complicated in layout. And it's not just about layout, because if you look at reliability, that really becomes extremely important as well. And that is impacted by layout. For FinFETs, you can have FinFET self-heating or the fish effect because of narrow fins and limited thermal conductance to the ambient. So this makes fins hot, it makes your transistors hotter, that causes degradation in reliability, etc. And so there are strict rules due to scaling that try to prevent these heating effects, particularly on electromigration in wires. If you don't anticipate this early, then you actually need a major rework of your design. So put all of these things together and you'll see that analog layout has gone from an art to a chore. You have an increasing gap between schematic and post layout results. You have to deal with reliability effects that you didn't have to earlier, and you have very significant design rule issues that you need to worry about. In light of this, it makes sense to start looking at automated analog layout, and the Align project tries to do this. Let me give you an overview of the Align project. The input over here is a netlist, which could be like a SPICE netlist. It may not have any annotation. And the output is a layout in the form of GDS2. So what do you do with a netlist? The first thing you want to do is to annotate it. And by annotation, I mean that you want to extract various types of structure or hierarchies. So if I look at this picture, if I think of it as a network of capacitors and transistors, I want to recognize the fact that there's an OTA sitting in here, or that there's a switch capacitor network sitting in here. As I do this, I also recognize that I have some constraints. So I have constraints. The circuit needs to be laid out symmetrically about this line over here. Beyond that, I need to work with electrical constraints because the circuit has some performance constraints that translate into requirements for layout. So we generate electrical constraints, apply Align to 4 different classes of circuits. Now, traditionally, a number of analog layout automation tools have only targeted a narrow range of circuits, but we want this to be truly general. So we divide circuits into 4 classes: low frequency analog circuits, wireline circuits, wireless circuits, and power delivery circuits. Low frequency analog includes things like OTAs or data converters. Wireline circuits are for high-speed links, such as DLLs, PLLs, etc. Wireless circuits are in RF transceivers, and power delivery circuits are things like LDOs or power regulators that are on chip. Align has been applied to circuits of all 4 categories. These are color-coded over here and presented with the same color codes over here. Now, why is the circuit class important? It's because each circuit class is associated with a different set of constraints. And broadly speaking, within a certain class of circuits, the constraints are very similar. For instance, low frequency analog really does worry about active and passive matching. If you look at wireless circuit, it worries a lot more about noise sensitivity than any of the other classes of circuits. So accordingly, when you think about this, this tells you what's important to this class of circuits. This formulates the electrical constraints or perhaps even the geometric constraints and helps us generate good layouts. We also provide multiple entry points into the Align flow. Align is very modular, so each of these modules is kind of a separate piece of code. So the basic approach is no human in the loop. If you give me a netlist, I'll get you a GDS. And the idea here is that we want to be able to serve the inexperienced designer. If the designer knows a little more and can put in a little more effort, they can actually put in constraints. So maybe they get this layout and they say, well, this is nice, but I could actually do better if I provided some constraints. So they could provide these constraints right at the beginning or override some of the constraints that are provided and start from here. And this gives more designer control. Another alternative is that the designer can also provide place and route guidance. And with this place and route guidance, there's much more designer control, but the floor planning, placement, and routing is still done automatically. And then finally, the 4th entry point is a situation where the user codifies placement and routing in Python. This is extreme user control, but there's still a major role for automation because generating layout is a very tedious task. And if it can be scripted, then Align can generate that layout. And as we'll see in some of the examples later in this tutorial, this is a mode that turns out to be extremely useful. Now, if I look at this abstract picture and try to convert it to something that is more meaningful, let's take the switch capacitor filter over here. As we can see over here, this is presented in terms of a netlist. What we would like to do is to identify things like symmetry or blocks that are hierarchically structured. So the first step is auto annotation, which says, okay, given the circuit, I'd like to extract this functional block out of this. Then I go hierarchically to the next step because within this block, I can identify these structures, and these are my lowest level structures. So my hierarchy actually goes backwards from here to here. Now that I have the hierarchy annotated, I can start generating layout. The first thing I need to do is to engage with the process technology. So the PDK or the design rules are abstracted first, and we use a gridded layout structure. Then what we do is we create layouts for all of these primitives. These are parameterized. So for example, the sizes of these transistors could be different, or maybe you use a different number of FinFETs. So depending on that specification, we generate layout for these primitives. These are very specific, specialized structures, so it's relatively easy to generate these algorithmically. Now we start generating layout by assembling this. So we take this and we connect these together, and then we get this layout for the OTA. Then we take the OTA, plug it in here, generate layout for all of these. These capacitors are going to be really big, by the way. And then we generate a layout for the whole structure. And this OTA now is rotated by 90 degrees and comes in over here. The capacitors are shown over here. There are some switches and so on that are also shown in this corner over here. And so through this entire process, through annotation, through primitive layout generation, through block assembly, placement, and routing, we've been able to come to the final layout. I will now hand it over to Kunal, who will be presenting a demo showing how Align works.
Hello, everyone. I'm Kunal, and today I'll give you a brief demo on how to use Align. Align is an open source tool that you can download from GitHub. This is our GitHub repository. To install Align, you can clone the repository and use install.sh file to install on your system. Once Align is installed, you can create your work directory and copy the make file from the build directory here. You can try out some of our examples available in the Align identifies common structures in the design, such as differential pair, current mirrors, and the differential loads. You can find these instructions for installing and getting started on our documentation page also.
Thank you, Kunal. In the next part of this tutorial, I'm going to talk about the auto annotation step, which is the first step of Align. Let us first see what auto annotation is. The idea is that you're given some kind of a netlist, which is in SPICE form, for example. And from this, you want to be able to recognize the hierarchies in the netlist. You want to be able to recognize the symmetries and other structures and other constraints that need to be obeyed during layout generation. To understand why auto annotation is hard, let's try and look at some examples. So here's a structure that is an operational transconductance amplifier. Any designer who looks at this knows that this is an OTA because it consists of a current mirror, a differential pair, and a load. Now, if you consider a different OTA topology, it might look something like this. And in this case, instead of PMOSs up here, you have NMOSs down here. The structure is a little different. In this case, you had this cascoded structure. Over here, you don't. But again, anyone who looks at this in a well-drawn schematic will know it's an OTA. Now, if you look at a netlist, that's much harder. And if you're a computer who's looking at a netlist, it's even harder because a computer doesn't have the benefit of being able to encode experience. Now, the types of OTAs that you deal with are typically much more complicated than this. Here's another one. This is more complex. Here's another one, and this one, and this one, and this one, and this one. And you get the picture. So there are multiple types of OTAs, and you need to be able to have your algorithm detect all of these in the same way that a human could, but using some kind of an intuition that has to be built into the computer. Now, clearly, computers don't have intuition, so we go back and see how we could try and do this. Ramesh Harjani actually had done one of the earliest works in the area of analog layout automation, and what his approach was primarily rule-based. This was in the late 1980s, and the general model of an OTA was something like this. And the idea was that if it obeyed a certain set of rules, then you recognized it as an OTA. And you could also encode those rules for more complex OTA structures. The trouble with this is that it requires a lot of data entry. And so what has changed today is that machines have become a little more smart because the algorithms driving them have become a little more smart. In particular, we've got machine learning to aid us now, and machine learning can actually learn some of these rules and learn to recognize some of these topologies. The real problem is that there are too many variations and special cases for a human or even a set of rules to figure out. So we need to be able to do things in a slightly different way. Today, we have machine learning to help recognize the blocks that we are looking for. So automated annotation is the key to being able to generate good layout. If you can recognize hierarchies in much the same way as a designer could, if you can annotate symmetries, if you can annotate other constraints like a designer would, then you're a good part of the way towards building a layout tool that can work. So auto annotation facilitates building block style layout. It can automatically recognize constraints such as matching devices, unit element arrays, same orientation structures, adding dummies, or symmetries such as common centroid, interdigitated, or symmetry about an axis. So these are some kinds of things that you need to think about during analog layout. Design rules, of course, have to be obeyed. You may want to match devices, so you may have unit element arrays that are placed in regular patterns. You may have symmetries, and for example, in this case, you have common centroid, so you have a centroid over here, and B, the device P is placed symmetrically about this, the device A is placed symmetrically about this, so the centroid of A is the same as the centroid of B. You can also have interdigitated styles, which tend to kind of have more regular routing patterns. So these are preferred in some cases. Or you can have symmetry about an axis. And all of these things are styles that are used to reduce, for example, the impact of process variations. So let's go back to a switch capacitor example that we had earlier. We started with this. We said we wanted to recognize hierarchies. We said we wanted to recognize lines of symmetry. And the way we did this was that if we could somehow recognize this and go to this stage, we could then go to this stage and then work backwards to generate the layout. So an integral part of this is being able to recognize substructures of this, for example, the OTA within this netlist over here. As we saw earlier, there can be many different types of OTAs, so we need to be able to recognize one of those topologies out of a large list. So we use a couple of approaches to handle auto annotation and building these hierarchies. The first approach is based on using graph convolutional neural networks for automated annotation. The idea is that we take the netlist specified in SPICE format. We flatten it because we want to get rid of any user-specified hierarchies that could confuse the neural network. And then we perform recognition based on the graph convolutional neural network. Once we recognize this, the structure, then we can find primitives within it. So if we recognize the OTA, we can find the differential pair and the current mirror. And then finally, we might go through some post-processing. And at the end, we have a hierarchical netlist that's ready to go in the reverse direction for layout generation. Let's look at this in a little more detail. So the idea of a graph convolutional network is very similar to the notion of a convolutional neural network, except that CNNs work on images. Image data has a very clear topology. You divide an image into pixels. If you take a pixel, there's something to the left, right, above, and below it. In graphs, it's not so clear. If I build a graph representation of this network, if I draw it this way, this node will be to the left of this one, but I could just as well draw this connection over here, and then the node would be to the right. So graphs do not have a unique embedding. So when you are trying to perform convolution on graphs, you need to do something different as compared to convolution on images. But GCNs actually allow you to do this. And the idea that we use over here is that we convert the circuit into a graph structure. And we use the GCN to recognize patterns in this. So we might, for example, recognize that these highlighted nodes in red over here correspond to the OTA structure over here. And then we can take the original netlist, extract the OTA as one element of hierarchy, and then go further into that OTA and try and find sub-hierarchies within that. The graph convolutional network is basically some kind of a neural network. So it inputs a neural net graph. It goes through a number of layers, and each layer is a convolution and a ReLU operation followed by pooling. And finally, there's a fully connected layer. And at the end of that, you may have different classes that get recognized. So you might recognize a block as an OTA or an LNA or a mixer or an oscillator, for example. The difference between GCNs and CNNs is the way in which you perform convolution. The convolution is typically performed in the frequency domain or using some equivalent of that using topological structures. So we use this technology. This is one particular GCN. There are other graphical networks that are also available out there. And when we use this, we can find patterns within the netlist graph. In particular, the GCN that was used in this work uses a spectral filter in the Fourier domain. So if you have a graph, then the neighborhood properties of the graph get characterized in the eigenvalues of a matrix associated with the graph. That's called the Laplacian matrix. And if you try and look at the spectrum of the Laplacian, that gives you an idea of the structure of the graph. So briefly, if the spectrum of the Laplacian of your target graph has some match with the spectrum of the Laplacian of the graph that you're looking at, or some subgraph that you're looking at, then you found the pattern that you're looking for. So in particular, the filter looks something like this. In this case, it's a Chebyshev filter that's shown. The details are really provided in the Deferard paper over here. But the general idea here is that I can use this to recognize patterns. And my filter size looks at the neighborhood of a node. So how many nodes do I look around the neighborhood? And you can see that if you increase the filter size within a certain neighborhood, the accuracy begins to saturate off. Once you found this, once you've identified this as your OTA, the next thing to do is to extract primitives within the OTA. So we want to extract these primitives. For every transistor, we use a source, drain, and gate node to represent it. And we show connections between these in a certain way. So for example, if I look at the drain of 2, and I have a node for every vertex, the D1, D2, and S. I have a node for every transistor M1 and M0. And if M1 is connected to D2, S, and D1, then that's the connection that I have here. M0 in this case is connected to D1, D1, and S, so it's connected over here. And the labels over here tell you which nodes are connected. So if I look at this, if this 101 tells me that the drain as well as the gate are connected over here. In this case, the drain is connected here, etc. Now I've taken this structure and translated it to something like this. I can build a similar representation for each of these basic primitives, and the next task is just primitive mapping. Do I find any of these substructures within the larger structure? So if I have a representation of this graph in terms of this kind of a structure, if it's something like this, if I have a representation of the current mirror as something like this, then I try and look at this and see if there's a subgraph of this form that's found in here. This subgraph isomorphism can be done extremely efficiently because these subgraphs for primitives are very small. And as a result of that, you can identify primitives within this. Notice that the big difference between this and the previous step, earlier we needed GCNs because there are many different types of OTAs. But if we look at current mirrors or differential pairs, there's really a much smaller universe of that. So we can create label graphs for these and match them with the label graph for the original circuit and identify the lowest level of hierarchy. If we look at this overall approach and we apply it to this circuit, our first crack at this, where we apply it to perform recognition using the GCN, has a confusion matrix that looks like this. The confusion matrix basically says, if I compare the actual class versus the predicted class, how accurate was I? So if I'm on the diagonal, I'm good because the actual class of OTA matches the predicted class, the class predicted by the GCN, which also said OTA. In this case, if I look at the bias circuit, the actual class is over here. It was also predicted to be a bias circuit. But in this case, there's one misprediction where the GCN predicted a bias circuit, but it was actually an OTA. We go through a simple post-processing step, and this actually is a very cheap step. And in this case, if we apply this, we get a perfect prediction. Everything's on the diagonal. Once we have this, we can generate layout based on the annotated constraints. So in this case, if we kind of look at the primitives, I can see that there's a constraint that requires symmetry over here. There's a constraint that requires symmetry over here, and so on. So there's this line of symmetry that's identified through the annotated constraints once I go to the lowest level. These lines of symmetries are aligned and provided to the next level subblock. And so when you go from here to the layout, you can generate a structure that looks like this, and the OTA gets translated to this. Similarly, if I have a capacitive array, which happens in the switch capacitor network, I may want a common centroid structure. And if I put all of these things together, then I can generate a layout that we've seen before that looks like this. In this case, the OTA is over here, turned by 90 degrees. The capacitors are shown over here. They're all in common centroid format. And we've used annotation and the extraction of hierarchies to build the structure of the circuit and then go backwards to generate the layout. We've also applied this to a phased array receiver. So in this case, this is the structure that we're looking at. It consists of an LNA, a bandpass filter, a mixer, and an oscillator. We feed this to the GCN to try and identify the structures. And we train the GCN on structures that resemble the base structures over here. And when we apply this, the prediction between the actual and the predicted class after post-processing is again perfect. All of the instances, all of the nodes were identified correctly. So there were 78 nodes of the circuit that belong to the LNA, 120 that belong to the mixer. And so the GCN was able to extract these perfectly and feed them to layout generation. Now, one of the issues to worry about over here is that when you use this kind of an approach, you need a very intensive training set. You need a number of LNAs, a number of mixers, a number of OTAs, etc., in order to feed this. And this requires a lot of manual data entry. Are you going to encode all circuit topologies in the entire universe, or at least a large fraction of them, into a tool? In principle, it's possible if you have enough people doing it. But in practice, for a relatively small team, it's not so easy. So we looked at a second approach where we looked at annotation and hierarchical symmetry detection, where we try to find symmetries in unknown structures. So for instance, over here, we have an FIR equalizer, which is not sent to a training set. And you can see that there is this repeated pattern over here, and we can try to find ways that identify this repeated pattern. In fact, it's even more complex than that because this pattern looks repeated, but it's not exactly repeated. If you look at these current sources, some of them are 5-bit current sources, some of them are 6-bit current sources. So they're approximately equal, but not equal. But at the same time, you would like to recognize them as being the same so that you can lay them out regularly and evenly. So the idea of this is that you can apply this without a training set. And that's the key idea here. It's a bottom-up approach. And the idea is to identify multiple lines of symmetry, identify matching blocks, identify multiple symmetry levels. If you have a repeating structure such as this, then you identify it, you create an array hierarchy, so a differential pair here, this current source over here, the current mirror, and then you have this thing that repeats, so there's another level of hierarchy over here, and so on. And you need matching between the blocks, so you need instance type matching between the primitives. So this is basically the overall extracted hierarchy here. There's a line of symmetry that's seen over here, and each of these is a separate structure. Let's look at a more simple structure that's over here. And within the structure, this is an OTA. Now you have a current mirror here and a current mirror bank over here. So you should have a line of symmetry here, even though seemingly this connects to something that's different from this. But a human designer would recognize this. And you can actually train, or you can apply a graph-based approach to also do the same. The difficulty is when you have structures like this, you sometimes have dummy structures that are connected by designers because maybe you want to make some post-design changes that allow you to incorporate these into the design. So these dummy structures have to be recognized as arrays and placed as such. Let's go back and reconsider the problem of error-tolerant matching. Here we have matching requirements between blocks that are similar but not identical. We saw this in the case of the FIR equalizer earlier. Here's another example. You have a common gate LNA here, a common source LNA here. And when you lay them out together, they are drawn beautifully symmetrically. This is a manually generated layout. But if you look at these structures, they're not identical. Here, the source goes to the capacitor. Here, the source goes to ground. So we have to be able to recognize structures that are approximately similar, whether it's in the FIR equalizer or over here. We use the idea of a graph edit distance in this case. Consider this circuit over here, which is a CG-LNA, and this one, which is a CS-LNA. The question is, how many edits do I need to go from this circuit to this circuit? So let's start over here. Let's say I make 2 edits initially. I delete this edge and I delete this edge. So I get something that's blank over here and blank over here. So I'm not quite at this point, but I'm a little closer because these were differently connected over here and over here. Now I make my 3rd and 4th edit where for this hanging structure, I connect it to Vin. For this hanging node, I connect it to ground. And I'm at this common source LNA. So the difference between the common gate LNA and the common source LNA is 4 edits. And in reality, we don't do this on the circuit. We do it on a graph representation of the circuit, but the idea is basically the same. If the number of edits is small, then we can say that the 2 circuits are sufficiently similar that we should lay them out in a symmetric manner. How do you compute the graph edit distance? It turns out that neural networks are really good at this. So we use something that's known as a neural tensor network, where again, we take this, remember the representation of this as a graph, we create the structure over here. The elements are on one side, the nodes are on the other side, and different types of elements have different colors over here. And then we basically feed this to a GCN followed by an attention layer. And then we use this standard neural tensor network structure to compute a similarity score between these. If the similarity score is sufficiently similar, then we say that the 2 circuits are close enough that we should lay them out symmetrically. So now, going back to the big picture, the reason why we were looking for this is we were looking for repeated patterns in a circuit. So if we found 2 structures of this sort and we were able to say that they were repeated, we would be able to lay them out in the same way. Let's look at how accurate this is. This is the accuracy of the graph edit distance metric computed using the neural network. The exact graph edit distance is shown by the blue bars. The computed graph edit distance is shown by the red bars. And you can see that the algorithm is not perfect, but it's pretty close. So the idea here is just to differentiate between a low graph edit distance and a high graph edit distance. And in most cases, it does pretty well. Let's again look at the big picture. Auto annotation requires the recognition of block structures, lines of symmetry, and hierarchies that are nested. So the first approach to use GCNs that require training. The second approach is going to use this graph-based approach followed by neural tensor networks to identify structures that are sufficiently similar. So in this case, if I have this OTA over here, I can identify the hierarchies, the nested hierarchies using graph-based approaches. And I can also identify regular dummy structures over here. When I lay it out, I find this line of symmetry, and I can lay this out here. Notice that we did this without having any information about the training set. We were able to do this without a training set. For this structure over here, we can see that we recognize these 2 being similar, and then we can generate a layout. And the key to that is using the graph edit distance based on a neural tensor network. Now that we have this, let's see how this works out for layout. So here we've already seen that we can go from here to the layout. Let's look at another example. This is an R2R DAC. In this case, you can see that there's this R2R structure that's repeated from here to here. And our approach is able to identify this R2R repeated structure. The R2R structure is laid out as an array over here. The switches really don't need to be matched as well. So they are actually placed outside the array. And then we have the OTA that's placed over here, and this generates a layout for the entire R2R DAC. For the FIR equalizer structure that we had talked about earlier, we've seen the circuit already. As we said earlier, the current sources have different numbers of bits. So in this case, it's 5 and 7 bits. And we want them to be recognized as being sufficiently similar to have symmetry. But at the same time, we want to kind of maintain the 7 bits together, etc. When we convert this to a layout, what we get is something like this. R1 and R2 are shown here. There are these blocks over here. The 10 taps, which are these structures over here, are shown by the 10 taps shown here. The larger taps with 7-bit current sources are placed symmetrically over here. The smaller taps with 5-bit current sources are placed over here. And finally, this array of latches that's shown here comes up over here. So this is a beautiful, completely symmetric layout, and it's all facilitated by the fact that we were able to detect these hierarchies automatically without a training set, and we were able to use these to create hierarchies and dictate how the design proceeds. So to conclude, when we look at auto annotation, there are two types of approaches that are used. One is based on a training set using graph convolutional networks. The other is much more lightweight and much more transportable to a wider variety of circuits, where we use the insight that regularity in the circuit structure should translate to regularity in layout. And so we use this notion of nested hierarchy detection and use that to create the hierarchies that are used for layout generation. We'll now move on to the next part of the tutorial, where we'll talk about primitive layout generation. The lowest level of hierarchy in the circuit design is a set of small cells with a small number of schematic transistors. And we use techniques to generate the layout for these primitives by understanding the design rules. So we first have to abstract the design rules, which come from a process design kit or PDK. And then we take the PDK information and the information about the netlist structure of the primitive to generate layout for these structures. It's important to realize that your transistors could be sized to be large or small. And so primitive layout generation has to be conscious of this, and it has to be able to build parameterized primitives. So over to Dr. Sharma.
Hello, everyone. My name is Arvind Sharma. Now I will discuss PDK abstraction and cell generation module of our Align tool. First, I will discuss motivation for PDK abstraction. With the technology scaling, the number of design rules has increased significantly. Moreover, the PDKs are highly complex in nature, and it's very hard to standardize the PDKs across different processes. The issue can be resolved or simplified using PDK abstraction. The PDK abstraction offers process portability as well as it links to other tools in a system. For example, in our Align tool, the PDK abstraction module is linked to cell generation, placement, as well as global and detailed routing module. This helps us to port or use our tool on a different process. So if you want to use our tool on a different process, then we have to just replace the PDK abstraction module. The PDK abstraction module also simplifies design rules, and it enables improved code quality. Now, I will discuss main concept of PDK abstraction. So if you look at a PDK, there are different kinds of rules. For example, distance-based rules for metal layers, for VRs, there are coloring rules, etc. In PDK abstraction, we define grids for each of the layers such that all of these rules are enforced. For example, in this figure, we show grids for a metal layer. The continuous lines show the major grids, whereas these dotted lines show minor grids. The metal layer can be placed at this major grid or this major grid. This enforces side-to-side spacing rule. Similarly, this metal layer can end at this minor grid or at this minor grid. This would enforce end-to-end spacing rules. Moreover, Boolean rules can be used to define the presence or absence of the objects on the grids, and these rules can be used to model the via spacing rules. One thing is to note down that each of these layers have their own grids. So if these layers follow their grids, then the layout will be DRC clean. So the main advantage of PDK abstraction is that this allows us correct by construction layout generation. So for a given PDK, first we create all of these grids, then we store them in a file called PDK.json file. The template for metal layer grids is shown in this figure. We can see from the figure, this has direction parameter, which defines the direction of the metal layer, color, which defines that this metal layer is available in these two colors. Then there are other different parameters which are shown in this figure. Similarly, the template for VRs is shown in this figure. which has a stack, which defines that this VR is used to connect these two metal layers. Then there are spacing rules, then there are enclosure rules, and there is minimum number of VRs, which define that these number of VRs are required to connect these two layers. And all these parameters are shown in this figure. So for a given PDK, first we generate all of these grids, then we store them in a file. And this file is used across our align tool. And if we want to use our tool on a different process, then we have to generate this PDK JSON, and that is a one-time job, and this is not a big overhead. Now, in the last slide, we discussed the grids. These grids can be uniform and non-uniform. So a uniform grid means the center-to-center spacing between the metal layers is same, as in this case or in this case. However, in case of non-uniform grid, the center-to-center spacing can vary. So what is the use of non-uniform grids? At lower technology nodes, the wire and VR resistance is very high. So to reduce the resistance, we need wire tracks. But if we define all of these tracks as wire tracks, then what will happen? The track density or number of tracks will be lesser. But if we define narrower wires, then what will happen? The resistance will be higher because the wire width is smaller. This issue can be resolved by using non-uniform grids. In this case, we can see that some of these tracks has wired wires and other of them are narrower. So wherever we need wider wires, we can use these wide wire tracks. At other connections, we can use narrower wire. So this helps us to improve the performance without degrading the track density. So now I will discuss main features of PDK abstraction. We have applied PDK abstraction to cell generation, and we found out that the layout generated using this concept are very similar to the manually generated layouts. The PDK abstraction allows us to reduce the number of design rules by 10 to 20 times, and it simplifies the layout generation code. We have applied PDK abstraction concept to different PDKs. For example, 12 nanometer FinFET and 65 nanometer bulk PDK. We have applied it to ASAP7, which is a open source PDK. Moreover, we have developed two mock PDKs. One is FinFET based, another is bulk based PDK. And these PDKs are available on our Align GitHub repository, and these PDKs can be used to run our tool. Moreover, the PDK abstraction concept has been used within Intel to different processes like 22 nanometer, 14, 10, and at advanced FinFET processes. Now, I will discuss motivation for parameterized cell generation. Analog circuits requires layout of a large diversity of blocks. For example, a transistor size in a power delivery circuit can be as high as 1000 micrometer, whereas it can be below 1 micrometer in a low frequency analog circuit. Moreover, parameterization may be required for different gate lengths, multiple aspect ratios, multiple layout patterns, etc. This issue can be resolved by parameterized layout generation of a library of lowest level primitive blocks, for example, current mirrors, differential pairs, resistors, and capacitors. Thereafter, these basic blocks can be assembled together through block assembly. In the figure, we have shown three different circuits: 5T OTA, current mirror OTA, and a strong ARM comparator. We can see that these circuits can be decomposed using these basic label primitives. For example, this 5T OTA has one differential pair and two current mirrors. This current mirror OTA has one differential pair, two NMOS current mirrors, one PMOS current mirror, and two switches. Similarly, the strong ARM comparator. So, if we can generate the layout of these basic primitives in different patterns, aspect ratios, sizes, etc., the issue can be resolved. In our Align tool, we have defined basic primitives. This is the list of primitives, and a user can add other primitives also. So you can see we have primitives like resistors, capacitors, capacitor arrays, switches, direct connected load, differential pair, etc. And our cell generator or primitive cell generator can generate the layout of these primitives in different aspect ratios with different gate length, different sizes, etc. We will discuss these features later. Now we will discuss main concept of primitive cell generation. So in primitive cell generation, first we define one gridded unit cell. The gridded unit cell can be of an NMOS, PMOS, or a resistor or a capacitor. So as we have discussed already that each of these layers have their own grids, and if we place all these layers on their grid, then there won't be any DRCs. That means these unit cells are correct by construction. These unit cells are parameterizable. We can increase the number of pins and increase the width. We can add more transistors in series that will increase the gate length. Now we'll discuss the layout generation of a primitive. So we take a differential pair. So as we have discussed that the input to our cell generator or line tool is PDK JSON file that we generate for a given PDK. And for the primitive, we take a netlist for the differential pair. So first we define template gridded unit cell, which is NMOS unit cell in this case. The user can define number of pins in the unit cell, number of gates, that means the gate length can be increased. Thereafter, this unit cell is placed and routed. In this case, we can see that source of both the transistors A and B are connected, so that will generate differential pair. Thereafter, we can have multiple wires at a given terminal to reduce the resistance at that node. So in this case, we can see that there are two connections at the source. So there are two parallel wires at the source node that will reduce the resistance. Thereafter, we use multiple patterning, which is required at lower technology nodes for a DRC clean layout. And finally, we generate a GDS of the layout and a lab file. The GDS can be directly imported into its cadence per system. Now, we will discuss some of the features of our cell generator. So, our cell generator can generate layouts with different number of pins, multipliers, and fingers. For example, in this case, we have a differential pair, and in FinFETs, these are defined as fins, then these are the fingers, and multiplier is the just copy of the same object. In this case, M is 2 means the same, there are two copies of the same object. Now, if there are a given number of fins, in this case, which is 96, we can generate that total number of fins 96 using different features. For example, in this case, we have M equal to 1, NF equal to 16, and M equal to 6. That will give total number of fins equal to 96. However, we can also generate these 96 fins using M equal to 2, NF equal to 8, and N fin equal to 6. So total number of fins will be, again, 96. We can also have M4, NF4, N fin 6. That will also give us N fin equal to 96. So all cell generator can generate the layout in different number of fins, different number of multipliers and fingers. This feature can be used by designer to improve the performance, reliability, or density. Our cell generator can generate the layout of these primitives in different VTs. For example, this primitive can be generated in standard VT, low VT, high VT, super low VT, etc. In analog layouts, long channel devices are used to reduce the random mismatch, as well as to increase the output resistance or improve the gain of an amplifier. So our cell generator is parameterized in terms of number of stacks also. For example, in this left image, there are 4 transistors which are connected in series. And this is the way in FinFET we increase the gate length. In FinFETs, we can't increase the gate length by increasing the poly length, but we connect the transistors in series. So this will give you LG equal to 4 into L min. Whereas in this right image, you can see there is all on LG equal to L min. So our cell generator take stack as an input, and it can generate a layout for the given stack. Our cell generator can be parameterized in terms of multiple wires or wire width. So if you look at this differential pair, the transconductance or effective GM is defined as GM by 1 plus GM into RS. And RS is the resistance at the source terminal. So if RS is high, the effective conductance will be less. To improve the transconductance, we have to reduce the RS. This RS can be reduced by using multiple parallel wires at the source node, as in this case, we are using 3 parallel wires to reduce the R, or we can have a single wire with the larger width. For example, in this case, we are having a single wire at the source terminal with a width of 4 times the minimum width. So in that way, the GM will be improved. Our cell generator is parameterized in terms of number of parallel wires as well as the wider wires. Analog circuits are very sensitive to differential mismatch. For example, a differential pair and current mirror require very less differential mismatch for a good performance. If there is a VTS mismatch between device A and device B, that will result in a copying current mismatch and it will degrade the performance. To minimize the differential mismatch, common central layouts are widely used. In a common central layout, the devices are divided into small cells called unit cells. These unit cells are placed such that the centroids of these devices coincide. A common central layout is shown in the figure. We can see from the figure that the centroid of device A and device B coincide. The common central layouts ensure that the linear variations cancel out. Based on the user input, our cell generator or primitive cell generator can generate a common central layout or interdigited layout. At lower technology node, layout-dependent effects are very critical. A device performance depends on its surrounding. For example, 2 different layout patterns are shown for this differential pair. In this left layout, we can see that surrounding of device A is different than the surrounding of B because there is no other device to the left of this device and there is no other device to the right of this device. However, in this layout, the surrounding of A and surrounding of device B is similar. For this device also, surrounding of A device and surrounding of B device is also similar. So this layout pattern is better compared to this layout pattern. Our cell generator or primitive cell generator can place the dummies based on user input. Our cell generator is also parameterized in terms of body contact. Body contacts are required to avoid latch-up. If body flag is off, we don't place a body contact in the primitive, whereas if body flag is on, a body contact is placed in the primitive. Moreover, our cell generator can generate a guarding primitive. The guarding primitives are required to isolate a noise-sensitive block. As you can see from this figure, for a noise-sensitive block, the block is isolated from other blocks using guard rings around it. Our primitive cell generator can also generate primitives for bulk technologies, and these primitives are parameterized by number of fingers, active width, or gate length. In the figure, we show a current mirror bank layout for L is equal to Lmin or L is equal to 4 times Lmin. In case of bulk technologies, we can directly increase the poly length to implement a longer channel device, whereas in case of FinFETs, we use stacking to increase the gate length. Our primitive cell generator can also generate passives. For example, in this figure, we have shown a passive resistor implemented using a metal wire. The resistor is implemented in 2 different aspect ratios. Our cell generator can also generate capacitors and capacitor arrays as shown in the figure. These capacitor arrays are implemented or generated in 2 different aspect ratios. Now, we discussed 2 different examples which uses the primitives we discussed before. This is an example of low power current mirror OTA. In this one, we required a differential pair with a stack of 10 transistors. As we discussed that our cell generator or primitive cell generator can generate a primitive with a given number of stacks. So we generated this differential pair with a stack of 10 and so on in this layout. Similarly, in this comparator, we required primitives with wired wires to reduce the IR drop, and our cell generator generated these primitives with the wired wire width to reduce the IR drop and improve the performance. Now, we will analyze different layout patterns in detail. We have presented our paper in Date Conference 2021 on this topic. As we have discussed before, that common center layout patterns can cancel out differential mismatch, but at the cost of higher routing parasitics. A common center layout pattern and cluster layout pattern is shown in the figure for device A. We can see from the figure that the routing parasitics are higher for the common center layout pattern. Moreover, due to its complexity, it takes more design time for the common center layout pattern. Therefore, a question arises when to prefer common center layout patterns or other layouts. To answer this question, we consider three factors. The first factor is on-chip variations. The total on-chip variations can be classified as global, random, or spatial. The impact of these variations on two devices I and J is shown in the figure. We can see from the figure that global variations affect devices uniformly irrespective of their location on the chip. That means the correlation coefficient is 1 due to global variations. Random variations affect a device randomly irrespective of the location on the chip. That means the correlation coefficient is 0 due to random variations. However, spatial variations affect a device based on its location on the chip. And the correlation coefficient due to spatial variation is a function of distance as well as one parameter called correlation length. If the correlation length is higher, the correlation coefficient will be higher. Pelgram's model has been widely used to analyze the impact of random and spatial variations. According to Pelgram's model, random variations can be minimized by increasing the device area, whereas spatial variations increase when the distance between two devices increases. Now, to analyze the impact of variations, we consider two layout patterns for a current mirror, as shown in the figure. We plot sigma by mu of the current ratio for these layout patterns. We can see from the figure that when R is very less compared to the correlation length, which is 10 micrometer in this case, the value of sigma by mu is similar for both the layout patterns. This is because random variations dominate. However, for R comparable to RL, which is 10 micrometer in this case, the spatial variations starts to dominate, and we require a common center layout for a better performance as shown in this figure. To further investigate this, we consider a 16x16 color mirror bank used in a current steering DAC. We consider two different layout patterns. One is shown in this figure. This is non-common center layout, and one is this figure, which is a common center layout used from this paper. And the RL is 100 micrometer for this experiment. We can see from the histogram that the sigma VTH value for the non-common center layout pattern is very high compared to the sigma value for common center layout pattern. This is because the layout size in this non-common center layout is very large compared to the RL value, and we need a common center layout to cancel out the variations. Whereas in this common center layout, the spatial variations cancel out due to the common center pattern, and sigma value is very less. That means when the array area is very large compared to the correlation length, we need common center layouts. We further consider one current mirror example. The size of current mirror is very small compared to RL equal to 100 micrometer. So we can see that irrespective of the layout pattern, this is a non-common center layout, whereas this is a common center layout. The value of sigma is similar for both of these patterns. That means small arrays are dominated by random mismatch, and other factors should be considered while selecting a layout pattern. The second factor which should be considered while selecting a layout pattern is layout-dependent effects. In nanometer technology nodes, the device parameters are a strong function of LDs. One of the main LDs is length of diffusion effect, or LOD effect. The LOD shifts the VTH of a device from its nominal value based on two parameters called SA and SV. These parameters are shown for a unit cell of device A and device B in the figure. Based on these two parameters, the VTH shift can be calculated from this formula. Now, to discuss the impact of LDs, we consider a current mirror example. Three different layout patterns for the current mirror are shown in this figure. From the P1, that is clustered pattern, we can see that for each unit cell of A, there is a corresponding unit cell of B, which has same values of SA and SV. That means there is no LOD-induced mismatch between device A and device B. Similarly, for pattern P3. However, for pattern P2, which is common center pattern, all the B devices are placed inside, Therefore, there is a mismatch between SA and SV for device A and device B. So this will induce VTS mismatch between device A and device B, and it will shift the mean value. So LDs affects the mean value and should be considered while selecting a layout pattern. The third factor, which is critical when selecting a layout pattern, is routing parasitics. Some layout patterns may have inherent parasitic mismatch. For example, this P2 pattern, which is common centroid, has higher parasitics at drain terminal of device A compared to device B. Due to this one, there will be a coping current mismatch between device A and device B, and it will degrade the performance. However, for pattern P1 and P3, the routing parasitics at drain terminal of device A and device B are same. So there is a no parasitic mismatch for pattern P1 and P3. For differential structures like differential pair, there is another parameter which should be considered while selecting a layout pattern is a small signal current. For layout pattern P1, we can see that the small signal current increase from left to right because all of the unit cells of device A are placed together. So the small signal current increase from 1 to 2, 3 times that way. This will increase the drop at the source terminal, and consequently the GM value will be less for the P1 pattern. However, for the CC pattern, we can see that the small signal current value first increases, then it decreases. Therefore, the effective drop at the source terminal is smaller and the GM value is higher compared to the cluster pattern. Similarly, for P3 pattern also, the GM value will be better compared to the clustered pattern. Now, while selecting a layout pattern, we should consider 3 factors. One is RL, that is correlation length, LDs, and parasitics. RL affects the sigma value, whereas LDs and layout parasitics affect the mean value. So now, when to prefer CC over other layouts? So when a layout size is comparable to the correlation length value or RL value, we should select a common center layout, which will improve the sigma value. When we have differential structures like differential pair and LDs and parasitics are not significant, then we should consider CC layout pattern because this will give us better mean value. Clustered and interdigitate patterns have lower LDs and should be preferred over CC whenever their LDs are dominant. Detailed analysis on this topic can be found in our date paper titled Common Central Layout for Analog Circuits, Advantages and Limitations. Finally, to summarize, I will discuss main features of our cell generator. Our cell generator can place body contacts. It can generate the cells in different aspect ratios. The cell generator can generate multiple wires at a given terminal, or it can generate a single wire with a wider wave. It can generate the multiple layout patterns like common centroid or interdigitate one or clustered pattern. The cell generator can generate primitives in a bulk as well as in a FinFET-based technology node. So that's all on the cell generator. Now Professor Jiang Hu will discuss the placer and router.
Okay. Thank you very much for a very interesting first half of the tutorial. We have some questions from the participants. Let me just start from the top. Belal Iqbal asks, does Align work with only lower technology node or with any technology?
So Align is designed to handle both FinFET and bulk technologies. So we've applied it to various FinFET technologies. We've applied it to a 65 nanometer bulk technology as well. There's free PDK that's now available through Skywater. It's the Skywater 130 nanometer node. It's an open source node. And we are in the process of trying to get Align to work with that node as well.
Thank you. Next question is from Muthukrishnan Chinnaswamy, who asks, who first of all says fantastic. Almost replicating DC SNPS environment, do you have formal verification equivalent built in? It must be in some form.
So I think it may be sort of a little misleading to think about it in terms of formal verification in that sense, because we don't do formal verification in the digital style. There is the notion of formal performance verification even on the analog side, but we don't do that. The way we build this is that it's correct by construction. And since it's correct by construction, it should be correct. It should work correctly. The one issue here is that we try to meet performance constraints to the best of our ability. And so far, we've been able to meet, as we'll see at the later end of this presentation, we've been able to meet stringent performance constraints on several circuits.
Thank you. Thank you. And Dr. N.B. Balamurugan asks, will you list out merits and demerits of FinFET? I don't know whether you want to take that here or you want to leave it out. It might be too much, but anyway, I just thought I'll ask that anyway.
I can, so in general, if you want to scale to smaller geometries, you pretty much cannot use bulk technologies. Below a certain technology, people use FinFETs. It's more expensive. It gives you, in general, higher performance. Design is more complicated. On the other hand, when you think about it from the point of view of layout automation, it actually gives you some benefits, because in FinFET technologies, your rules are very regulated. So you have all your transistors in a single direction. In FinFET technologies, your wires are typically in reserved layers too. And so that actually reduces the design space that you have to explore in layout generation. So in a sense, that's actually a positive from the automation point of view. And clearly, the performance also could potentially be better, especially for digital circuits. For analog circuits, depending on the circuit, this may or may not be so. Many analog designers, if they don't have requirements for kind of digital performance, might actually prefer to work in older bulk technologies because there's lower process variation and so on.
Thank you. Thank you. Sorry, did someone want to say something else? No. Anshik Gangwa asks, there are two questions. The first one is, how do you handle false positives in validation? In slide 37, I think he's referring to slide 37. That might be from the first talk, maybe.
Let me just take a quick look at this to understand it. Excuse me while I just look up slide 37. I suspect the question here is about the neural network, which tries to identify structure. So the idea there is we're given.
Sachin, if you want to share your screen, you can do that.
Thank you. There's actually not. I don't necessarily have anything to share on the screen.
Sure, sure.
Actually, maybe I can do that. It's a little more complicated because I need to set some preferences. So since I don't need to share a screen for this one, maybe I'll just answer the question directly. So the question, I think, was related to the fact that we're using this graph convolutional network to try and recognize structures. So when we take the entire netlist, the netlist is abstracted as a graph, and then the neural network tries to predict which nodes belong to specific substructures in the graph. So which node belongs to an OTA, which nodes belongs to, for example, an LNA, and so on and so forth. In the process of that, we have the possibility of identifying false positives. So we may, for example, end up identifying a node as belonging to a particular module when it's not supposed to. If we do, the net result of that is that it goes downstream and the layout that you generate may not be completely optimal. In most cases, at least for the structures on which we've applied this, it seems to turn out okay. And one of the things that we do is that we also have this other approach for recognizing regularity, the second approach that I talked about. And over there, that gives you sort of another way of trying to decide how to lay modules out in a regular way, identify symmetries, identify blocks, and so on. It's true that even in that case, it's possible that you may get false positives, and that translates to a suboptimality in layout. I think I don't have a definitive answer to the question, because in any recognition system, you can always have false positives, which will lead to suboptimality. I think for many cases, we've been able to find that suboptimality is not too bad.
And then the second part of I guess a separate question. How do we convert circuit into graph?
Oh, yeah. I actually had a slide on that, which was a very quick description. But the basic idea is that if I have a circuit, every element in the circuit, for example, every transistor corresponds to a node, every resistor corresponds to a node in the graph, and also every wire, every connection corresponds to an edge. So we have a way of constructing this graph where we have a net edge and an element edge. And if the net is connected to an element, then we have they're connected in the graph. So I think the best way to kind of answer this question in a way that becomes clear is if I refer you to our paper at date 2020. This is explained in pretty great detail. The first author on that paper is Kishore Kunal.
Thank you.
So Kishore Kunal, date 2020. That will give you details on how the graph is created.
One before the last question, could you elaborate a little on the post-processing step on slide 39?
Yeah. So in the post-processing step on slide, this is again going back to the graph convolutional network. I mentioned that in many cases, it identifies things correctly. In some cases, you need post-processing. So what happens there is that there are situations where you have a transistor where for example, the drain and the gate are set to lie within an OTA, but the source is not, which of course is really strange because the entire transistor should be in the component or not. So what post-processing does is that it just catches weird situations like that. And the correction that I'd shown you that where something was misclassified, that correction actually got taken care of when the post-processing step handled this issue.
Sorry, I thought the questions are finished, but they keep coming. Yes, Sivakumar Chintu asks, is Align layout tool, is it open source and is it available for 22FDX?
It's open source. It's not available specifically for any kind of proprietary technology. It needs to be customized for that technology. But there's basically, we've shown that it can be customized for a variety of technologies, including FET and bulk technologies. So my suggestion is that if you're interested in looking into this, please contact me. My email is sachin@umn.edu, SACHIN@umn.edu, and we can talk offline about this.
And Danny Lalit Mohan says, I think the question is the layout tool or the layout optimization tool, can it backtrace the analog circuit design? I don't know whether
I'm not sure what backtrace means in this context. Is it possible to clarify what that means?
So this is there two separate modes, two separate. The speakers are in one environment and the audience in another environment. So I'm not sure. We'll hopefully there'll be some clarity before end of the session.
Yeah. So if you could please clarify this, and the next time we have a Q&A session, if you could ask the question in slightly different words, I may be able to understand it better.
The last question here now is, how can we test FinFET-based system design?
I think the way to really test it is to build a chip, fabricate it, and measure it. That's the ultimate test, but you can still basically design it, simulate it, and see if it meets specifications and if the layout looks comparable to a human designer. And these are the modes that we've been operating in. We've looked at both modes. The first mode, as I said, was just designing it, finding out the specifications through simulation, seeing if the layout looks okay in terms of symmetry, getting it okayed by a human designer. And the second is sending some chips for tape out to see their performance.
One more question came in, but I think we'll take a quick break and come back with the second part of the tutorial because we're running out of time. The last question, by the way, came from Sivanandam S. So we'll just wait until the second half before we get on to the rest of the questions. Thank you.
Thank you, Sri. Thank you, Sachin. So we will have the next session starting now, and then we can take up these questions in the next set of Q&A.
Would that be okay? I hope it's not too late for you all.
But that's the reason I'm starting.
Thank you.
Thank you a lot. Thank you very much.
Hi, this is John Hu from Texas A&M University. I'm going to introduce the block level placement and routing in the Align flow. Our placement and routing support a hierarchical design. In the example on the left, there are actually like 3 hierarchical levels. So the placement is performed in a bottom-up manner, level by level. And at each level, we also perform guard ring insertion if there is such requirements. After the placement is completed, we're going to perform routing. And the routing is performed in a top-down manner. So this is the routing of the top hierarchy, middle hierarchy, and the bottom level of the hierarchy. After the routing is completed, power supply network is constructed. That is a power mesh and the local connections between the power mesh and the local devices. Okay. Next, I'm going to introduce how is the placement is performed. So in placement, we needed to specify the relative order among different blocks or devices. Okay. On the left, there's one example. We use a sequence pair. So this is A, B, D, C, E. This is one sequence. C, B, A, E, D, which is the other sequence. So this is a pair of sequences. They can specify the relative order of those 5 blocks. So in the 2 sequences, if we have A, D, A, D like this order, that means A is left of D. And likewise, we can specify which block is above or below or on the right of another block. Okay. And the reason we use sequence pairs is that besides the capability of specifying relative order. We can use a sequence pair to handle those symmetry constraint, alignment, abutment, separation, and the range constraint. These are commonly seen constraints in analog designs. So this page shows you some examples of some geometrical constraint. So this is horizontal alignment, vertical alignment, vertical symmetry, and this is a mixed vertical symmetry and horizontal symmetry. And we can change the roles of the designs while at the same time we can keep the symmetry. Okay, and after the relative order is specified by a sequence pair, next we're going to use integer linear programming to find the spacing between different blocks. And here, this is an optimization process where we are going to minimize the total layout area and the total wire length. Lambda is a weighting factor for this wire length. Okay, so the area can be found by looking at the lower corner coordinates of all the blocks and upper right corner of those blocks. Okay, and for wire length, we use this half parameter wire length model. So in this example, it has 2 pins. We use the minimum bounding box to cover these 3 pins. And so this is the half parameter wire length. Okay, and in this integer linear programming, we're also trying to follow those constraints. And one constraint, that is the order constraint specified by sequence pairs, and also non-overlap among different blocks. So this is a block I and block J, and J is to the right of I. So we can add this constraint to make sure there's no overlapping. And in the middle example, we show how to specify symmetry constraint. So xi plus a half of wi actually is the center line of block I. Okay, so the left hand side is the center of block I and J. So this constraint says that the center between block I and J must be aligned with the center of block K. And the bottom is an example to show how to enforce the horizontal alignment constraint. Okay. And so the overall placement algorithm is simulated annealing. And the reason we choose simulated annealing is that it is very flexible, can be easily integrated with any kind of cost function. And also it is very general, does not require a special problem structure. Traditionally, people have concern on simulated annealing because it might be slow, but analog circuit in general, they're not large, and we do it in a hierarchical manner. In each hierarchy, the number of elements actually is not large, so the runtime is not a problem. And also, simulated annealing can be easily parallelized. Okay, so the moves in simulated annealing include swapping 2 blocks, rotate a symmetry group, and swap a symmetry group with another block or another symmetry group. Okay, and after these moves, we perform this integer linear programming based compaction to evaluate the cost function, that is the weighted sum between area and wire length. So that is the whole procedure of the simulated annealing based placement. And this page shows you the placement for capacitor with the common centroid constraint. So this red is the center for this common centroid constraint. In this example, there are 16 tiles for 2 capacitors, and each capacitor occupies 8 tiles. So the algorithm starts from the center. We do the diagonal of C1 and C2. We rotate in the clockwise to complete the whole placement of these capacitors following those common centroid constraint. On the right is one example of this layout. And besides those capacitors, functional capacitors, the C1 and C2, we also use some dummy cap that's trying to make the environment to be uniform, to be insensitive to process variations. After placement is done, next is global routing. In global routing, the first step is to generate candidate route for each net. That is to generate a standard tree, and different routes actually can be obtained using digest algorithm by changing the different edges. Okay, and after those candidate routes are obtained, we annotate them according to design constraint in analog circuit. So for example, two nets, they needed to be symmetric with each other. So if we find such candidate route, we can pair them, say, hey, these two are a pair of route following the symmetry constraint. Okay, and there could be other constraint we consider, like match the number of bands, topology, orientation, and wire length. Okay, after the annotation, the last step is then integer linear programming process to choose one candidate for each net. Okay, and the selection is to minimize wire length and the number of bands. At the same time, we needed to make sure that the routing capacity constraint is satisfied and then those geometric constraints are satisfied. And after global routing, we perform detailed routing. Detailed routing is performed for each net one by one. For each net, the routing is conducted through A star search, and the routing is on grid. That is friendly for those design rules. We consider all these geometric constraints, especially we consider FinFET design rules. Okay, and we also add shielding if there's need. That is trying to reduce the noise. Okay, and for FinFET, there's also a special case that is, what if we would like to have a wider wire? That is not supported in FinFET. So what we do actually is to have multiple pass connections for the same net. That is equivalent to wire sensing because they can reduce the wire resistance. Okay, and after the signal routing, we do power routing. That is construct a power mesh, and this mesh we consider the density of this mesh is decided according to the iron job constraint, and also there's a local connection between the power mesh and the devices. And again, we use redundant connections. That is to further reduce the iron drop to those devices. Okay. And next, I'm going to talk about a technique for performance-driven placement. Okay. So this is one example of telescope OTA. And so in the bottom figure, you can see the gain, bandwidth, unity gain frequency, right? Okay. So this gray bar is from schematic design, and these orange bars are for those post-layout simulation. So we can see that layout has a huge impact to analog circuit performance. So the idea is that given like one analog IC placement solution, we use a graph neural network model to evaluate the performance. And then we use this machine learning based model to guide the solution search for analog placements. Okay, so there are many different options for machine learning models. There could be linear regression, support vector machine, decision tree, and even neural networks. There are different options. So the one we use actually is graph neural network. The reason is that an analog circuit can be abstracted to a graph. Okay, so in the graph neural network, the first part is graph convolution, and after convolution, there's one fully connected layer or MLP to classify the result. Okay. So before introducing graph convolution and the graph pooling, here I show you convolution and the pooling in the image recognition. So image convolution pretty much is take the average of a pixel among its neighbors. Okay, and pooling is a procedure of coarsening. So this is originally, which is a 4x4 array. So the pooling becomes a 2x2. Okay, so there are different approaches. So maximum is to take the maximum among the 4 to take this one. Okay, and so we can do the convolution for graphs as well. Okay, so in the graph there are nodes. For each node, there are feature vectors. So graph convolution means to do aggregation of node feature with its neighbors. Okay, and for graph pooling, it's a procedure of clustering. So you see this orange cluster becomes a node here, right? And this is red cluster becomes a node. Okay, and this is orange cluster becomes node. So we can do this multi-level clustering. So that is graph pooling procedure. Okay. So we propose a customized graph neural network. It is called pooling with edge attention. So given a circuit, we first get a graph, and it has multiple convolution layers. We call it P layers. Okay. And after multiple P layers, the results are flattened and feed to this MLP, and finally we get the classification result. Okay. So given a circuit, we first abstract its topology into the graph, and also we take its placement information to get those node features. So we use X to represent node features. So that includes like device type and the functional module. That means, for example, a device belongs to a differential pair or not. And the dimension, that is the size of a device, and the location, because we take a placement information. And adjacency matrix tells the connection in this graph. Okay, and edge features include those features of associated pins and their distance and the metal layers. Okay, okay. The first step of this P layer is to construct an attention. This is attention. Okay, so this is for edge between node I and the J for case feature. Okay, case for the case feature. So E is an edge feature. Okay, so tau is an coefficient which is obtained from here. So X are node features, and this A and W, those are trainable weight. So after the normalization, and we get these alphas are 3-dimension, because that is too complex. We do one compression to compress it into 2-dimension. Okay, because we have a multiple P layers, so the indices here, L means the layer index. Okay, the second step is graph convolution. So this is node features, and this is the edge attention after compression. This is weight. Okay, so this procedure is pretty much aggregation of node feature among its neighbors. Okay, this is a Z. Okay, and for the Z of each layer, we're going to do pooling to reduce the dimension to go to the next level feature X. Okay, so the pooling consists of 2 steps. One is node pooling. Okay, so in order to do pooling, we need to get this assignment matrix. The assignment matrix, the dimension of NL plus 1. NL is the number of nodes in iteration I or layer I. NL is for the next iteration. So NL is less than NL plus 1 is less than NL, so that we can shrink the size to reduce the number of nodes. So this is assignment can be obtained from the features and those weighting factors. Okay, and after that we can apply this assignment matrix to the Z, which is embedded the node features to the next level. And the last one is to change the adjacency matrix of layer L to layer L plus 1. Okay. The last step is to do edge pulling. First, we get this edge feature encoded attention. So this is attention we got in the first step, and these are our weighting factors. Okay, and that can reduce the dimension from PL plus 1 is the dimension in layer L plus 1. We can reduce it to the dimension of PL. Okay, and so this is the edge features after pulling. We put all these together. Okay, after we get the edge pulling, we can put the result into MLP to tell whether or not a placement solution result is good or bad. Okay, so now the simulated annealing objective function is changed a little bit. So this is area, and this is wire length, and so Q is the probability that performance violate a specification. Okay, so this is the weighted sum of multiple performance metrics. So yi is one of them, like a gain. Okay, so phi I is a specification. Okay, and so if it is less than phi I, means there's a violation of a specification. Okay, so we take the weighted sum of all of these metrics to get this Q function. Okay, and so this P actually is obtained through this P network. And here I show you some experimental results. So we use 3 OTA design as the test cases, and we generate many training samples, and some of them are used for testing. So on the right, you see this is the architecture of the P network. Okay. And first, we're going to show the result of the model accuracy. There are different measures for machine learning model accuracy. So this is true positive accuracy and precision false positive. I'd like to address your attention to this ROC curve. ROC curve is important because it shows the trade-off between true positive and false positive. Okay, we can also evaluate the area under this curve. Okay, and this area is the greater the better. The ideal one is 1. If it is random prediction, it is 0.5. Okay, so now let's look at this machine learning performance for different approach. The green bars are from our P model, and so GAT is from off-the-shelf graph attention network, and this is in a CNN approach. So for all these different metrics, PE gets the best result. We also test the knowledge transfer. Okay, transfer means this is that suppose here cascade OTA to current mirror OTA. That means we first train the model on cascade OTA, and then we have a few incremental training in current mirror, right? Okay. So we can see that the orange one is we applied one from cascade directly to current mirror. It's not that good, but if we use this is so this orange bar is we have only limited training on current mirror. Its result is not that good. But if we combine the training of cascade and current mirror with the knowledge transfer, the result is much better. And our approach is also better than the CNN approach. This is the true for different combinations. On the right figure, we also show the effect of knowledge transfer for different metrics like accuracy, precision, and true positive, and the area and the curve of ROC curve. For all these cases, we see the effect of knowledge transfer, and we're better than the CNN approach. Okay, so this is one example of this is ROC curve. Okay, so the ROC curve, if it is closer to the northwest, that is better. So our PEA, so this is a self-sustained learning that is completely trained and evaluated on a single topology. So this is best. So our approach that is they're much better than the CNN approach. Okay. So now let's look at the impact of performance solutions. So this layout score, overall score, okay, 1 is the best. So the gray bar are from those schematic. After layout, we have a degradation. And so this purple one is from the traditional automatic layout without consider performance. And this is from CNN. So we can see that our P results are much better than those CNN results. And here we show some details of a current mirror OTA. We look at the gain, unit gain frequency, bandwidth, and the phase margin. So this column is a schematic, manual design, conventional, automatic, without considering those performance CNN. And so this is our result, and so these results are better than CNN and the conventional automatic, and they're closer to the manual design. On the bottom, which we illustrate on the left, that is the layout from manual design. On the right, that is the layout from the PT design. So now let's look at the training time and the running time. So we have a comparison between our model and the CNN. So one advantage of our network is that it is much simpler, okay, much simpler. And it uses much less number of floating point numbers, and it has much less parameters, and the training time is 1 order of magnitude faster, okay. So our automatic placements can complete a circuit placement in less than 1 minute. And but if we do in the manual design, it will cost like more than 1 hour. So we can achieve an automatic design at the same time. We can address the performance issue. That's so for the placement routing part.
Align is an open source software project, and the emphasis there should be on software. We spent a lot of effort in developing new techniques and algorithms, but at the same time, the idea was to provide deployable software that would be used both within the university teams, within Intel, and also hopefully in the wider world. So in order to make this scalable, in order to make this robust, we received extensive help from Intel. This was a team that actually contained a number of students, a few industry veterans. And so there were significant learnings on the university side, especially on the software front. We'd like to share some of that with you in the next segment, which will be presented by Dr. Steve Burns at Intel Labs.
My name is Steve Burns. I'm from Strategic CAD Labs in Hillsboro, Oregon. And today I'm going to talk about the software aspects of the Align program. So on the agenda are a list of the challenges of managing multi-site open source projects, the software architecture that we chose for Align, some of the software tools that we use to get the quality results that we've got, and some future directions. So some of the important software and infrastructure challenges include the multiple sites that are used by the program. There's teams in Hillsboro, Oregon at Intel. There's teams in Minneapolis, University of Minnesota, and there's teams at College Station in Texas. There's also a varying amount of experience of the different team members with software development. We also have problems unique to digital design programs in that there's some IP restrictions on the collateral that's needed. So some teams members don't have access to particular PDKs. For example, Intel doesn't have access to the GlobalFoundries 12 PDKs that Minnesota and Texas A&M have access to. And at the same time, those team members don't have access to the PDKs that Intel wants to use. Even those that do have the same PDK, it's still difficult to exchange information directly because you need a multi-party NDA. So between those two universities and the PDK provider. And those things can be cumbersome to execute. The team's also using multiple different programming languages, Python and C++. There's also this desire to build a system that will outlast the lifetime of the DARPA IDEA funding that the program is receiving. And there's some more license-oriented challenges associated with open sourcing a project. We at Intel like to use permissive licenses where we could take the code and change it any way we feel like. But there's also some packages that we want to use that are licensed under more restrictive licenses, such as LGPL. And we need ways of working in both worlds. So the original software architecture for Align started along the paths of the early diagrams talking about the flow. So the flow was divided into multiple stages. There was netlist auto annotation, there's electrical constraint generation, there's primitive layout generation, place and route. And so each stage was originally developed more or less at one site. Each site had their own development environments and wrote code in whatever language they felt like using. The Tamu team used C++ for the place and route engines, and Python was used for most of the other parts of the flow. And so we as a team decided to use a decoupled architecture where the interfaces between modules were done using files, either using industry standard formats, actually likely simplified versions of those, just for the parts of that format that we actually wanted to use, or we use some custom JSON schemas. And because of all this sort of disparity in development environment, we relied on Docker containers to quickly bring up these individual build environments. Over time, each site's build environment sort of solidified, and we were able to come up with a unified build environment that we could share across all the sites. And Docker containers were sort of relegated to only one usage, which is in continuous integration, which we'll talk about more later. So now we have one install script, which will gather and build all the collateral package needed for the software components using Align. That script is used for local builds. So if you have a Ubuntu 18.04 LTS system, then you can just run this script and everything will work. Or you can use it inside a container that also starts with this Ubuntu operating system. And we use that for CI builds. And to keep this Align code base licensed under a permissive license, we also keep other code in separate repositories. So if we have a component we want to use that's not licensed under a permissive license, we keep that separated from our permissively licensed code, and we don't modify it. We just grab it from whatever source it's available. We store it in that location and either call it a new process or link to it without modification. So at the end of this evolution in the software architecture, we now have all the different Python stages of the flow integrated into a single program that looks something like this. We call this program called schematic to layout.py. We give it a directory where the design is and a pointer to the PDK directory. And this program contains the Align package, which is some shared Python libraries and command line API. And then it has the compiler, the first stage, which does the topology identification and constraint generation. And it has then the primitive generation capability and other utilities for analyzing the results of layout. And then it has the place and route system, which we've seen talked about in previous parts of this tutorial. There's also some underlying data structures, circuits, and cell fabric, and C++ programs that we call the place and route flow or the detailed router. Each of these pieces is highly configurable and can be used independently. And we've done that by creating multiple entry points in the flow, which will also be discussed about at different parts of the tutorial. So that's the software architecture. In terms of the software tools that we used within Align, we've used GitHub extensively for both source control and communication between team members. All check-ins to the repository are done through GitHub pull requests. And when you issue a pull request, it must be approved by at least one other team member before it will cause the repository to be updated. Reviews are done online, and in addition to there must be one other team member reviewing the changes, all changes must also pass our continuous integration checks. And we'll discuss that a little bit later. We also use GitHub issues, and we use them to communicate questions, things that we think need to be fixed, or ideas for major changes to the system. And these issues usually result in one or more pull requests that will address the issue. Here's a screenshot of the Align GitHub repo. The repo is located at align-analog-layout/align-public. There's a screenshot of the code section of the page and a screenshot of the readme.md. At the top of the readme.md is a list of 4 badges showing that CI is passed, that we're achieving an A through Codacy code quality check, and what license we're using, and whether the documentation is passing its flows as well. At the bottom right, there's a graph showing the contributions to master over the lifetime of the project. And at one point in the project, we were checking, we had 50 commits, 50 to 100 commits a week. In total, there have been 3,744 commits across 27 contributors. So now let's talk about testing. So one of the important aspects of creating quality code is running tests. And in the Align program, we use both unit tests and integration tests. Unit tests check whether individual methods perform correctly. Integration tests, in our sense, are running whole blocks through the flow to see if the flow runs through without errors and creates layout that is free of obvious design rule or LVS errors. We use PyTest as the test runner for our Python code. For C++ code, we use Google Test. Our check-in tests and the results of that check-in test are shown on the right here. It runs about 714 tests, and all of them pass. Some of them are skipped, and it runs in about 40 seconds. This is a mix of both unit and integration tests, and running this test also generates some coverage metrics, which we'll discuss later. So as part of the system is the way that tests are run is through the continuous integration flow. So every push to the GitHub repository will trigger a pull request. Every push to GitHub of a pull request triggers a continuous integration run, and we use the Circle CI cloud service for this. So when that happens, the cloud service will grab a fresh Docker container with a fresh version of Ubuntu, and it runs this install.sh script, which downloads all the collateral packages that are required to run Align. It will then clone the Align public repo, and it runs setup.py, which is a standard way of initializing a Python library, and it will run pip install on all the libraries that are needed for the Align, all the Python libraries that are needed for the Python program to work correctly. And it also compiles the place and route C++ code. It then runs the PyTest command from the previous slide, and then some other tests as well. And you can see the picture on the right where we see how we've split up the flow in Circle CI. The first thing it does is the build a line part, which is the part of downloading the packages in the repository, running setup.py and compiling the C++ code. That takes about 12 minutes to do from scratch each time. And then after that, we run in parallel, if the machines are available, 4 tests. One takes, the longest one takes 6 minutes or so. And we do this on every check-in, and we need a successful run in order to allow the check-in into the repository. So one of the utilities of this testing, or the reason why it works well in our environment, is that we've also added some simple internal DRC and open and short checks to the system. So we've added these simple tools to check a variety of things. So we want to make sure that each wire in VIA is on our grid. So we're using this abstract PDK, and we're using grid-based design. So every wire in VIA needs to be on the grid. And then each wire has to satisfy some minimum end-to-end spacing and minimum length rules, and this is easy to do when the wires are on a grid. Each VIA has to have correct metal enclosures. There's also more complex checks between vias and wires on different tracks that are done. We also check that there are no shorts. In this case, this means that we have 2 rectangles in the design that have different names and they're touching each other. That would be a short. And there's also cases where we also want to make sure there are no opens. In that case, we want all rectangles with the same name to be connected together. So this is all simplified because all wires are expected to land on grids. And because of that, we can use a very simple technique to make all these checks. The technique is to bucket all the wires into their corresponding grid bucket, as shown on the right here, where we have 3 different vertical grid lines for this particular vertical metal layer. And the different rectangles will land somewhere on those grids. We put them in the bucket corresponding to the center line of the grid. We then sort them, and then we can just scan that line from top to bottom, say, and we can merge wires that are adjacent to each other. That is the case on the right. We can check for shorts to see if the names are different, and we can also check all the wire and enclosure rules as on this particular data structure. And everything is essentially linear time. Maybe the sorting, or in log n time because of the sorting. We also check opens using some little more sophisticated techniques of assigning each wire segment a unique ID, and then using connectivity through the vias to generate equivalence classes of the various nodes that are connected together. And this is classically implemented using a union find algorithm, and we can do this very quickly as well. So this ability to do these internal checks and continuous integration has been really helpful to the Align project, keeping the code working as it's changed and improved. So we also have to use mock PDKs when we're running the CI with these abstract rules gleaned from publicly available sources, for example, IEDF papers. And that's required that we don't have any protected IP out on the cloud, public cloud where the CI is running. It's also, both time-consuming and error-prone to manually check layout visually for errors. So it's just much better to have this thing being done automatically. The other choice would be to run it through commercial DRC and LVS checkers, but then we have both vendor license issues and PDK IP issues to deal with. So we have ended up with a scheme to do things using mock PDKs and these simple internal checks to make sure most of the code is working correctly. So this leads us to the final part about coverage. So as part of CI, we also generate coverage artifacts. So here's a list of, so this is a screenshot, or 3 screenshots, showing what the coverage results look like. So after a Circle CI run, the final one, you can click on the artifacts tag. And in that artifacts tag is a list of coverage reports that were generated throughout all our testing runs. And those coverage reports look like what you see on the bottom and the right. So there's a list for every program in the system of how many statements are in that program, and how many of them are missing or do not have any line coverage on them. So when we ran tests, when we ran our PyTests, that particular line of code was not executed in any of the test runs. So that's the missing column. And then the excluded column is other cases where you've artificially, or you've excluded it somehow. So the result is a coverage metric telling you how well that particular files has been covered by the test. If you click on that file, for example, the one I circled over on the left, then you get a listing of the program where there's green bars for the lines that were covered and red blocks for parts of the code that were not covered by any test. So this helps you understand how well you're doing with your testing and whether you need to add more unit or integration tests to your design. It can also tell you whether you have a piece of code in your design that isn't being used anymore and that would be a good idea to remove it from the code base. So we have some ongoing work to improve the software infrastructure of the Align project. We want to improve the CI so that not only do we provide this layout quality feedback, we're also providing some feedback on the electrical characteristics of the generated layouts. And we have all the pieces in place finally to do this. So this is something that we'll do in the next several months. So this requires test benches for example circuits, and we have some test benches already for certain example circuits. We need a publicly available PDK with device models for simulation. And recently, 2 of those have been made available, ASAP 7 and Skywater 130 nanometer. We need a publicly available circuit simulator. Zeist has recently been enhanced sufficiently to be used for this activity. And then we need some sort of extraction flow. And we've developed an internal PEX engine similar to our DRC and LVS engines that can be used for quick extraction and has high enough quality to be used for CI-like activities. So in addition to that work on electrical characteristics in the CI, we're also working on modularizing the C++ place and route engines and connecting them to Python-based drivers using the PyBind 11 infrastructure so that we can control the place and route flow more easily. Currently, the C++ data model is translated into JSON and dumped to a file to communicate with the downstream Python-based DRC checkings. So if we do this connection to PyBind 11, these JSON files, which are quite large actually, won't be needed because we'll have direct access to these data structures with Python. This arrangement will also encourage more unit testing of C++ code because we can use Python-based flows, which we're more familiar with, to generate testing collateral for individual components like the place or the global router, the power router, the detailed router. And this will also allow a more direct usage of the Intel analog detail router. So that's my contribution to the tutorial. Thank you very much.
In the next segment of the tutorial, Dr. Sona Rialdes at Intel Labs will be presenting how the Align tools were deployed on industry designs at Intel. These industry designs were not only helpful in being able to prove that the tool works well, but also in driving new features and in driving us to understand what the real problems faced by analog designers were. So there were a number of designs that we ran that were on the university side, but there were also other designs on the industry side that used design nodes that we had never seen before. So this required customization all the way from the abstraction of the process to the development of primitive cells to the various entry points that Dr. Yildiz will be talking about in the next segment.
Hello. In this section, we will look at exercising Align at Intel, specifically on power management circuits in 22FFL technology. Let's start with a recap of why analog layout has become a chore in FinFET technologies. First, there is an increasing gap between schematic, post-layout simulation, and silicon due to parasitics and layout-dependent effects, as shown by an example on the bottom left, which compares schematic versus post-layout performance for several analog circuits in Intel 10nm technology. Secondly, the design rules have become increasingly more complex and restricted due to multiple patterning and the fin structure. As the bottom right figure shows a hypothetical design rule violation for the placement of vias. And thirdly, the reliability rules have become more strict due to fin-induced self-heating and interconnect scaling. As a result, layout has become a key bottleneck in analog circuit design. Let's have an industrial perspective now on analog layout automation, where automated layout doesn't always need to be tape-in ready. And the expectation from automation varies over the design lifetime, which starts at an early stage feasibility to late stage engineering change orders. And what is very crucial is to have fast feedback on the post-layout performance during this early stage of exploration or while designing on a leading edge process. So the figure on the slide is showing a typical iterations between an analog and a layout engineer, where the analog engineer, when finishes the schematic sizing, hands off the layout engineer, and then the primary objective is to come up with a layout which is dirty. It doesn't necessarily meet all the DRC rules, but the objective is to get high confidence on the performance. And this may take several iterations to converge. And the more iterations, if the performance requirements are higher. And just when we think that great, we converge on the performance, then the design rule and the reliability closure starts. And what may happen is a significant violation might be revealed that may change the placement and routing significantly, and even have an impact on and require schematic sizing. Therefore, getting this early feedback is very crucial, and it can prevent conservative budgeting and over-design. And where we want to really get to is this scenario where we empower the analog engineer to have very fast iterations using layout automation, and then hand it off to the layout engineer for final closure of any remaining design rules or reliability checks. And motivated by these needs, we propose several extensions to Align. And the objectives are to make it more practical for analog circuit design for modern SoCs. And the second reason is to push the performance or area limits when needed. And do this in a way we could rapidly explore the placement and routing design space. And finally, we would like to be able to research and develop novel circuit techniques or topologies. And this is where machine learning algorithms can be challenged due to circuits that are outliers or false positives. Therefore, we propose these extensions marked by entry points 1, 2, 3, and 4. And let's take a closer look. So this slide shows the high-level flow, which starts with the input netlist and the output layout. And the first entry point is where everything is fully automated, including placement and routing. The next level of input that the engineer can give is high-level placement and routing constraints, which could be in the form of symmetric placement or match routing. And this can assist the automation and improve the layout quality. If we take this one step further, then engineer can actually codify placement while using the align primitive generators and still benefit from automated routing. And if we take this one step further, we can get to the entry point number 4, where we can codify both the placement and the actual physical routing completely in Python. Now, before we go deeper into entry points 3 and 4, let's review the Intel analog detailed router, which is actually powering entry point number 3. So the Intel analog detailed router, it's a SAT-based and design rule clean router. It allows us to model complex design rules, such as this hypothetical design rule shown on the right. It can be actually formulated in the Boolean formula. It also allows non-uniform metal grids, which we will talk about more later, and it is very effective for compact layout, as shown by the bottom figures, the before and after, where we have a very dense placement, and if there is a feasible solution, the SAT-based router is able to find it. If we take a deeper look into this, as an input, the router would require the PDK abstraction, the placement of the primitives, the pre-routes, and the global routes. In this context, pre-routes could be the actual physical routes, either for power grid or for very critical nets, or the primitive pins. So here on the left bottom, we see like 2 metal 1 terminals, and let's say the objective is to route these 2. So there's going to be an abstract routing grid, and we can overlay the metal templates. And what is expected here is to create a routing plan. So in this example here, basically routing on M2 and then going up M3 for the vertical. And given this input, a Boolean formula is constructed that models net connectivity and design rules. And this is solved by a off-the-shelf SAT solver. As SAT solvers produce the first satisfiable solution, that is not always optimum for analog circuits. And to improve the quality, we basically iteratively impose external literals so that we can further optimize the routing quality. And in this example diagram, you can see SAT-based router first enumerates all the possible connections and then finds a feasible solution for all nets concurrently. Now, given this technology, if we look at the entry point number 3, we can actually codify placement and while still automate the routing. And this can allow us to pursue higher performance. It could, for example, allow us to do a more compact placement, such as we can share the tabs, reduce the padding between devices and so forth. And this could enable shorter and more fine-tuned interconnect. And the bottom left figure is showing actually a typical placement and routing spec drawn by analog engineer. And the idea we had is, okay, instead of drawing this drawing this diagram, what if we capture these specs in the form of a Python script? And this is how a typical script would look like. It would start with defining the primitives and then instantiating these primitives with the connectivity. Then if we would like, we can specify pre-routes, for example, either the power grid or the critical nets. And then we can specify the global routes, which are basically the route plans on the abstract grid. And once the script is written, then we can generate the layout within minutes. And if, let's say, we want to change routing changes done by making just few lines of code changes, we can explore the routing or the placement space. And this slide takes a deeper look on the entry point number 4, where both placement and routing is codified. And in principle, this is actually very similar to Berkeley analog generator. And where this approach really shines is for large circuits with repeating substructures, such as current mirror banks, power gates, or circuits with high current density. And this type of circuits would require maximizing interconnect utilization, or they might require adding intentional white space dummies to reduce power density. And given this regularity, codifying placement and routing actually becomes quite straightforward. Here, an example is showing a power gate, which is one very big transistor, and it has more than 2,000 fingers in total. And typically, this can be organized in the form of a 4x4 unit cell, which could be stamped to create the bigger array. Now, how we could do this is we first write a Python script for the unit cell. Again, we define the active and the dummy primitive. In nested for loops, we can instantiate these primitives. And then we can, again, using for loop structures, we can specify the pre-routes. And once we have this unit cell, constructing the power gate becomes trivial, where we just instantiate this unit cell within nested for loops. And then with these extensions, we applied a line to power management circuits in Intel 22FFR technology, which is a FinFET technology, and it combines features from both 22 nanometer and 14 nanometer. And we applied this to two low dropout voltage regulators shown on the right. One is an analog LDO, and the second one is a digital LDO. And these low dropout regulators are basically mandatory for noise sensitive and high efficiency SOCs. And these circuits required some of the building blocks, required high performance and high reliability. And as we generated these layouts, the circuits were fabricated, and here the die photo is shown on the bottom right. And to give one example on the latch comparator, we were able to demonstrate 10x to 96x faster mask design time. So this figure is actually showing the time cost with the manual layout and then different various entry points. And we can see as we put more time into it, we could actually significantly get productivity gains. This slide is showing a latch comparator, and it is comparing the Align generated layouts with the manual layout. Important thing to note here, you can see the manual layout, the engineer chose to consolidate PMOS devices in a single well, but the placement is not fully symmetric necessarily. And then you can see the Align layouts through entry point 1, 2, and 3. It's important to note that all of these comparators were clocked at 2 gigahertz and meeting the input offset specifications. And an important thing here is in the table here, which compares the key performance metrics, you can see that there is an Align entry point 3 version 1 and version 2. So version 1 was the first time we codified the placement and routing. And then after the first post layout simulation, we did quick iteration where we could actually improve the performance of the circuit within minutes. This slide shows the same comparator with additional circuitry for kickback noise mitigation. And again, we compare with a manual layout, which has been done by an experienced mask designer. And in this case, where we, for example, can see that the entry point number 1 did a suboptimal identification and placement of the replica DB, the differential pair that could be further optimized through entry point number 2 or entry point number 3. And here again, what we can see a clear trade-off and how we can basically spend a little bit more time and then reduce the area footprint while still meeting all the key performance specs. This slide shows the two-stage capacitorless analog LDO, and it consists of an op-amp, error amplifier, the powertrain, and the compensation capacitor. So we utilized Align to generate op-amp and the powertrain layouts and assembled together with the compensation capacitor. And for the capacitor, we follow the black boxing approach. So if you look at the modern PDKs, they typically offer these parameterized cell layouts. And we wanted to leverage that instead of drawing layer by layer from scratch, which would reduce the development effort and also make sure it's correct by construction. However, these parameterized cells may not be on the same routing grid that the automation is using. And we mitigate this by wrapping the P-cell layout and adding these additional pins that are on the routing grid. And then we could easily assemble this with the rest of the analog LDO components. And this slide is showing the manual layout, again, designed by an experienced layout engineer, and the Align generated and assembled layout. And on the table compares the key performance metrics for two different dropout voltages. And we can see that the Align generated layout is, again, very competitive with the handcrafted layout. And finally, we did generate some layouts for the digital powertrains. Here, we generated a 5-bit binary powertrain and a 64-bit thermometer-coded powertrain. Both of these had more than 2,000 fingers in total, and they had basically high current density and reliability requirements. For these circuits, actually, we didn't see any need to draw or create any manual layout, as the optimal placement and routing has already been codified. As we go through these exercises, we also continuously feedback learnings and enhancements to Align, which include constraint language enhancements. For example, to override subcircuit identification when there are false positives, netlist syntax generalizations, row-based primitives, and non-uniform metal grids that we will take a deeper look. So if you look at an analog IP today, it may consist of various device types. That means different threshold voltage flavors or oxide thicknesses. Again, the circuit may also consist of varying stack size, as stacking is commonly used to mimic a long channel device in FinFET or to lower random mismatch. And also, we wanted to respect the design engineer's intent in the transistor configuration. For example, in a FinFET, you can configure the number of fins, the multiplicity, and the number of fingers. So the example below is actually showing two different combinations for the same total size of a transistors A and transistor B. So the left is showing a more compact configuration, where the right is showing a more sparse configuration that might be preferable for more routing tracks or to reduce the power density. And the other two enhancements are the row-based placement and non-uniform metal grids. So one approach we followed is to design primitives that are integer multiple of a unit cell height, just like the standard cell design. And this greatly simplifies placement and also prevents design rule violations due to misalignment. And the second enhancement was to enable non-uniform grids. So analog circuits actually require wide tracks for lower resistance of high-speed signals, or to lower the resistance to meet the EM rules for high current nets. And one approach to do is, instead of a narrow grid, we could define a wide uniform grid. However, then this has a penalty on the track density. And in this case, non-uniform gives us an intermediate solution where we have wider tracks without a big impact on track density. With these learnings and enhancements, we are currently exercising Align on a more advanced FinFET technology. And this slide is showing some preliminary results. In this node, we are leveraging P cells even further, including transistors. And on this slide, we see the manual and Align generated layout for a current for a latch comparator and a current mirror OTA. Again, for both of the circuits, the Align generated layout meets or exceeds the performance obtained by the manual layout. So I would like to finish by thanking you for your time.
As we close out the presentation, we will present a couple of demos of circuits that use Align. We'll begin with a voltage-controlled oscillator or VCO circuit, which is being presented by Meghna.
In this demo, we will be generating the layout for a VCO circuit. This VCO circuit is a differential ring oscillator-based VCO circuit given to us by USC. The designer has provided a hierarchical netlist. There are also very few constraints in the circuit. At the top level, there are two constraints: sim block between the two differential ring oscillator stages, and a line block between the buffer stages that places them in a horizontal manner. We will now run this example. It takes about 2 to 3 minutes to generate the layout. The layout has been generated. It's taken 2 minutes and 17 seconds. We can view the results. The GDS is available, and we will import this into Virtuoso. The big metal layers here are part of the power grid, and you can see the transistors in the circuit as well. We will now run DRC and LBS to verify our result. We can now generate LBS clean layouts. We run exact to get the extracted netlist and verify the circuit's performance in simulation. Here we now have the extracted netlist for the VCO circuit and a test bench that is associated with it. We've set VDD and VSS in the test bench, and we also set the control voltage, which when changed, will change the frequency of oscillation. Once we run it, we view the performance results. The output voltage, it looks something like this, where there's an oscillating waveform. We can then measure the frequency of this waveform, which is 4.05 in this case, to associate a control voltage to the frequency of oscillation. The important specifications for this circuit is the frequency range, Fmax to Fmin, and also the control voltage difference between them.
Finally, we take the case of a mixer-first receiver and show how we can generate layout for this circuit. The demo is being presented by Jitesh.
Hello everyone. Welcome to the demo of creating a layout through Align entry point number 2 with custom-made cells. In this demo, we will see how to create a mixer-first receiver layout through Align 2. Before we go into the layout creation, let's look at the type of the receivers. The first one is the conventional receiver. In a conventional receiver, we have an LNA, which is the low noise amplifier, which sets the noise figure of the system. After the LNA, we have the mixer, which down converts the RF signals to IF signals, and the IF signal is then amplified using the IF amplifier. And after the IF amplifier, the signals are digitized using the ADC. Since the active circuit LNA is at the front end, we have a low noise figure in this case, but we also have a low IIP3. In a mixer-first receiver, we have the passive mixer at the front end, so it's a highly linear system, thus it increases the IIP3 of the system. But since we have a passive mixer at the front end, the noise figure of the system is higher than the conventional receiver. Let's look at the top plate mixer-first architecture. In a top plate architecture, we have the switch which sees the antenna signals and then it goes to the capacitor. The switches in this case are turned on using the clock signals 50, 590, 5180 and 5270. These signals are then given to the IF amplifiers. As you can see on the input side, we have the input spectrum with two signals. We have an in-band signal and we have an out-of-band signal. The in-band signals are down converted and then amplified using the IF amplifiers. And we can see in the output spectrum, the in-band signals are amplified. But for the out-of-band signals, they are spectrally filtered using the passive mixer front end and then amplified in this case. So we see a reduction in the amplitude for out-of-band signals at the out. In the bottom plate mixer first architecture, we can see that the switches are connected to the bottom plate of the capacitors in the green box, and the capacitors directly see the RF signal, RF plus and RF minus. These signals are then switched using the switches 50, 5180, 590 to the capacitor CB and then given to the IF amplifiers for amplification. The IF amplifiers have the transimpedance amplifier in this connection. Now we will see how to create the layouts of the transimpedance amplifier and the mixers. We can see the layers.json file, which is in the input directory over here, which has the layers information of the technology. We have also given the Verilog file of this blocks, which is the TIA amplifier, and we have the gtest.json file, which have the geometrical information of the layers. We can now run the align tool to create the layout. Align takes 4 seconds to create this layout. We can view the layout in K-Layout tool or in Cadence. We have already imported the layout of the transimpedance amplifier into Cadence. We can view this layout in Cadence now. As you can see, we have this TIA amplifier placed symmetrically, and we have the routes made in the specified layers. We'll now look into the mixer layout creation. For the mixer layout too, we have the Verilog file. We also have the constraints file given to the mixer. We can look into the inputs of this constraint file. In this case, we set the align block constraint to create a vertical alignment of the capacitors and the switches, and we also have given a criticality of the nets in this case. We'll now run the align tool to create a layout of this mixer. The layout has now been created. We can view the layout in Cadence. As we can see, the capacitors and the switches are placed symmetrically around a center vertical axis. Now we will use the TIA layout and the mixer layout to create the system level layout of the receiver. We have already created the layout for the top level receiver. We'll now view the layout in K-Layout tool. As we can see, this is the top level layout. We have the TIA layout placed at the bottom. We also have the mixer layout, which is placed at the top. And all the blocks have been placed symmetrically as per the requirements of the receiver. We will now look at the performance verification of these blocks. As we can see in the slide, we have the TIA layout placed by the align as well as the manual layout. The area taken by the align tool is smaller than the manual layout. We also can look at the performance verification in this case. The align numbers are very similar to the manual. We can also compare the layout done for the bottom plate mixer versus the manual layout. In this case as well, we have the align layouts taking a smaller space than the manual layout. This is the top level layout of the receiver. In this case, this layout is very similar to the manual layout, with the mixer layout placed at the top and the TIA placed at the bottom. Let's look at the performance of the receiver. If we compare the align layout versus the manual layout performance, we have the align layout IF bandwidth slightly higher than the manual layout. The reason for this is the PECs taken for the align layout is for the transimpedance amplifier and the mixer. It's the top. If we take the top level PECs of the align layout, the numbers will be very similar to each other. We also see the power gain and the noise figure numbers are very close to the manual layout. Thus, the layout created by align tool is comparable to the manual layout performance in this case. Hence, we can use the align tool to create layouts using the entry point number 2. Thank you for your time and attention.
This concludes the tutorial. We hope you've enjoyed it. We've tried to give you an overview of the notion of why analog layout automation is important, as well as a detailed look into an open source project on analog layout automation. This gives you insights into the algorithms that have gone into the approach, how we've developed the software, code base and how we've deployed it within university and industry environments. Thank you for your attention.
So, thank you, Professor Sapatnekar and his team. It was a very interesting tutorial, and there are a few questions which which have come. So, I'll just read out those questions, and the team can answer. So, this first question is from Professor from Pyare Sarkar of in Cadence, from Cadence. Pyare Sarkar from Cadence. Does Align software support crosstalk related guidelines for high speed long differential routes to make sure that their coupling to shielding nets are the same? So he wants to know that if there are differential signals and going on long differential routes, then their coupling to shielding nets is the same. That is a constraint, and whether Align considers these environment kind of effects.
Jiang, would you be able to take that question about shielding and matching?
Yeah, currently the Align router does have the feature for at the studio for specified route. So for this long differential signal, if there's such a specific specification, we do have this capability to add shielding, and we also can match the wire length as well. Yeah.
Yeah. Yeah. There is another question. So it is it is from Anand Kumar Mishra in ST Microelectronics. So do you think Align tool can be useful for digital layouts such as standard cells, such as using standard cells, as the constraints on matching are smaller and routing complexity is common, except that there may be denser layouts and lower metal utilization? So that's what is the question. So he's saying that the routing complexity is similar and in digital standard cell based designs, and the layouts might be more denser. So can Align support these kind of layouts also?
Arvind, since you're handling cell generation, do you want to take that?
Yeah, sure. So mainly we are doing like as we have discussed, we are having primitives, basic primitives in analog. So our cell generator can generate these layouts with different parameters like gate length, stacking, other parameters. But we are also working on the standard cells like base design for with one of our collaboration with the University of Michigan. They also want like a one open source kind of tool which can generate the standard cells with a given track height. So we have applied our Align tool on basic cells like pass gates and the transmission gates and inverters. So we were able to replicate the standard cells given by some given from Foundry with given cell heights. So the basic cells we have generated, but now we are working on some different, a little bit complex standard cells that we and we will try to generate those also. So right now, till now we have generated the basic cells like inverter, pass gates, and other cells.
Yeah.
Steve, would you like to jump into, because you've done a lot on standard cell design, I think?
Yeah, this Intel analog detailed router that Sonar was discussing in one of the last talks actually came out of work where we were doing standard cell-based layouts. So the design is using SAT for actually solving the routing, and it's quite powerful to use SAT technologies. when you're trying to route a very highly constrained design like you would have in a standard cell. So there's been a couple of papers on this over the years. There was one at ISPD 2 years ago that won best paper that discusses how to use SAT-based constraints to design standard cells.
There is another question that is from P. Tirumani from IIT Dharwad. So he's asking there is this threat of Trojans, hardware Trojans. So in analog design, is there? So it's not directly related to the tool. It is a question he's asking in analog designs. How important are hardware? Is a consideration of hardware Trojans?
Jiang, you've done some work on security. Do you want to take that?
Yes. I have done some work on hardware security. There are threats for hardware Trojan, but not in the sense of malicious attack. It's more like they put. So there's one example. There's by University of Wisconsin. They show how to use a single transistor and to put into analog circuit to monitor to steal some information. And from as far as I know, actually, it's more commonly seen security threat is not a Trojan. It's more of reverse engineering and piracy, because for analog circuit, the number of transistors is small, and it has a certain layout patterns. For example, symmetry. So if one takes one chip, if they polish the layers, it's much easier to reverse engineer than those digital circuit. So there are some work to do. Like we did some work on locking to mitigate this risk of reverse engineering of analog circuit.
So there is another question that has come from Chaitanya Lakshmi from Global Foundries. So she is asking whether this Align tool can be used for triple well technology layouts.
If I can answer that, the design that we talked about, the VCO in 65 is a triple well design process. So it can definitely be used in a triple well process.
So this finishes the questions that have come. So thank you very much for the tutorial. This was an invited tutorial, and it was, I think, there are no new questions, so we can close for lunch. And we will again meet at 1:15 Indian Standard Time at 1:15 p.m. for the next tutorial.
Thanks to all the attendees on
is on scaling the memory wall 2.0. What, why, and how. So this is the tutorial topic, scaling the memory wall 2.0, what, why, and how. So the speaker is, there are three presenters in this tutorial. One is Professor Preeti Ranjan Panda of Computer Science and Engineering Department of IIT Delhi. Professor Panda has done his PhD from University of California at Irvine, and he has been a faculty member, a professor in the CSE department of IIT Delhi for a very long time. Earlier, he had worked in Texas Instruments, Bangalore, before joining IIT Delhi, and he was also a visiting scholar at Stanford University. He has authored two books on one on memories, memory architectures in embedded systems, and the other on low power design. And he is the chief editor of IEEE embedded systems letters, and he was on the editorial board of several IEEE journals and transactions, TCAD, etc. So Professor Panda has been extensively working in this area for a very long time. And then I'll briefly introduce the other speakers. I'll not take much time because the tutorial is more important. So Professor Sandeep Chandran is a faculty member in IIT Palakkad. He did his PhD from IIT Delhi, and where he received Best Industry Relevant PhD award. And he was a senior design engineer in AMD, where his work was on Zen microarchitecture. And he works in he also worked as an intern in Freescale Semiconductors. He is currently working towards finding ways to reduce the effort in verifying complex processors and systems on chips. So he works in the area of alternative design for high performance processors. The third speaker is Professor Rajshekhar Kalayappan. So Professor Kalayappan is working presently at IIT Dharwad. So he has worked, he did his PhD in IIT Delhi. He worked extensively in computer architecture, hardware reliability, hardware security, etc. And microarchitectural simulation. So he maintains a popular open source architecture simulator called Tejas, and one can get in touch regarding Tejas with Professor Kalayappan. So now we start the tutorial. The questions can be sent on in the chat box, and they would be taken after the tutorial is over. This is a 1.5 hour tutorial. Right. Let us start. The video would be started.
Scaling the memory wall 2.0. What, why, how? I'm Dr. Sandeep Chandran from IIT Palakkad. In this tutorial, we would also have Dr. Preeti Ranjan Panda from IIT Delhi and Dr. Rajshekhar Kalayappan from IIT Dharwad co-presenting this tutorial. This tutorial would have three parts. In the first part, we'll introduce the background of what memory wall 1.0 was and how we scaled it. What are the new emerging memory technologies available as of today, and what is memory wall 2.0. In the second part, we will be looking at prefetching and how we can intelligently use the on-chip resources in trying to overcome or scale the memory wall 2.0. And in the third part, we will be looking at partitioning, where we would reserve certain on-chip resources in order to try and scale the memory wall 2.0. A typical computer system would have a CPU, a DRAM, and an interconnect which is joining or which is connecting the CPU to the memory or the DRAMs. So this forms the hardware of the computer system. On top of this, you would also have the software running. In this case, I'm just indicating a C-like code snippet where you have a for loop that goes from 0 to n, and the loop body just contains one statement, which is sum equal to sum plus I. So here I, n, and sum are variables. If we compile this code, we would get a corresponding assembly code that looks something similar to this. So the first two instructions are basically initializing the variables I and sum to 0. The third instruction onwards is the loop body, where the third instruction add R3, R1, R3 is doing the equivalent of sum equal to sum plus I. The fourth instruction add R1, R1, 1 is incrementing the value of I. And then the last two instructions, the compare and jump less than equal to is doing the I less than equal to n check. So needless to say, here R1 is a register that is storing the variable I. R3 is the register that is storing the variable sum. And R2 is the register that is holding the variable that is corresponding to the variable n. Now, to begin with, the program resides in the disk. It is then brought into the memory. So even before it starts executing, you can say that the program resides in the memory before it starts executing. And once the execution starts, this program is then brought into the CPU for execution. And as it is executing inside the loop, you would see that most of the operations are just register manipulations, and so you would not really have to access the memory. The entire execution can proceed only on the CPU. So this brings us to the first the observation, where we say the overall performance of this program is limited only by the performance of CPU, because once the program is brought into the CPU, it no longer accesses the memory for that code that we indicated. But that is just one kind of code. An equally popular and equally prevalent code is as shown here, where inside the loop body, you are accessing an array. So you have sum equal to sum plus array of I, or A of I. Okay. So the corresponding assembly code would look like this, where you have an additional load instruction that is coming to the assembly sequence. So you have load R4, 4 of R1. So here 4 is basically indicating the base address of array A, and 4 of R1 is the address of A of I. And when you say load R4, 4 of R1, you're basically taking the data that is stored at the address of A of I and loading it or moving it into the register R4. The rest of the loop body is similar to the one that we saw earlier, where you have R3 being added to R4 and the result being stored back to R3. So R1 holds the value I, R3 holds the value of sum, and R2 holds the value of n as earlier. So when this particular code snippet executes on the CPU, you would see that the CPU generates a request to the DRAM. So when the load R4, 4 of R1 executes, the CPU sends the physical address of A of I to the DRAM, and the DRAM would then search for the data that is stored at that address and return that. So DRAM responds with the data stored at that address. So what was given out was an address, and what is responded is the data. The next instruction, which is add R3, R1, R3, can complete only after the previous instruction, which is the load instruction, completes. This is because we want the instructions to commit one after the other in the same order as the programmer had specified. So in this case, we notice that the performance of the program not only depends on the performance of the CPU, but also depends on the performance of the DRAM. And typical applications have around 30% of their instructions, the dynamic instructions, to be memory accesses. And in applications such as web servers, these percentages can go higher. So if you look at a realistic system, the performance of the DRAM plays a very crucial role in the performance of the program. However, the primary focus of the memory designers was on increasing the capacity of the memory. So, whereas the primary focus of the CPU designers was on increasing the performance. Okay, so when we talk about performance of the CPU, we are looking at the number of instructions that were executed in a unit time. So the focus of CPU designers was on increasing the number of instructions executed per unit time. The focus of the memory designers was to increase the RAM capacity by increasing the density of the memory chips. So we wanted, say, the main memory to go from 4 GB to 8 GB to 16 GB and so forth. Because of this difference in the focus of difference in the design focus, what happened was the performance of the CPU started scaling at a much faster rate than the rate at which the performance of the memory was scaling. And this led to a performance gap, and memory modules became a performance bottleneck. And this performance bottleneck is what we call as memory wall 1.0. So in order to scale this memory wall, the CPU designers started modifying the CPU design to overcome memory side bottlenecks. This also allowed the memory designers to focus primarily on capacity and increasing the capacity of the DRAM. A higher capacity of DRAM does indeed improve the performance of the CPU fairly well. And so it is not that both of these groups were working at tangent to each other. It was just a clearer separation of responsibilities, so to speak. The CPU designers used a two-pronged approach. The first approach was improvements in the pipeline design. When I say pipeline, it means the execution pipeline, where features such as multi-threading and out-of-order execution were implemented. And in the second approach was to introduce these on-chip caches into the processors. So the important point here is that the design improvements that were proposed by the CPU designers are transparent to the software. Okay, so the instructions that were generated by the compiler can remain as is. You don't really have to tweak the compiler to do anything different. The older code also would continue to run as is. The instructions, once when they're executed on the CPU, they would continue to generate memory access requests, and these memory addresses were that would eventually hit the physical addresses of the DRAM as earlier. So there is no change in that. But like I said, the additional circuitry that the CPU designers implemented would prevent some of these memory accesses from reaching DRAM. They would try to handle these memory requests within the CPU itself. So if you look at only the load instructions issued by the CPU, which is the I3, the instruction, the third instruction, the 8th instruction, the 13th instruction, these P1, P11, P21 are basically holding the different values of I in subsequent iterations. So it will be P of 4 of 0, 4 of 1, and 4 of 2. So your I3 would be accessing A of 0, I8 would be accessing A of 1, I13 accesses A of 2, and I18 is accessing A of 3, so to speak, right? Okay. So memory locations that are currently adjacent to the location that is being accessed now are more likely to be accessed in future, because you can expect such loops to be fairly common where you're iterating over an entire array. Okay, so this is one observation that is there. The second observation is that you can also have these nested loops where, let's say you have this loop, this is the inner loop being executed for m times because there was an outer loop outside. So what would happen is that these locations A0, A1, A2, A3 are likely to be accessed again in the near future. So this is called temporal locality. The earlier one was called spatial locality. Okay, and by caching, what we do is we take those values and keep a copy of it inside the CPU itself. So what happens is all the subsequent memory requests do not have to go till this RAM, but instead those requests can be serviced from within the CPU. Okay, so caching basically exploits both the spatial and temporal locality of accesses in a way that if you have a copy of A inside the CPU, subsequent accesses can be serviced from the CPU, and you really don't have to go to the DRAM. We now look at the cache hierarchy, or how to organize these caches in an effective manner. So the cache basically has two internal arrays. One is called the tag array, and the other one is called the data array. Okay. The address that is issued by the CPU is split into two components. One is called the offset, and the other is called the tag. So when the CPU or the pipeline issues a memory address, that address, the tag in that address is matched with the tags in the tag array, and all of this is happening in parallel. So you take the address tag and you see if any one of these locations in the tag array has the same tag as the incoming address tag, and if the tags match, you return the data that is corresponding to the matched tag. Okay, so let's say, for example, 0x1234 was the tag that is stored, and it's 0x1234 is also the tag at the address. Whatever is the data corresponding to this location, this where the tag matched, that data is returned on the data bus. If in case the tags don't match, the address tag does not match with any of the stored tags, then we call that a cache miss. And if there is a cache miss, the incoming address is then passed on to the memory for the memory to respond to the request. Okay. The control lines are used to indicate whether it was a cache hit, cache miss, whether you are trying to read data or write data, and so forth. The address and data lines are used to communicate the address and the data. Okay, so let's take this example and understand what are the different kinds of misses that are possible in a cache. So the very first time you get an address sequence, this is the address sequence, and the very first time you get an address, that is certainly not present. The address tag is certainly not present in the stored tags, so you would get a miss, and those misses are called compulsory misses. So you can just fast forward a little. You would get a compulsory miss for 0x1234, 1235, 1236, 1237, because there are 4 locations where you can store data. Then when you get 1238, you would see that this cache, there is no more location that is possible here, but this is the first time you're seeing an address 1238. So this also would be counted as a compulsory miss. But this address, this 123800, would have to replace one of the addresses or one of the locations where it was already stored. So let's say we go and overwrite 0x1234. And typically these are what are called as replacement policies, and these replacement policies will dictate which among the 4 lines would a newly incoming line have to evict or replace. So here we have used the least recently used, because If you go back in the address sequence order, the least recently used address was 1234. So your newly incoming line, which is 1238, is going to replace the location where the data corresponding to 123400 was stored. Okay, so all of these are compulsory misses because you are seeing these addresses for the first time. Now, when you come back and see this 0x1234 again, you had already seen this address sequence before, but then that got evicted by 0x123800, which came before this 123400. So in some sense, had we had a larger cache, this particular access request would not have seen a miss. And as a result of this, what would happen is the least recently used line in this case is this 1234.500. That would get replaced with this line 0x123400. Okay, so just to recap, 0x123400 was already seen before. Just because the cache had only 4 entries where it could store data, and we got 5 different data to store, one of it had to get replaced. And when that same data is requested again in the future, you would see a capacity miss in that sense. There is one other way to organize caches, which is called as the way or set associative caches. So in this case, what you do is you replicate the data in the tag array multiple times. So one such data and tag array is called way 0. The other tag and data array is called way 1, right? And now you would have what is called as set. Okay, so this particular index where there is both data and tag in way 0, this at the same index you have data and tag in way 1. These two together is called a set, and this index here, a few bits in the address, is used to index into these sets. Okay, so what we are showing here is a two-way associative cache. So now that we have understood the set associative caches, let us look at the third kind of misses, which are called as conflict misses. To understand conflict misses, let's consider this address sequence as shown here. So we would see that the addresses 0x12400 and 123600, these two would result in set 0, and that's why tag A and tag B are sitting in the two different ways of set 0. The next address access, which is 0x123700, would result in set 1. It would hit in set 1, and so tag C would be in way 0 of set 1. And here, all of these would be the compulsory misses. The next one, where you're seeing the address D, 0x123800, this would again hit on set 0. Okay, so this would also be a compulsory miss, and as per LRU policy, this would go and evict the tag A. Okay, now when we get the access to 123400 again, we see that this also goes to set 0, but that got overwritten by the previous access, which was to tag B. Okay, and now although there is capacity to hold one more line here, this which is in way 1, set 1, we cannot use it because of the way in which we have defined the sets and the set indexes. Okay, so these are called conflict misses because the addresses 123400, 123600, and 123800 are conflicting on set 0. So now that we have understood how a basic cache is organized, which is into tag and data arrays, and also into different ways, let us look at how we can use these basic cache modules to increase the overall design of the CPU. So instead of having just one cache, you can always have multiple levels of caches, in which case you call this the L1 cache and the L2 or the level 2 cache. So if the data is not present in L1, you would forward that address to L2, and L2 would be a larger cache. And because it's a larger cache, you expect some data to be in L2, which is not there in L1, in which case this also gets checked before the address goes out into the main memory, right? So you can have multiple such levels of caches, which is like L1, L2, L3, and if the data or the address, the data corresponding to their address is not there in any of these caches, only then it will go to the main memory. Now, the question is, why can't we have one big cache, which is basically the sum of the capacity of L1, L2, and if there's an L3, L3. The reason is, as the cache size increases, the access latency also increases. You want the L1 cache to be small so that the pipeline can try and access most of its accesses would hit only in L1. Only cases where the spatial or temporal locality is not satisfied, the CPU accesses a line which is very far away, then you might want to go to L2 or L3 further. So the lines that are spatially and temporally local would be in L1, which are temporally slightly far away or spatially slightly far away would be in L2 or in L3. So what this would result is that the pipeline which is trying to access, which we expect will be accessing the L1, which will be accessing the temporally and spatially closer lines, those accesses would hit only in L1. So typically we would see that the L1's hit rates are over 90%, which indicates that 90% of the accesses are being serviced out of the L1 cache. Similarly, you can also think of having two separate caches, one cache which is holding all the instructions, one cache holding all the data, and these caches can be small, so they'll be really fast, but then they're replicated at the level of L1. So you have an L1 I cache and the L1 D cache, but the L2 cache can be a unified cache where both the instruction lines and the data lines are residing inside the same L2 cache. So with this, let's try and take a real-world example of Intel Skylake and to try and see what are the different kinds of caches that are possible. So here you see that this is a multi-core system. So you have CPU1, CPU2, and inside the CPU you have the caches. So here they are going with a split cache. So you have an L1D and an L1I. You have a unified L2 cache, right? And the L1 and L2 caches are private to this particular CPU. Similarly, this L1I, this L1D, and L2 is private to this CPU. And beyond the CPU, beyond the private caches, you can also have a shared cache called the L3 cache, which is the last level cache here, which both the CPUs are sharing. So L3 is a shared cache, L1 and L2 are private caches. L1 is a split cache, L2 is a unified cache, but L1 and L2 are private caches. So beyond this, you have the DRAM, which is coming outside off chip and so forth, which we will worry about in the coming slides. So what is Memory Wall 2.0? Now that we have managed to introduce modifications to the pipeline, we have managed to introduce modifications into the CPU design by adding caches. Have we not solved the Memory Wall 1.0 problem? Yes, we have solved the Memory Wall problem to a certain extent, but over the years, the applications have become fairly data intensive, and now the miss rates are still quite high for these data intensive applications. One of the reasons why these miss rates are high is because these data intensive applications bring in a lot of memory in into the CPU for computations, and caches can fall small or can fall short. The other problem with the data-intensive applications is the limited off-chip bandwidth that is available. When the requests have to go over an interconnect to the memory, the interconnect themselves can become a bottleneck. The second issue that has come up with the multi-core era is that of inter-application interference. So what does this mean is memory accesses from multiple threads or multiple cores can conflict in the unified caches or the shared caches. Okay. The other problem that can come is the accesses from one thread can evict the lines of the other application. So where we were talking about the address sequences, these address sequences can be from multiple threads or multiple cores which are coming in conflicting at the caches. Similarly, you can think of a scenario where one application can consume a whole lot of off-chip bandwidth, thereby starving the accesses of another application, in which case you see that the performance of the other application starts dipping in presence of another application. Now, these are the kinds of issues that are coming up and what we call them as the memory wall 2.0. And one of the reasons is that the multi-threading and caching alone has not solved all of these problems, and newer architectures and designs are now necessary to scale this memory wall 2.0. Now, what are the early directions to scaling the memory wall 2.0? So we have some support from the manufacturing technology, wherein we are now able to stack chips one on top of the other. So in this case, we are showing that a CPU or a compute die has been stacked with multiple memory modules or memory dies, one on top of the other. These are called as embedded DRAMs, and these would also solve some of the problems around the off-chip bandwidth that is there. So the CPU would now not have to request data that is there here. The CPU requests can go within the chip up multiple layers into data or memory modules that are stacked on top of it. So this is the technology advances that are helping us scale the memory wall. There are also some support coming from design changes that can help scale this memory wall. One such big design changes is that of prefetching. And in prefetching, we are bringing in data from memory before it is requested. So thereby, we can try and hide the memory latencies to a certain extent. To do this, we might have to predict what are the future addresses that might be accessed by the CPU, and then you try and really bring those addresses in before that. Similarly, prefetching can also be used to better use the off-chip bandwidth by scheduling these off-chip requests in an intelligent manner. Similarly, to cut down on the interference, we can also reserve the system resources, and what are the resources that are limited or reserved would be discussed in the coming parts.
So we have seen how caches can help improve performance. When the pipeline demands some memory content, if we can find that content in a cache, then the pipeline gets its required content quicker and can hence move faster. And we can see an overall improvement in performance. This is known as a cache hit. But if we don't find the content that we're looking for in the cache, then we have to go search in the lower levels. And it's known as a cache miss and is actually detrimental to performance. So ideally, we would like a lot of hits and few misses. So how do we increase the number of hits? One way of doing so is known as prefetching. The idea is to guess beforehand what requests the pipeline is going to make, and then bring that content into the cache such that when the pipeline actually makes the request, the content is found in the cache and hence turns out to be a cache hit. So in the next 20 minutes or so, we will explore this technique further, understand it better, see what the challenges are to implementing a good prefetcher, and see what exciting opportunities are available. So let us take a simple example to understand prefetching. Let us say we want to sum the elements of an array as depicted by the code in the top left of the screen. Let's assume we have a simple architecture as in the bottom left of the screen. We have a pipeline, we have a memory, and we have one level of cache in between these two. Let us assume that the cache is empty for simplicity's sake. So when this piece of code runs and tries to sum the elements of the array, it does not find any of the elements in the cache. So each of the 100 requests end up going to the memory, and so we see very low performance of our application. But if you notice, the accesses have a very nice pattern. So if we assume that array A was present in address 1000, so we're going to access address 1000, address 1001, address 1002, address 1003, and so on. Right? So can we somehow exploit this nice pattern? So let's say when we're accessing A of I, can we also prefetch A of I plus 1, because we kind of know that A of I plus 1 is going to be used in the next iteration of this for loop. Right? Generalizing this statement, when A of I is being accessed, can we prefetch A of I plus j such that later on when the pipeline asks for A of I plus j, we actually find the content in the cache itself. Right? So this is the overall idea of a class of prefetchers known as the stream prefetcher. This is widely used in today's processors and is known to be a great boost to performance. Right? Now that we have the basics covered, let's see what it looks like in terms of hardware. So prefetcher is usually an auxiliary, have no bearings on the architectural state, and so they have no effect on the correctness, and they're completely invisible to the software layer. So this idea of prefetching can greatly increase the hit rate of a cache and greatly improve performance. But there are a variety of challenges that we have to face. The first challenge is that of pattern recognition. So in the example that we saw, the pattern was a simple linear stream, which is quite easy to detect and then exploit. But patterns may not always be that simple. Right? There are many popular patterns that are quite irregular and quite complicated. What do we do in those cases? How do we detect the pattern, and then how do we exploit and issue prefetches? So let us look at some of the strategies employed by researchers. The first broad class of strategies are known as temporal prefetching. So let's discuss this with the help of an example of searching in a linked list. Okay? The code to do this is in the bottom left of the screen. It's a simple piece of code. You just need to go to each node, see if the value of the node is the value that you're looking for. If yes, great, you can return. If not, you use the next field of the node to go to the next node and then repeat the process all over again. So while doing so, you can see that here the addresses that the code is accessing are not in a very regular pattern, right? In the array sum example, we simply had a linear sequence of addresses. But here, in the case of the linked list, we are first accessing 1, 2, 3, 4, then we're accessing address 4, 5, 6, 7, then 2, 2, 2, then address 7, 7, 7, 7, right? So this is a very irregular pattern. So how do we detect this and how do we exploit this for the purpose of prefetching? So the idea is something like this. So the first time the search function is called, the prefetcher notes that addresses are made in the order 1, 2, 3, 4, 4, 5, 6, 7, 2, 2, 2, 7, 7, 7, 7, and so on. Right? The next time the search function is called, and the prefetcher starts noting the addresses that are accessed. It notes 1, 2, 3, 4. It notes 4, 5, 6, 7. Then it notices that it has a previous record of a stream. The previous stream that it had recorded was 1, 2, 3, 4, 4, 5, 6, 7, 2, 2, 2, 7, 7, 7, 7. And now the current accesses made by the pipeline are actually 1, 2, 3, 4, and 4, 5, 6, 7. So the first two elements are actually patching the stream that it has already recorded previously. So since it has seen that there is some match, it can start issuing prefetches for future elements of the same stream. So when 4, 5, 6, 7 is accessed, the prefetcher can detect that, okay, this particular stream is being exercised, and it can go ahead and guess and prefetch 222 and 7777 and maybe more elements after that as well, right? So this way, the subsequent elements 222, 7777 find a hit in the cache rather than a miss. So this technique is known as temporal prefetching, and it is really great for repetitive irregular patterns as seen in our example. One important thing that we have to think about is, okay, so when we detect a stream, how many more elements from the stream should we actually prefetch, right? Should we prefetch just one element in the stream, or the next two, or the next three? How many, right? So the first guess would be just let's fetch as much as possible, right? So let us, whatever comes into the cache is good for us. We'll maximize the number of hits. And if some of the things that we bring in are not used, well, who cares, right? It's not used. But that's not actually a very great strategy, because we will see in the coming slides why that can be detrimental to performance. Okay? We will see that. So deciding how many elements to prefetch is actually a critical decision and is known as throttling of the prefetcher. Okay. So we will see why, what is the detrimental effect of aggressive prefetching in the coming slides. Before that, now that we've seen temporal prefetching, another class of techniques that has been widely explored is known as spatial prefetching. So to explain this, again, let's take a nice intuitive example. Let us consider a database application. So databases, as you all know, are made of tables. And let's assume that we have a large table and the tables are spread across many pages. Right? So each page will end up having a similar kind of structure. Maybe the first few words in the page deal with locks, right? So database servers are usually parallel applications. So we need to make sure that no two threads of the database server are, illegally modifying the same page at the same time, and so same part of the table at the same time. So to ensure this, locks are usually maintained. So maybe the first few words of a page are actually the locks. Then maybe the next bunch of words would be the primary keys, the secondary keys of the data contained in that part of the table. Then maybe we have some more words that are dedicated to recording certain statistics. And then we may have the rest of the page that's holding the data of the table itself, right? So when we're searching for something in the database, in the table, it would probably look something like this, that we go to the first page that the table is occupying, we lock the page, then we go through all the keys to see if the key that we're looking for is actually there in that page. If we find the key, then we go to the data section and then pick the data. And if we don't find the key, then we'll actually be having to move to the next page. But before doing that, we have to update the statistics, and then we have to unlock the page before either returning in case of finding, or in case if you found what you look for, or you have to move to the next page, right? So the sequence of accesses are usually similar. So if you didn't find what you're looking for in page 1, we go to page 2 and do the same thing. We lock the page, we go through the keys, we access the data section if the datum is present, we update the stats, and then we unlock the page, right? So on every page, the pattern of accesses are the same, right? The portions that we access are the same. So can we do this when we are going to page I? Can we prefetch all these parts of the page that are popularly accessed, the locks, the keys, the stats, right? We can prefetch all these parts of the page such that all these accesses end up as cache hits, right? So what are we exploiting here? We're exploiting the fact that the accesses made within a page have a certain spatial arrangement about them, right? So we're exploiting this fact and triggering prefetch requests. So when we are exploiting these spatial patterns, the techniques are known as spatial prefetching. So spatial prefetching has a unique capability of being able to tackle compulsory misses. Let's say we are accessing page X for the first time, right? But we know it is part of this particular table, right? So we know that page X will also follow the same pattern of locks and keys and stats and so on. So we can prefetch those things even though we have never seen, the pipeline has never made accesses to those parts of the memory before, right? So it has, spatial prefetching has this unique capability of tackling compulsory misses. Right, so these are two broad styles of designing prefetchers, temporal and spatial. Researchers have widely researched both of these techniques as well as combinations of them. And this is still an open and rich area of research. Okay, now let's move on to the next challenge. We just spoke about what to prefetch in terms of how to detect patterns and how to exploit patterns. Now let's go to another question of capacity, right? We are prefetching and bringing content into a cache that's of finite size, right? Remember we spoke about throttling and about aggressive prefetching. If we go ahead and prefetch too many things, right, in the hope that at least some of them will be hits, if the others are not hits, I'm fine with it. That kind of strategy can actually prove detrimental because the cache may fill up. The cache may fill up with potentially unused data, as a result of which many useful things may get evicted, right? So let us consider this extreme example where even though the content that we are bringing in as part of a prefetch is useful, it is evicting another piece of data that's actually more critical to performance. Okay, if you can look at the example, there is a assembly code snippet on your left, and the same code snippet is represented as a data flow graph in the middle pane. Okay, so let us focus on the three loads, I1, I2, and I3. You can see that the load I1 must complete first for I2 and I3 to begin. Okay, because of a pure data dependency. Now between I2 and I3, we can intuitively say that the load I2 is more important to performance because there are a lot more dependents on it. And so whether or not I2 finishes fast is very important to the performance of the overall application, right? So let us consider this example scenario where I1 loads from address 10,000. I2 would like to load from address 23456. I3 would like to load from address 10,004. Now let us assume that as part of fetching address 10,000, we prefetched address 10,004. Now let us further assume that this 10,004 ended up evicting 23456, which was already there in the cache, right? So we decided to prefetch. We brought in some useful content, that is 10,004, and that helped I3 to finish fast. But we ended up evicting 23456. As a result, we ended up delaying I2. And as we earlier discussed, I2 is more important to performance than I3, right? So we have delayed I2 and made I3 fast, but the overall runtime of the application has actually increased, right? So even though we did a successful prefetch in terms of actually helping I3 finish fast, the entire application has actually become slower, right? So we need to be very careful about what to prefetch in terms of the limited capacity of the cache, right? This is another challenge of prefetching. Third challenge. Let us talk about when to prefetch, and let us talk about an issue of lateness. Okay, so let us look at the left pane first. The left pane represents a desirable behavior, right? First, at time t1, a prefetch is issued for address A, right? At a further time t2, the particular content is brought to the cache, and at a further time t3, the pipeline actually accesses address A, and it finds the content in the cache. Everything's well and good. This is what we wanted to see. Now let us look at the right pane. Okay, at time t1, prefetch was issued for address A. At time t2, the pipeline accesses address A, but the prefetch is not yet completed. right? The prefetch completes much later at time T3, and that's when the content is brought to the cache. So between time T2 and T3, the pipeline was actually waiting for the content to be available. So what has effectively happened, our prefetch was actually issued late, and it was so late that when the demand was made by the pipeline at time T2, the content was not available. So the pipeline was forced to wait from T2 to T3 until the content was available. So this is not a desirable scenario, right? So this is a problem of lateness. So we need to issue the prefetches early enough such that our demand accesses by the pipeline are satisfied in time. But wait, should we then issue things too early? Is there such a thing of issuing too early? We have noticed that even that is also a problem, right? So again, the left pane is the desirable sequence of events that we discussed from the previous slide. But the right pane shows the problem of issuing prefetches too early. Let us see what happens. So at a time T1, prefetch is issued for address A. At time T2, the content is brought to the cache. At time T3, the content of A ends up getting evicted by some other content. Okay? And at time T4, the pipeline is demanding that, okay, I want A, but it has already been evicted, right? So we did issue a prefetch. We issued a prefetch for the correct address A. We were good at guessing that. But we ended up issuing it so early that the content came to the cache and also got evicted by somebody else, right? So we issued a prefetch that amounted to nothing. The pipeline did not benefit from that prefetch at all, right? So too early is also a problem and too late is also a problem, right? So that is the fourth challenge. Now let's look at some more challenges. So between any cache and its lower level cache, or if the memory is the main memory is what is located below the cache, there is a finite amount of bandwidth, right? It can only support so many demand and or prefetch requests at the same time, right? So the bandwidth between a cache and its lower level cache has to service both demand requests as well as prefetch requests, right? So since this is a fixed resource, we need to be very prudent in using it. So if you want to issue a prefetch, we need to weigh the benefit of this prefetch content against the loss due to bandwidth contention. Because you are issuing this prefetch, maybe some other demand request is getting delayed because it's not finding the bandwidth free, or maybe some other prefetch request is getting delayed. That is possible. Another thing that we have to consider is maybe there are times during the execution that the bandwidth is relatively more free, right? Maybe the requests being made by the high level cache are fewer. It may be a prudent idea to use such periods of low utilization and issue our prefetch request during that time. Okay, so to summarize the challenges, our first challenge is how to recognize the pattern and how to exploit it. Right? It's not always as simple as a stream prefetcher. We sometimes have to do more complicated analysis to detect patterns and exploit them. The next challenge is that of capacity. We cannot be overly aggressive while issuing prefetches, because that would mean eviction of other content which could be potentially useful. So we need to weigh the benefit of the content we are prefetching versus the content we are actually evicting from the finite sized cache. The third challenge in the WAT series of challenges is that of bandwidth. As we said, we should weigh the balance of the benefit to be gained by prefetching something versus the contention in terms of bandwidth. The fourth challenge is lateness. That is, we have to issue prefetches early enough such that when the demand request is made, the content is available in the cache. If we are late, then the performance gain due to the prefetching reduces. The next problem is that of earliness. So if we issue prefetches too early, then the content that we prefetch may get evicted and the prefetch may turn out to be useless. And the last challenge is related to bandwidth. We should look out for periods when the bandwidth is relatively underused and try to exploit those periods to issue more prefetches so as to not starve demand requests. Right, so these are the overview of the various challenges that a designer of a prefetcher would face. So, moving on, as we discussed in the early portions of this talk, that 3D memories are fast becoming common. So, what does this mean for a prefetch architect or a prefetcher designer? So, the first thing is 3D memories provide a significant increase in memory bandwidth. Can this be used to improve prefetching to the last level cache? Intuitively, larger memory bandwidth leads to lesser bandwidth contention. So this must strike a bell in terms of our list of challenges. So we can therefore tackle the what issue that was related to bandwidth. That is, we didn't want to issue too many prefetches such that they were competing for bandwidth with other demand requests or other prefetch requests. And we can also tackle the when bandwidth challenge. That is, we were worried that we should only send prefetch requests only at times when the bandwidth is relatively less utilized. But now we don't have to be worried about that too much because of the large increase in bandwidth brought about by 3D memories. So this area is now being researched quite actively, and it's quite exciting. Let us look at another domain of research within the prefetcher design area. So this is related to NVM-based on-chip memories. So NVM stands for non-volatile memories, and various companies such as IBM, Samsung, and others have managed to realize non-volatile memory-based on-chip memories, either in terms of the RAM or the last level cache. So what nice properties these NVMs have are that they have significantly higher density as compared to standard SRAM, which is used for making caches these days, right? So since we have higher density, we can actually achieve higher capacity caches in the same area, right? So now that we have higher capacity caches, how do we make use of them? Can we somehow use that to improve prefetching? Again, it may ring a bell. We were faced with a capacity issue, right? We were worried that we may prefetch too aggressively and end up evicting other useful content. But now if our caches have become much larger, the worry of this eviction, or what is known as termed as pollution, the worry of this pollution has now reduced, right? And another problem that can be tackled is this earliness problem, right? We were worried that we may prefetch something too early and it may end up getting evicted by somebody else, right? Before it is even used by the pipeline. So the chance of this happening also reduces when the caches become significantly larger. Okay, but so non-volatile memories don't just come for free. They have certain drawbacks. As compared to SRAMs, they have larger latencies. They have, and significantly in terms of write latencies, right? They take much longer to write. So this makes the problem much more interesting, right? You have the advantage of higher density, but now you also have this drawback of larger latency. How do you balance both? How do you design a prefetcher that exploits the good features of NVM-based caches and cleverly sidesteps the drawbacks of the NVM-based caches? Or researchers are also exploring hybrid caches where a part of the cache is composed of standard SRAM while the rest of the cache is composed of non-volatile memory space cells. So yes, this problem is quite exciting, and these are interesting times in the design of prefetchers.
In this part of the tutorial, we will study cache partitioning, and towards the end also touch upon main memory involved in the partitioning function. The objective of such partitioning usually would be to minimize interference among applications and maximizing utilization of the cache and the main memory. The outline of this part is as follows. We will try to motivate the problem first, and then discuss a couple of different aspects of partitioning and how they are relevant. First, about partitioning the space of the cache memory, and later about partitioning bandwidth of the cache memory. Let's study a few different scenarios. The first one of which is I have an application 1 that is running on a CPU 1, and let's illustrate its cache behavior. So what we showed was that it's getting a lot of data into the cache. It's accessing a lot of data that pretty much sweeps the entire cache, but the lifetime of each of those data elements is short, and the cache and the application pretty much needs effectively a small amount of space, because the lifetimes are small, and maybe the space could have been reused, or space of one data element could have been reused by the other one. If we gave it a relatively small amount of space, it might have been okay. So this application pretty much needs a relatively small amount of space. Let's compare it to application 2 running on the CPU that actually is accessing a smaller amount of data, but nevertheless is keeping it in the cache for a long time. It requires the data for a long time. Perhaps there are multiple computations happening on that data. So you can see the sort of behavior is very different of the two applications. Let's ask this question: what happens if now I have both CPU 1 and 2 sharing the same cache? Now data from the multiple applications, data and instructions of the multiple applications would be sharing the same cache. That might lead to some kind of behavior as follows. So two of the elements came in of the second application, and then this first application started. It threw out those two elements, and later on we have two other elements. What happened in of the two other elements of the second application? Now, what happened in the process was that some useful data of app 2 was thrown out by app 1 because of the nature of the two applications. What this is just showing in a very simple way is that there is an interference at the shared cache between the two applications. The question then is, can we do something about it? What could we do about this? Maybe we can partition the shared cache. Let's go ahead and allocate one partition to the first CPU. This is the first half of the cache. And maybe the second partition to the second CPU. What happens? Now, if I start execution, the second application goes ahead, and anyway it needed only half the cache, so it nicely uses the half of the cache. Never gets thrown out because we have achieved some isolation in the process. The first application is now restricted to just the first half. It doesn't affect the second half, and therefore this is one way of making sure that you don't really compromise on performance. The second application performed as well as earlier, but even the first one was not really affected because that was the kind of application that did not really require a lot of the cache, even though it got in a lot of data. In fact, the kind of data was such that the same space could be reused. You did not need to keep the data in the cache for too long. So you can see that if I understood the nature of these applications, maybe I could do a better job by effectively isolating the space that we allocate in the cache to the two different applications. So that's the idea of cache partitioning. Conceptually, hopefully the idea is clear. In terms of its realization in a working system, there may be some different ways of doing it. One way is, let's assume I have an associative cache here with 8 ways. And those 8 ways could be divided into a number of partitions corresponding to the number of processor cores that I would like to divide them among. So I have, in this example, the colors here corresponding to the corresponding to the CPU. So I have a CPU 1 being allocated these 3 ways, CPU 2 being allocated that way, and 3 being allocated these 4 ways. Way-wise is not the only way to do the partitioning. You could try some other ways. It could also be set-wise also. But nevertheless, how it's so some of those details are not very important, but let's just talk in terms of regions and spaces in the cache. We have divided the cache space into 8 regions, and we are trying to allocate those individual regions to the 2 individual processor cores. So that's the idea of cache partitioning. Such ideas are already implemented in commercial systems today. An example of that is the Intel CAT technology that actually permits the programmer to allocate specific partitions to CPUs or groups of CPUs. So what if we wanted to automate this cache partitioning? What happens is that applications keep changing their behaviors. If they are complex enough, then they go through different phases. The same application goes through different phases, and we would like the runtime system to respond to changes that are happening by maybe partitioning the cache differently as time proceeds. So we would like to dynamically respond in a way like this. So time goes from top to bottom, and we are still showing those 3 CPUs, and the way the 8 cache regions or cache ways are partitioned among the 3. Maybe we started off in this kind of a partitioning where 3 of the ways were given to 1 CPU, 1 of them was given to the second one, the last 4 were given to the third one. But as time progresses, maybe the nature of the applications become different, because of which we would like to make these kinds of changes. Right? So that partitioning needs to evolve with time. What kind of sensitivity are we talking about? Let's now bring in something concrete from the architectural space and see how it can influence our decisions. Suppose these applications that were running on CPU 1, 2, and 3 were of the following nature. The first one was a memory-intensive application. The second one was also a memory-intensive application. The third one was a compute-intensive application. Let us say these are the kind of memory-intensive applications that are sending a lot of requests to the memory, but are not necessarily requiring a lot of cache space. On the other hand, the compute intensive application is the one that requires a lot of cache space. But this is just an example to illustrate the point. So the green one is the compute. So we allocate a relatively larger number of ways to CPU 3, but the other 2 receive only 2 each. Now, as the time progresses, let us say the first application that's running on CPU 1 that now enters a compute phase, or maybe the application changed and the new one is a compute intensive application. Then what might happen is perhaps this results in a demand for a greater number of ways being allocated. So maybe we take one of these ways and change its allocation to CPU 1 instead. And later on, maybe some other such changes happen. On CPU 1, we changed the kind of application. On CPU 2, also we changed the application that resulted in one of those ways that was earlier allocated to CPU1 going into the CPU2. So some such changes might happen. The reasons for those changes perhaps have to do with the nature of the application. Here we were just defining two kinds of applications, CPU intensive, compute intensive and memory intensive, but you could define those differences in some other ways too. So let's take a look at how do we go about doing such partitioning, because there are many different ways of partitioning the same cache among multiple CPUs. So what we have an example of here is a four-way cache in which the four ways are partitioned as follows. The first two ways are allocated to one CPU, and the next two ways are allocated to a different CPU. The numbers that you see here are a count that we have maintained of the number of cache hits that were observed in the recent time interval. So we divide time into intervals, maybe of fixed duration, and in each of these intervals we keep some statistics. We keep track of what has been happening in the different components. So here those four different components are those four ways, and we have collected some information about the behavior of the respective programs. So in the first program, it seems running on the first CPU, it seems as though the first way there were a lot of cache hits, but in the second way, not too many. In the second and the third ways that were allocated to the other CPU, CPU2, it seems they are about equal. So that's what we have observed so far. What do we do with this information? We want to finally take a decision of is this the partitioning that we should retain, or we should change that partitioning in some way. So to answer that question, we would need to maintain some additional information. Let's just go ahead and do that. For that CPU1 that is running the app 1, we maintain not just these two ways, that information that anyway we have already allocated to that CPU, but hypothetically maintain some additional information that may help us in the following way. We pretend that we have actually all those four ways being allocated to the CPU1, and if those four were to be allocated, then how many hits would we have in the first way, in the second way, in the third way, and in the fourth way? This information, as you can see, is sort of very interesting. The third and the fourth, these ways have not actually been allocated yet. However, so while the data is not there, we could maintain the respective tags and perform the comparisons and still retain and maintain these counters that tell us if I had given you those additional ways, then how well would you have done. That's the information that we have collected about this CPU1. What you have on the left here is the most recently used. What you have on the right here is the least recently used. So these two ways are not actually allocated. This is just hypothetical information we are collecting. That will help us in the decision. It's these first two ways that are actually allocated to us over here in the real cache. And of course, since we'll assume that the least recently used policy is used, it is these two most recently used ways that are actually there in the cache. The other two ways, the less recently used ones, those are just additional information that we have maintained. Similarly, we maintain the information for the second CPU. The first two ways are actually allocated to us, but let's go ahead and maintain these counters for the other two ways by maintaining those additional tags. You find some additional information here, which is that if you had given two more ways, that's what the behavior would have been. Right? So in the third way, you would have got 5 hits, and in the fourth way, you would have got 3 hits. So that's some more hit counters that we are maintaining for these cache lines. For now, let's assume that we maintain this additional information for every cache line. So some more tags have to be maintained, more hit counters have to be maintained. And with that, here is the kind of inferences we can make. What we are saying is that if you had given me only one way, then I would have delivered 10 hits for that application. If you have given me two ways, which is what you actually did, then I would have delivered 12 hits. That's what I actually delivered. However, if you had gone ahead and given me three ways, then I would have given you 13. If you had given all four ways to CPU 1, then you would have got only 13, because anyway that last one wouldn't have been of much use. That's the information that we have maintained, and graphically you can see that the number of hits is sort of plateaus as you increase the number of ways that you allocate for the program, for that CPU. So there is some additional valuable information that we have collected. Let's go ahead and do the same thing for the other CPU. If you just do these calculations, you see that if you gave only one way, then you would get 7. If you gave 2, which is what you actually gave here, then you get 13. But if you gave 3, then you would get 18. And if you gave all 4, you would get 21 hits for that application. So that's information, interesting information. This is a different shape of the curve than what we saw over here, right? Okay, so now the question is, what do I do with this information? A lot of additional information it seems that we have collected, but then let's go ahead and see how many hits did I actually deliver. How well did the current partition perform? I delivered 25 hits in this current partition. Okay, that's some reference, but maybe there are some other alternatives. Here is another alternative. What if I had reduced the number of ways that I had given to the first CPU, right? I gave only 1, whereas to the other I had given 3. I should take the first 3 here, and this information is valuable for me, right? If I gave it 3 ways, remember, this will deliver 18 hits, whereas if I gave 1 way to this one, this would deliver 10 hits. So if that was my partition instead, 1 to the first CPU and 3 to the second one, then I would get 10 plus 18, and that's 28 hits. Compared to 25 hits, it seems as though that would have been the better way to partition. Okay, now it's too bad we can't do anything about what happened in the previous interval, because that execution has already happened. However, if we predict that the future behavior, the current trend is in some way predicting what will happen in the future, the decision of the runtime system can be then to go ahead and change that partitioning that we did into something like this, where I have adjusted the number of partitions that I gave to the first CPU and the number that I gave to the second CPU. This is one way of maintaining some additional information. This is not without overhead. This comes at a cost, and that cost is first of all the space that I would have to devote here to maintain all these additional structures. I can be more efficient than what I am here. Nevertheless, there is all these counters that we'll be maintaining, that amounts to additional space that we would be maintaining. So there is some area overhead here. But nevertheless, this is a nice way of predicting what would have happened if I had given some more cache space, and based on those additional counters that we just maintained, we can then build some logic that helps us in the partitioning. A totally different approach to this would be treat that entire system architecture as a black box and just define some states that meaningfully capture what's going on in the system. Define some reward functions for evaluating what's going on, what has recently gone on in the system, and encode the learnings in what is called a Q table, that is a table of states and actions, where what we have captured is the expectation on performing different actions in each of those states. And every time window we look up this table and populate it with the newer states and rewards that have been observed, and also find out from them what is the suggested action among all the actions that are there. These actions for our problem then translate to the partitioning decisions. Those actions are suggested, they are imposed on the system architecture, and we have a loop where every once in a while we are observing the state, we are evaluating in terms of the reward functions, computing the expected rewards, and taking the actions. So this is a loop that can be applied to many systems, however simple or complex, without necessarily getting into the logic of why a certain action is good or bad. We try to make the system itself learn. If enough data is there, then perhaps the results will be good. To use reinforcement learning on this problem, we would have to come up with our state definitions, our actions, and our reward functions. This is actually not as easy as it might seem. It seems as though we need to make only 3 decisions here: what are states, what are actions, and what are rewards. But a lot of iteration is needed, a lot of understanding of the system is needed to actually come up with a reasonable set of states that actually capture the system the way we want to analyze it. So what could it be? Maybe, so how could we define our states? It could be that we just maintain the number of distinct cache configurations. Right? That seems like a reasonable one. Let's say I have 16 ways in my cache and I have 4 cores. Unfortunately, the number of combinations is way too many. The number of states such a system would have is way too many. How many cache configurations are there? Each of those ways could be allotted to any one of the 4 cores. So effectively it is something like 4 to the power 16 states we have. Such a system is too complex. It would never do an efficient learning. For us to succeed and learn something reasonable about the system, we do have to contain the state space quite a bit. So alternative strategies have to be thought of, and this is where a lot of hit and trial is involved, a lot of several different ways of capturing a state ought to be there. And one of the things that maybe we could try out is just have something like 3 states per core. Instead of the configuration just blowing up per cache way, we could just maintain the state of the cores themselves, and that tells us something about the system, and take the decision for the allocations with respect to the cores, and that might actually help us contain this a little bit. And let's just say I maintain 3 states per core. What are they? I increase, well, maybe the performance is improving, maybe it is going down, or maybe it is about the same. So that's about the 3 states I define for the core. And since there are 4 cores, I have 3 to the power 4. That's 81 states. That's much better than 4 to the power 16. So that's an alternative way to do it. Here's where actually a lot of architectural creativity can be used. What is the way to define the system? There is no single way to come up with a definition, and pretty much it is up to us and the problem that we are solving. We would that we would take into account in defining the state of a system. For such a state definition, what actions make sense? The one that we have chosen here is essentially 3 actions per core, where we say you allocate away or you deallocate away, or there is no change, and that's reflected as +1, 0, and -1 here. And an action vector would consist of all the things that we do for each of those cores. So the +1, 0, 0, -1 tells us that I allocate an additional way to core 1. No changes to the allocation in core 2 and 3. And in the 4th one, I subtract away. So in this particular way of defining an action, the allocation to one core is paired with a deallocation to another. Why do things this way? That just helps us contain the number of actions. In the general case, you could allow states to be anything and actions to be anything, but this kind of restricted definition of an action actually helps us define the problem in a way that is more amenable to a solution. Reinforcement learning formulations do have the danger of the state space exploding or the action state exploding, which would lead to way too many considerations, the way too many configurations to consider, and all of that might actually lead to inferior quality of the learning. So quite a bit of experimentation has to be done to arrive at a decision like this. It's pretty much, it's very open. What I have shown here is just one example, but this is, like I had said, an area where a lot of creativity could be used to properly define in a way that is tight, that is efficient, that is small, and yet is something that is comprehensive enough that it captures what's actually going on in such a complex system like a multiprocessor. So anyway, these are examples of states and actions. This is not the only way to define it, but that's one way to define it. And what I have here is an example allocation to the course. The 16 ways are divided as 4, 3, 3, and 6. An action of +1, 0, 0, -1 leads to a allocation change like this. 4 becomes 5, 6 becomes 5, and 3 don't change. So this is a new configuration. This is a new allocation, and for the next interval we can go ahead and let the system execute and observe what happens. If it turns out that in terms of the reward function that we specify, that's the third thing that's there in reinforcement learning, that we have to define. Well, that reward function would be in terms of whatever it is that we are trying to optimize here. If it's throughput, then maybe it's a measure of the throughput that we are measuring, and based on whether the throughput was good or bad as a result of the changes that we did, we would then influence the future evolution of the reinforcement learning based system. Let's switch to a different problem here and illustrate the need for partitioning in a bandwidth allocation problem. So here I have my 4 cores as before. Those are my 4 cores. There is a shared cache, and all these 4 cores are sending requests to that shared cache. And that's a whole lot of traffic, and you can see that ultimately if there's only one request that the shared cache can service at any time, then there is a merging traffic over here that leads to a bottleneck that we need to be aware of. This kind of a bottleneck is quite independent of the space that we have made available here. Maybe there is a space is appropriately partitioned and there is enough space, and yet there is a bottleneck because of the limited number of requests that can be served at any point in time. This is a different and a sort of an orthogonal problem. With this bottleneck, how do we actually manage the bottleneck? You could come up with some different solutions. Maybe we split that one bag of cash into several private banks, right? So that each core interacts with its private bank, and it seems as though this is a better solution. However, this too is not great because maybe there is a wasted resource. Maybe there are some of these banks where space is there, but we are not using them. This may be maybe such an example. There is a need to keep all of them busy. That's when the system is behaving optimally. So this too might not be the best. So in general, even though we would like for a core to access largely its local bank, there is definitely a need to make access available to all these other non-local banks also. So we need that, but we need that not just for core 1, but also for 2, 3, and 4. And you can see this these accesses become messy, so this does demand a network for us to provide. Nevertheless, that bottleneck is still there. If you look at one of those banks, the situation has become slightly better. All the cores are not accessing it at once. Nevertheless, so maybe the traffic has reduced, but that bottleneck is still there because it is receiving requests from all the cores, and so that bandwidth-related bottleneck still exists. So some kind of prioritization is necessary for us to decide what order to service the requests in. So it helps to get some architectural intuition. That's what we'll quickly go through here. And what we have here is the distribution of the last level cache accesses, and what we are counting is in the reorder buffer of the core. These are all the instructions that are being executed. So what we are counting is between successive loads, the successive accesses to the last level cache. We are counting how many instructions are getting executed, and that's a count we are calling ISL, and that's the number of instructions between successive accesses. You see that number is 10 here, but if that program was different and you have more LLC accesses happening, maybe that number is smaller here. So this could actually maybe help us prioritizing. If higher ISL could mean higher priority, which means that we prefer a core like this that actually has a lot of non-memory instructions, or at least non-accesses to last level cache. That way it will make more progress if we give it a higher priority. Such intuitions can be used to solve the bandwidth. The general situation might actually have multiple sources of bandwidth, like maybe there is a 3D memory that exhibits a higher bandwidth and is faster, and is actually coexisting with main memory that has lower bandwidth and is slower, but could be larger capacity. So this could actually be working as a cache, and in the background you have a main memory. These both deliver bandwidth, and this bandwidth may be higher than the other one. In such a situation, how do you manage the bandwidth? Some ideas could be that you partition the load in a way that is proportional to the bandwidth. So more accesses here and relatively less accesses here. So while that is ideal, if the situation is such that the cache utilization is high and the main memory utilization is not so high, then you could actually bypass the cache and divert some of the bandwidth so that the total bandwidth between the entire memory system actually improves. So those are some of the ideas that people have used with respect to partitioning. So important thing is that in summary, you could partition space. That helps in isolating applications and preventing interference. You could also partition bandwidth, which is a totally different thing. It coexists. It's a problem that coexists with the space partitioning, and we also have to do a good job of the bandwidth partitioning. That results in prioritization and better utilization. Our benefits then could be improvement of the overall throughput. There could also be some other nice applications of this kind of a partitioning where we can deliver real-time behavior by an appropriate partitioning of the bandwidth. Perhaps we could deliver better security by making sure that applications don't interfere with each other. So that was a summary of the cache partitioning part. Thank you.
Thank you for your presentation. There are a few questions which I will read out. And so Ramya Ramakrishnan has asked this first question. What is the tool used for implementing prefetching? So what is the tool which was used for implementing prefetching?
Hi, this is Raj Shekhar. The tool, okay, so what we discussed were actually ideas that actually work at the hardware level. So it's like a piece of circuitry that sits alongside the caches, and studies the access patterns and then decides to issue prefetch requests. Now, if you're interested to know how to do this kind of research, typically what we do is we use architectural simulators like Sniper, Gem5, or Tejas, and we implement our idea in these simulators and compare it with a baseline that does not have the idea implemented, and then we see if we get an improvement or not. So so I think the answer to your question would be to use an architectural simulator. Yeah, thank you.
Okay, the next question, I think it was not audible, was that it is from Ajay BS. He's asking, do you think neuromorphic computing, compute in memory approaches can completely solve the memory wall problem?
Hi, this is Sandeep. Those architectures do hold a lot of promise, but unless we have realistic implementations, it is kind of difficult to say whether it will completely solve such problems or not. It will certainly solve, I mean, in compute memory will certainly solve problems around the off-chip bandwidth issues. But then we have not known of any architectures that can deliver single thread performance the way the current architectures do. Yeah, I mean, it is certainly a trade-off, and right now it's kind of difficult to outright say yes or no to that answer. These answers could vary from one domain to another domain.
Next question is from Tirumeni from IIT Dharwad. He is asking the design of the question is the design of prefetch friendly caches in which information memory access is pattern repetitive, not scrambled. That is, when this information slash or memory access is pattern repetitive, in these kind of prefetch friendly caches can be exploited by attackers to infer the program's memory access patterns by carrying out cache-based side channel attacks. So in a way, efficient repetitive prefetch is not a good design in security point of view, since the information is not scrambled. So this is the question.
Am I audible?
Yes, you are audible.
Okay, thank you. Yeah, so the interesting question. The way I see it is the pattern anyway exists, whether we chose to use it for prefetching or not. Interesting patterns do already exist in the accesses that programs generally do. So now you can use those patterns to do prefetching, or you can exploit those patterns to do attacks. So yeah, I don't think prefetching really is opening up any security flaw, the way I see it.
So the next question is from Prashant Babu. He is asking, can AI ML be used for pattern recognition and to optimize prefetch?
Again, interesting question, and that is being explored by many researchers. So yeah, I welcome the person who asked the question to also explore this, and hopefully he finds the next awesome prefetcher.
The next question is from Raunak Chatterjee. He asked, what's the best solution for RAW, raw hazards? So, or true hazards. For raw hazards or true hazards, what's the best solution? Is it out of order execution or some other tricks? So that's what he said.
So, in the interest of time, we didn't really talk about the true dependencies and all of it in the video. But yeah, out of order execution is indeed one way of uh, of of achieving higher performance through design aspects and this thing. But that is not the only way. We do have a lot of other techniques that are being used by modern processors, such as speculative executions, value predictions, and so forth. So it is out of order execution is just one of the many ways which is used in conjunction with the other ways. So these are not, again, totally orthogonal that you have to choose just one technique to go with for improving performance. So yeah, out of order executions helps significantly, but also there are other techniques such as branch prediction, speculative execution, and so forth, which does contribute significantly to increasing performance.
So the next question is from Sayantan Chandra. He asks, temporal prefetch can we use some of the distribution to get likelihood value? That is, range of this address is highest probability, statistical distribution. So can we use some statistical information to get information about the temporal prefetch?
Yes, so it is all some kind of statistical analysis. We just have to keep in mind how much silicon are you going to spend on your prefetcher. So the more complex static analysis that you want to do, then the more you have to spend on storage for the tables, etc. So it's a trade-off. So if you can prove that you are doing complicated static analysis actually helps you get very accurate prefetches, then yes, then it may be worth spending on that extra silicon. But yes, it is possible. Yes.
So next question is from Raunak Chatterjee. What is the future of processing in memory or towards memory computing? So this is not directly related to the thing, but yeah. So what is the future of compute in memory approaches? That's what is.
So I mean, this is. Thank you for the question. I mean, the future is generally kind of speculative. So what my answer here would also be speculative. I have no great authority on these things. It is just a guess. It is going to come in, and it will certainly help a certain class of applications improve its performance. I mean, it could be a step change in a class of applications, but this is it. I somehow, this is again a personal opinion, and please take it with a grain of salt, that it might not entirely replace some of the current architectures that are kind of popular. The reason I say this is our present day architectures have indeed solved, or rather are fairly suitable to a large class of applications already. So let's say, for example, scientific computations, right? The current kind of architectures do solve some domains of scientific computations fairly well. I've not seen any results where the in-memory compute would significantly offer better performance, better single thread performance for those kinds of applications. So yeah, till we see those numbers, it's just a speculation. So but then, like I said, for a large class of applications where the current architectures do fall short, a subset of those applications will indeed benefit from in-memory computations. Not necessarily in memory, maybe because of technology constraints and things like that, but maybe near memory, it is certainly going to come and transform a large piece of. I mean, it is going to open a new dimension in design space exploration, certainly.
So the next question is from Rudula Singh. She is asking, what is EDRAM? What is EDRAM?
So EDRAM is this embedded DRAM. So you have the DRAM dies, which are stacked on top of a compute die. And all of this is part of the same package. So when you buy a chip and put it onto the motherboard, the socket for which you have the CPU socket, inside that socket itself you would have a DRAM. So when we say DRAM, it's a different technology from the SRAM cells which the caches are made of. These DRAM cells are of a different technology that is there. So you manufacture these individual dies separately, and then you bring them together on the same package. Now, because they are on the same package, the off-chip bandwidth is also limited in terms of how many pins can be drawn out of the chip through the package, and then you would have to have additional lines that go from the socket in which you put the CPU into the DRAM's slots. So there is again some constraints on how much width is there, with what frequency can you drive those interconnect lines and so forth. So some of those limitations are overcome when you have a DRAM module which is present inside the same package. So that is where these vertical stacks, right? I mean, layer 0 would be your compute die. Layer 1, layer 2, layer 3, which is all inside the same package, will be of memory modules, and these would be connected when from layer 1, layer 2, layer 3. The data would be brought down into layer 0 for computation through silicon vias, through microbump technologies, and so forth. So that's all the 3D stacking technologies that are there. And because they are all on chip, the distance from layer 0 to layer 1 would be much smaller than, let's say, the compute chip to the DRAM that is off chip that is there. So because your distance between these things are smaller, you would have some benefit in the bandwidth that you can get. Also, the number of lines that you can draw from layer 0 to layer 1 would be much higher than the number of parallel lines that is going off chip to the external DRAM. So these are the reasons why we say this embedded DRAMs can help scale the memory wall.
So the next question is from Shruti at IIT Harvard. The question is, can we use performance counters for deriving the reward functions used in cache partitioning using RL?
Thank you for the question. Now, the reward is typically something that you want to optimize. So if it is really performance that you are trying to optimize, then that's what you would measure. So it is again a function of what's happening in the system. So it is indeed the performance counters that could be used. But if you want to optimize energy, then it is the energy related counters. But appropriately, these are the systems, parts of the systems that you are scanning to find out how well the system is doing. So indeed, the practical implications of an RL based technology would need access to these kind of counters to find out what's going on.
So this is these are all the questions that we have obtained, and I'm very thankful to the presenters for the tutorial and from the organizing committee side. And so we will now. I will now introduce the presenters of the next tutorial. So the next tutorial is efficient computing with non-volatile memory from devices to system level management. So efficient computing with non-volatile memory from devices to system level management. The presenters are Professor Georg Henkel, Professor Jianjia Chen, Professor Hussam Amrouche, and Professor Yuan Hao Chang. So I'll introduce them very briefly. Professor Henkel is a chair professor for embedded systems at Karlsruhe Institute of Technology. He is interested in co-design of embedded hardware, software systems, and in power, thermal, and reliability aspects especially. He has been a general chair of ICCAD, ISL, PED, and such very good conferences. And he has several best paper awards to his credit. He is in steering committees of all major CAD conferences and has given several keynote addresses at important conferences. And he is currently editor-in-chief of IEEE Design and Test magazine, and had been and was the editor-in-chief of ACM TECS for 2 consecutive terms. He is a fellow of IEEE. And Professor, then the speaker, the second speaker is Professor Jianjia Shin. So he is a professor in TU Dartmouth. He is he was a junior professor earlier in KIT. He received his PhD from National Taiwan University, and he was a postdoc researcher in ETH Zurich. His research interests are in real-time systems, embedded systems, energy-efficient scheduling, power-aware designs, temperature-aware scheduling, and distributed computing. And he has received a European Research Council Consolidator Award in 2019. He has several papers and best paper awards to his credit. The next speaker is Professor Hussam Amrouche. He is a professor in KIT and also in University of Stuttgart. He obtained his PhD from KIT, and he has research interests in design for reliability and testing, from device physics to systems, machine learning, security, approximate computing, and emerging technologies. And he's highly interested in ferroelectric devices. And he has several best paper nominations to his credit in DAC and DATE, etc. So he is associate editor of Integration and VLSI Journal. Yeah, and he has several papers in top conferences such as DAC, ASP, DAC, ICCAD, and TED, and journals like TED, TCAS, TVLSI, TCAD, etc. So, and the fourth speaker is Professor Yuan Hao Chang. He is a professor in professor at National Taiwan University, Taipei, and he is currently a professor at the Institute of Information Science Academia Sinica, Taipei. He did his PhD from National Taiwan University, Taipei, and he is interested in memory and storage systems and operating systems, embedded systems, and real-time systems. He has published several articles and archive journals and peer-reviewed conferences. And he is a program co-chair and general co-chair of IEEE Non-Volatile Memory Systems and Applications Symposium in 2017 and 18. So first speaker is Professor Amroj. We welcome the speakers to start the tutorial.
Thank you very much for the very kind introduction. And sorry, I just want to make a small correction. The speakers today will be me, and then we have this, and Jörg Henkel actually is just the organizer, so was not planned actually to give a talk today. So, and our special session will consist of 3 talks, as just mentioned. So the first one will be at the lowest level, let's call it like a design, let's say the devices or physics, how to say the lowest level, where I will talk about emerging technologies. And the second layer or the second talk will talk more about the algorithmic level. And then we move further to the system level or the even operating system, where Jenja from Dortmund, Professor Jenja from Dortmund will talk about the operating system and non-volatile memory. So what we tried in this tutorial to give you hopefully an end-to-end perspective, how non-volatile memories, how emerging devices in general might really reshape the future of computing, and with the perspective about what are the new challenges for different groups from different backgrounds, people coming from circuit, people coming maybe from algorithmic level, and maybe people coming from operating system. What does that really mean for them? So with that, I would like to start with my part. I have already shared the screen, so I assume it's working. So everything's okay. So the screen is visible, and someone just confirm? Yes, good.
Yes, please.
Okay. Yes. Okay, thank you. So welcome to the first part in the tutorial, Journey with Emerging Technologies. So I will focus, as I just mentioned, on 3 types of emerging technologies, covering beyond CMOS technology for logic, non-volatile memories as an emerging new type of memories to hopefully replace our SRAM memories. And then I will also talk briefly about emerging cooling, because cooling is one of always the most important challenges that face chips. As we all know, deep neural networks have provided us in the last few years with lots of breakthroughs in the accuracy of AI in many domains and applications. This would not be possible, in fact, without other kinds of breakthroughs in the underlying hardware. We all know that neural processing units, such as Google TPU, has become recently an integral part in many of our computing systems, starting from the data centers and clouds and servers to mobile devices and even to edge computing. Without such accelerators, we could not really make the neural networks deeper and deeper, where we could really increase the accuracy significantly. However, when we look to the architecture of all and most of those neural networks accelerators, they share similar microarchitecture and similar problems. First of all, we can easily notice, and this is an example here from Google TPU, the first version, which came around 4 years ago. We can easily observe the very large computing engine, what's called the MAC array, a massive number of MAC operations, MAC units, multiplier accumulator units, are really packed in a very small area. In this example, in Google TPU version 1, they had 64,000 MAC units all in one area. And that's a huge number of multiplications are really required to accelerate the neural networks, because this is actually the core and the heart of any neural network, where we really have to multiply the massive number of weights with massive number of inputs in order to do the inference or the training. So we can easily observe that this huge number of MAC operations will providing us with this massive number of computations is all consumed in very small and confined area. There's no surprise, power density will emerge very quickly in this area, and then excessive temperatures and hotspots will be really there located. In addition, we can also observe, when we look to this microarchitecture, the very large amount of area that's reserved for the on-chip memory. We see here around 30% of the entire chip is reserved for the on-chip memory of the SRAM. And we know that our SRAMs is inefficient, is leaky, and also relatively consumes large amount of area. We need 6 transistors to store one single bit. However, such a very large amount of on-chip memory, which is, as you see, it's even larger than the computing engine itself, like there is 25%, that's actually indispensably needed, because with deep neural networks, we have to deal with a massive amount of data that we have to transfer back and forth between the chip, the neural processing unit, and the off-chip memory. And we all know that the memory wall and the previous tutorial gave us lots of hints and lots of indications about the problem with memory. We all know that a single communication with the off-chip memory can consume several order of magnitudes of energy compared to the MAC operation, for instance, or the multiplication or the execution or computation inside the chip itself. However, we cannot survive without this very large, on-chip memory. At the same time, this large on-chip memory consumes lots of energy and efficiency. But if we dig even farther behind the root of those problems, we can really observe the following. First of all, when we talk about the very large power density that's consumed in the MAC array, causing us problems in the temperature and cooling and lots of other challenges, it's actually traced back to a single problem, that voltage in the conventional CMOS is not scaling. And here, I'm not talking about scaling slowly, that what we used to talk in the last 10, 15 years after the discontinuation of the NARD scaling. I'm really talking about that we are approaching fundamental limits in voltage scaling, as I will show you soon. On top of that, minimization, in which we use to minimize the transistor geometry and the gates footprint with every new generation, it's becoming more challenging and coming to an end. We already know that 7 nanometer and 3 nanometer is coming, it's already in the production. The 7 nanometer, 3 nanometer is coming soon. So we don't expect, we will scale down to 1 nanometer even. However, as we just seen, and I have seen in the previous slide, we have more than 30% of our chip occupied for the on-chip memory, and that's still not sufficient. The 30% on-chip memory that's reserved in the Google TPU could only hold around 24 megabytes. This shows, but however, the deep neural network, you have to deal with gigabytes of data. This shows gaining more on-chip memory to avoid the communication to the off-chip memory and preventing the memory wall is actually not going to be solved with our traditional minimization, which anyway coming to an end pretty much soon in the conventional way. We just talked about the memory wall and the need for communications to the off-chip memory. However, this even getting more challenging with every couple of years, because people in the deep neural networks, deep learning and machine learning, they are keep making their neural networks even deeper and deeper to increase the accuracy. And this increase in the accuracy actually comes with massive cost with the data that needs to be calculated. And finally, there is also the cooling of the chip, which we don't think about it too much. But I will show you and motivate you soon that those chips for neural processing units, they are coming actually with a massive or a really enormous amount of power density that will really challenge the maximum theoretical capability of our cooling or conventional cooling using air force cooling as we used to do. In order to really solve those fundamental challenge where we keep gaining accuracy and speed for training and inference in our neural networks, so we should not give up from this luxury, of course. However, if we really need to solve the problems about power densities and about temperature and the communication to the memory and finding a better way to cool down the chip, interdisciplinary is really the key. We cannot have a one magic solution. In fact, we really need different emerging solutions for different areas where they hopefully complement each other and they couple with each other to solve the problem. At the physical level, at the lowest level, the physics, we have to think about beyond CMOS technology, kind of transistors that can really break the fundamental limits now in voltage scaling. which will open doors for solving the problems in power density and temperature, etc., hopefully without any loss in the performance. On top of that, we have to think about new types of memories to replace our traditional SRAM memory. And those memories should be more efficient than the SRAM. And this is where the large amount of research have been done amazingly in the last 10 to 20 years about different types of emerging memories, with all the hope and the dream, how to say, or the roadmap to replace embedded on-chip memory. So I will show you one example in this tutorial. Then finally, I really think the key for those chips and for the power density problem is to replace the traditional way of cooling, where we cool down the entire chip the whole time, even though we might not really need it. And this is what I call it intelligent cooling. In my opinion, intelligent cooling is to cool down the chip where it's needed, so where really the hotspot, and only when it's needed. This opens doors for increasing the efficiency and the capability for cooling. In the next few slides, and in this part of the tutorial, I'm going to take you with a small journey starting from the lowest level beyond CMOS technology, talking about the negative capacitance transistor, NCFET, which is one of the very amazing and promising emerging technology that might replace our existing CMOS with the capability to break down and overcome the fundamental limit in voltage scaling. Then I will show you how ferroelectric transistor, FEB, which shares lots of similarities with NCFET, can really turn magically the single transistor into a memory device. This, of course, opens lots of doors and many doors to replace the 6 transistors of SRAM memory with a single transistor and solve lots of problems in memory communication. Then I will demonstrate to you what does it mean to do intelligent cooling using superlattice thermoelectric devices. Those very ultra-thin film devices that we can locate them on top of the hotspot in the chip and cool down the chip on demand. On demand means cooling down the chip where it's needed and only when it's needed. Let me start this journey with the beyond CMOS and the negative capacitance transistor. First of all, we might wonder why we should bother now at this point of time about emerging transistors. Always that's nice and always it's needed, but why now we really kind of desperately start to look for transistors and technologies to replace the CMOS technology? First of all, we should ask ourselves where we really stand at this point of time in technology scaling. We all know that the blood cell we used to hear about around 100 micrometer, the viruses and coronavirus around 100 nanometer. However, if you think about the technology and transistors, amazingly, the 7 nanometer, it's already in the production 2 years ago, and that is actually almost 10 times smaller than the virus itself. And Samsung even announced that the 3 nanometer technology node is coming, in 2 years from now, and even it was just delayed because the current pandemic. Protein and DNA is a single nanometer. So we don't really expect to scale down beyond the 3 nanometer, which is expected to come soon anyway. Quantum physics and the huge uncertainty once we scale down beyond 3 nanometer will really prevent us, fundamentally challenge us to make reliable systems at the end. As usual, whenever we face such fundamental challenges, breakthroughs are needed. And those breakthroughs come from the lowest level, where we can think about how we can replace the CMOS technology with another technology, allowing us to keep gaining benefit with every new generation, even though we are reaching fundamental limits in scaling. There is another, what I call it, wall beside the minimization wall, which is the voltage wall. We used to hear, as I said at the beginning, in the last 10 to 15 years, that voltage is scaling slowly, non-ideally, the discontinuation of the NAR scaling. But maybe now is the correct time to ask ourselves how much room, how still we have to scale down the voltage. How much we can really still scale down the voltage. It's scaling slowly, but where is the fundamental limit on that? As we all know that the transistor is a switch between the on and the off state, and what really dictates the transistor speed is the steepness of this curve, what we call it the sub-threshold swing. If we could make the transistor much steeper, then we could reach the same on current, which means the same performance, but without any loss, in the performance. However, we could do that at a lower voltage. As we see here, if we magically make the transistor much steeper, we could operate at 0.2 volt without any loss in the performance. However, there is something prevent us of doing that. If you think about it, technology amazingly scaling down the transistors. However, voltage is not scaling down with the same amazing way. Is it a lack of knowledge, a lack of equipment, or there is something more fundamental in the material and the transistor itself which prevent us? In semiconductor physics, it's well known that there is a fundamental limit in the voltage, scaling. This is attributed to this subthreshold swing, and this is known to be 60 millivolt per decade. And this is what we call it the subthreshold swing fundamental limit. And due to this fundamental limit, we cannot scale down the voltage. And the consequence of not scaling down the voltage, new problems that comes in the extreme feature sizes, such as the 7 nanometer, nanosheets, nanowires, and FinFET, which called the self-heating problem, where the generated heat inside the transistor is not able to really escape and go outside and be dissipated. And once you have very high elevated temperatures inside the transistor, of course, all reliability problems will start become larger, and aging and many other problems. And this is a simple consequence of voltage not scaling down. How this 60 millivolt is coming to the picture, it's actually coming from two simple capacitances in series connected to each other, and always you will get a voltage drop. This is simple physics from high school, And you can see here from the simple math that this body factor lambda, it's always larger than 1, and then multiplied by a constant with 60 millivolt. And in fact, the 60 millivolt, it cannot be actually reached, because then you have to make lambda 1, which can only happen if the C insulator or C substrate or C insulator, they should either go to 0 or to infinity, which is of course not possible. So therefore, that is a fundamental limit. You cannot reach the 60 millivolt. But if you ask yourself, what is actually the subthreshold swing nowadays, you can see that TSMC 7 nanometer already achieved 65 millivolt per decade. Therefore, in technology, we are so close to the fundamental limit of voltage scaling. But then, if this is really the case, can we really suppress that fundamental limit? Can we come up with a device that's able to make this subthreshold swing below 60 millivolt, and then the consequence of that, scaling down the voltage without any loss in the performance? The answer is yes, but it took decades to get that answer. If we make this capacitor, the C insulator, if we make it magically negative, you can see that lambda becomes now smaller than 1. And as a result, the subthreshold swing becomes smaller than 60 millivolt. And then the question would be, do we have in nature any negative capacitance? It turns out, yes, and the ferroelectric material, which known for decades, could really behave and exhibit a negative capacitance effect under certain circumstances and conditions of capacitance matching, and that will allow us actually to replace the traditional voltage drop with a voltage amplification. So you can see it as a voltage amplification in this point in the middle. In other words, when you are applying a voltage to your transistor to operate it, the transistor itself perceive it as a higher voltage instead of a lower voltage as a traditional way to the voltage drop. What is the consequence of that? Let's take a look at this analysis for the 7 nanometer FinFET. We can easily see how the transistor, when it gets steeper, then we are reaching the same on current without increasing the off current, which means the transistor itself did not leak or did not become less efficient or more static power. And as a result of that, we have the same on current, means the same performance. There is no cost in the static power, and we could operate at a lower voltage. We see here around 0.4. But then the question is, if NCFET becomes reality and we are really able to scale down the voltage without a loss in the performance, how we can really link the benefit from the lowest level, the physics device level, all the way up to the system level or to the circuit level. And to do that, the gap is very large. So we have built the NCFIT aware cell libraries. We start from the lowest level where we have the physics, how to say, that capture the model physics that capture the impact of NCFET on the transistor. Then we integrated within the BSIM CMG, the compact model of the FinFET technology. And then we characterize the entire cell library as it's done traditionally or commercially. And then we end up by libraries that are fully compatible with the existing EDA tools. You can plug them in, let's say, in Synopsys, in Cadence, in any tool, and perform your analysis. As usual, this work has been done in collaboration with IIT Kanpur, with Professor Yogesh Chauhan from there, who are working on the BSIM compact model of FinFET technology. Then that's not still enough, because if you really want to go to the system level, you have to really think about many cores and simulations where we have workloads and applications. So therefore, we went also to the system level simulators, and I believe many of the audience are very familiar with those things, such as the Sniper and MacPad, and we modified them and we integrated all those scaling factors, how to say, to describe and capture the impact of NCFIT, and then we became able to really run simulations for many cores or for multi-core systems where we are able to translate the impact of NCFIT to the system level. Now, once you build this infrastructure, starting really from deep physics and material all the way to the system level, you will start to be able to answer questions like, what is the impact of NCFIT on our or on future computing? We know that from the trends that frequency is not increasing since, how to say, 2.5 decades, how to say, 15 years ago, because power densities became very high. And then and because of the discontinuation of the NAR scaling. So the first question we would ask, can NCFET revive frequency? Can we get higher performance due to NCFET without violating our power density budget and constraints? And the answer is yes. We have done this work for the entire processor, the system on chip, all the way from RTL to the GDS. And we can easily observe here that with the increase of the thickness of the ferroelectric, which means the increase the amplification due to negative capacitance, we get around 25 or 24% increase the frequency without increasing the power density. And this is important, without any cost in cooling, without any additional cost in temperature, so everything remains as a baseline. Now, the more interesting question is, which is actually more important than the performance, is the power itself, because we need power and low power devices in many areas, even in data centers. Can we revive the NAR scaling? Can we, in other words, reduce the voltage as we used to do in the past and still gain performance or keep the performance as it is? So here in this analysis, we can see how NCFET will allow us to reduce the voltage while we keep the performance and the frequency the same. As a result, around 50% reduction in the total power of the processor is achieved without any loss in the performance, which of course a large increase in the efficiency as a result. We have done this work not only for the CPU and the processor itself, but also we went to the Google TPU and the same architecture there in the Mac array that I showed you in the beginning, and we have run the same experiment, and then the answer was for different precisions with different accuracies, we are able always to achieve a nice reduction in the power, again without any loss in the performance, which can reach around 40 to 50%. And remember, the reason is the ability of the inherent voltage amplification involved in NCFET, which allows us to reduce the voltage while keeping the performance of the transistor same. Let's go back to the original problem. And now imagine if we are able to replace a traditional CMOS that used to implement our Mac array with an NCFET transistor that operated at a lower voltage, immediately you will get rid of the power density challenge, and then you will reduce the temperature. You will not only save power due to the lower computational demand and the lower voltage that you need to operate at, but also you will start to save lots of power due to the lesser amount of cooling that you would demand and need during the computation. And that's actually very important. The saving here will be not only from operating at a lower voltage, which is of course important, but additionally, remember, cooling is one of the biggest contributors to the overall power in any computing system, especially in data centers and servers. We have done also the work about the NCFET with respect to hardware security, and we know that power and always related to the power side channel attacks and the security and hardware problems, hardware security problems, and with NCFET, because it somehow manipulates the power or plays with the power, it's very reasonable to think about what would be the impact of NCFET on the hardware security and power side channel attack. And it turns out NCFET does help us by increasing, how to say, the complexity of the attacks, which means you need more traces in order to infer and get the key compared to the traditional technology. Let me now move to the ferroelectric devices. And as I just showed you, by replacing the insulator of the transistor by ferroelectric material, you are able to create what we call it an NCFET. And at that time, years ago, people tried to make the transistor steeper and steeper by increasing the thickness. But then they faced a problem. If the thickness becomes very hard, then you don't have anymore the nice behavior characteristic of the transistor, and then a hysteresis loop starts to appear, because at the end, the ferroelectric is a magnetic, ferroelectric material. And this hysteresis is bad because it prevents us from building logic devices. But this, what we might think at the first glance as a bug, it turns out to become a feature. By increasing the thickness of the ferroelectric largely compared to the NCFET, we are able actually to separate the transistor into two different states. Let me call it high state and low state. One provides us with a high current, one provides us with a low current. In other words, we are able actually to create a memory device. How? By flipping the polarization inside the ferroelectric material, we are able to make the transistor either a very high performance transistor, let me call it like this, where a high current can be provided, or a very low power, ultra low power transistor where low current can be provided. And by sensing that current, you can easily figure out if a logic 1 or logic 0 has been embedded and stored in the device. And this is the non-volatile ferroelectric transistor. It's a very ultra dense because a single transistor can be used as a memory. It's fully compatible with the existing CMOS because the discovery of the ferroelectrism in the hafnium-based material, which is the material that's used anyway in our conventional CMOS. And now let's go back to the original problem and imagine together, if we replace the SRAM memory with a ferroelectric memory, what does it mean? It means we have a large saving in power because this is non-volatile memory. However, the large saving in power is actually, in my opinion, coming from the ability to store more information within the same area footprint, which means lesser and lesser communication to the off-chip memory. And that is actually the big deal if you are able to replace your SRAM with another type of memory that provides you with a larger capacity with the same area footprint. As traditionally in any emerging memory, reliability is the biggest challenge, and we have studied both design time variation as well as runtime variation due to temperature. And this study is important because we know that those new devices are not perfect. However, if you are able to study the impact of variations, either due to manufacturing variability or due to temperature effects, you would be able to model the probability of error. And once you model the probability of error, remember that neural networks in general, they are resilient against errors. You don't really need full accuracy in your computations there. So a little bit of errors can be inherently tolerated. And we applied this to the neural networks of one specific type, which is the binary neural networks, because they are very efficient, much lighter, compared to the traditional DNN, and more importantly, they exhibit an inherent resiliency more compared to other types against errors. And once you have the error model, you can inject the errors, you can evaluate, and we can see how the impact of temperature would be tolerated or not. So that is important with any new device, that you are not only there are problems, but actually if you can quantify the probability of error and the problems that's coming from those devices, that would be great, because later you can at the system level, algorithmic level, either inject them, train in the scope of those errors, and do something to prevent them. Also, the ferroelectric, just very briefly to mention, the ferroelectric devices are very promising when it comes to neuromorphing, the spiking neural networks, and they can really build the synapses there. And actually, there's lots of research study done on this. And we have also done this work for the concept about what the impact of those errors that I have just explained to you coming due to temperature or process variation on the inference of spiking neural networks. Now let me move to the last part of my talk very quickly. We just said that cooling is problem, but let me explain you how problematic currently the power density in our, on those new chips in neural processing units. We have done this work we took the Google TPU, the systolic array there, this very large 64,000 Mac units, and we have implemented the complete design as usual from RTL to GDS2 level. And we used FinFET technology calibrated with Intel, and then we applied the multi-physics simulations using ANSYS, which is a very complex heat simulation, and for the entire system, and we applied the maximum air cooling that can be provided, theoretically. And then we can see here the results. The power density of the systolic array, 64,000 Mac units, can reach easily around 200 watt per square centimeter, and if you push the voltage, can go around 300, and that is really high. And to get a feeling, you can see here the temperature under the maximum capability of air cooling will exceed the 105 degree, which is considered the critical temperature in chips, and in fact can even go to around 180. This actually became also evident last year when the CEO of Google announced in his keynote, after they introduced the latest version of Google TPUs, version 3, he said, these chips are so powerful that for the first time we had to introduce liquid cooling in our data centers. This shows that the conventional way of cooling became insufficient to dissipate the amount of heat and the power densities that generated in those gigantic Mac arrays. The problem with the traditional cooling, and I believe most of you would agree with me on this, that you are applying cooling for the entire chip, despite that the hotspot is localized in one area. If you take example here, the systolic array, the Mac array will be very hot because all the computation is there, but the memory itself is not that hot and the peripherals are not, yet you are applying, the whole heat sink and the whole, a fan and the entire water cooling even for the entire chip. This is a problem in the traditional cooling because it's inherently inefficient. And if you magically are able to perform cooling only where the hotspot is generated, then you can be by far more efficient. And for them, there is something called superlattice thermoelectric devices. This is some breakthroughs in the material science in the last 10 to 15 years. And they were able to build a very ultra-thin film thermoelectric device, uses the Peltier effect. And those devices are so thin that you can really integrate them on top of the hotspot of your chip. And we have done this work for using, again, multi-physics simulations, and we showed that we are able to suppress, using those superlattice thermoelectric devices, a power density that goes to around 200 watt per square centimeter, reducing the temperature from 125, which is really high, all the way down to around 108, which is by far less than the critical temperature. This shows how superlattice can open doors to maximize the efficiency of your cooling. And more importantly, can open new doors for a larger design space to be explored. For instance, when it comes to neural processing units, we know that the traditional space, you have the power, the throughput, the performance that you have, and you have now how much accuracy you want, which means the precision of your Mac operations. And as a result, you get, your temperature. And now by introducing this cooling or the on-demand cooling, a new design space dimension will come, which allows you to how much power you want to put to dissipate the heat now in that systolic array. And you can see here in this analysis that we have done it recently for different, you can now trade off the temperature, whatever you have you have now a constraint as a temperature that you have. It could be very tight here, like 70 degree. And then you have an accuracy where it's represented by the precision of your Mac operation, as well as you have how much power you want to pay, and etc. and the throughput. And therefore, you can maximize your efficiency, which is how much tera operating floating operations per second per joule, and that can be really high once you have this localized cooling in hand, how to say. This brings me to the end, and before finishing, I would like, of course, to acknowledge the research team that we are working together, both in Stuttgart and KIT, and all the funding agencies that makes this work possible. And if you are interested in general in the NC FET and the ferroelectric devices, We have done lots of work, for instance, the last year in 2 areas, in the computer science area, as well as the circuit and device physics. So based on your background, you are welcome to take a look on our work, and I will be very glad to answer your questions and provide even the libraries or any models that you might need. And before finishing, let me now conclude quickly. If you want to really obtain very high, solve problems, how to say, in deep neural networks and all those accelerations for making that efficient computing, we have to go beyond the traditional way of computing by introducing beyond CMOS technology that breaks the fundamental limits in voltage. And we need to couple that with ferroelectric devices for non-volatile memory as an example. And finally, we cannot really maximize our efficiency without intelligent cooling, in which we cool down exactly where we need in the chip and only when we need. So on-demand cooling is really a key, in my opinion, to increase the efficiency of our neural networks computations. With those together, we are able, hopefully, to break down and overcome the cooling wall, the memory wall, the minimization wall, as well as the voltage wall. And this opens doors for very high efficient computing in the near future, hopefully. The journey with emerging technologies really inevitably pushes us to go beyond CMOS, to beyond von Neumann architectures, to also beyond even traditional cooling, and altogether can really, hopefully, open new doors for the future of computing. And if you wonder why I'm using this symbol here in the picture, because if we really want to maximize our efficiency, we really have to look to combining, how to say, breakthroughs from the underlying physics, and there's lots of amazing work there. However, there is a large gap into our community, and here I'm talking about, our EDA community, our, how to say, circuit community, and this gap is so large, and really state that all of us work together to really bridge the gap between deep device physics to circuit and computer science area. This brings me to the end, and thank you very much. And if you have any question, I'll be really glad to answer your questions either per email or at the end of the session. And yeah, this is my part today, and thank you very much.
Thank you, Professor Amroj. So there are a few queries which the audience have put in. I would like to share those queries. Maybe you can answer those questions.
Sure.
So the first question is from Mr. Ronak Chatterjee. He says that he asks, will quantum computing replace conventional CMOS? What is your take on that?
Well, this is very interesting, of course, but will not replace it in our mobile devices, will not replace it in the vast majority of our computing, how to say, devices. Might definitely be a very good option for the high-end, let me call it, for specific problems where you really, NP hard problems and other problems and maybe security. So in some areas, indeed, the quantum computing will open doors for problems that we will never, ever be able to solve in conventional CMOS. However, those are very, I would say, very, specialized problems, like, as I said, in security or maybe in NP hard problems to be solved. But for the vast majority of our daily life, how to say, where we really need to deal with normal computations and not those, specific problems, quantum computing, we don't expect it to really help in any way or any shape. And this is where we still need another type of beyond CMOS technology that, can be integrated with our daily life and our daily devices.
Thank you, Professor Amroj. I had some queries about your presentations, maybe. So where do you think your NC negative capacitance FET, how do you see its journey ahead? Or do you see it stopping in the middle?
Actually, it's the journey of the NC FET has started precisely around 2007, 2008, when the first breakthroughs came from Saif at that time. And since that time, many groups start to really reproduce NC FET, and amazingly, it's working. Then companies start, like Global Foundries in 2017, showed in IDM at that time how they are able to really realize NC FET in their commercial 14 nanometer technology at that time, which showed an evidence that the NC FET became compatible with the existing CMOS technology. And this is really a key, because any emerging technology that's not really compatible or doesn't become compatible with CMOS, it will stay in the lab. And that is the biggest challenge for any new technology. And that challenge has already been passed and overcome in the last few years after the discovery of the ferroelectrism in the hafnium material. Now, where we stand now at this point of time in 2021, after the discovery and the compatibility with CMOS technology, another barrier, another big challenge had to be also overcome is the thickness of the ferroelectric layer. It has been thought for a long time in physics as a fundamental idea that ferroelectrism and negative capacitance and ferroelectrism in general cannot be realized in a very thin films, like let's say 2 nanometer or something like this. However, that's really needed in technology because we want to keep scaling down. We cannot really afford, let's say, thick layers. And that actually has been also overcome in the last 2 years, where again, the group in Berkeley, Saif and his group, they show they are able to realize the ferroelectrism and NC-FET effects on around 1.7 nanometer. So this was the second biggest challenge. So now the technology able to really produce NC-FET from very thin layers, which means scaling is possible. They are able to really be compatible with the traditional fabrication line, how to say, which is important for cost adaptation from semiconductor industry. I believe it's almost ready. Now, it's a more commercial question when the technology and the semiconductor companies will start to adopt it. So I believe it's more economical now discussion than more scientific discussions. There's lots of evidences. It's now able now to take it seriously, how to say, the industry. But the industry will not do that unless they really see the biggest benefit from, economy, how to say. And this is different question. It's not scientific question, but from scientific point of view, the technology became so promising that to be taken seriously now by the industry. So I believe it can go to reality maybe in, I don't know, in the next decade.
Thanks a lot, Professor Amroch. For digital applications, we still are looking at low technology nodes, but for all mixed signal and analog applications, we still prefer to have a 90 nanometer or even 65, 180, because you have less process variation in that technology range. Now,
Correct.
do you see, right, so do you see NC or even that matter, say tunnel FETs, coming up in a big way for mixed signal applications?
That's a very good question. Actually, this question also applies why nowadays we don't use advanced technology, as you just mentioned, like 14 or 7 for mixed signal and analog applications, because the analog applications really demands certain, how to say, specifications. For instance, in analog and the high current there might create problems like the self-heating that becomes more dominant. And remember, for instance, with NC-FET, where we have an amplification in the voltage, problems like internal heat gets even larger. So NC-FET also opened doors for the analog from different point of view, from maybe the gain, maybe the resiliency to noise and other stuff. But now scaling, this is another dimension. So I would say NC-FET, we are able to build it with 65 nanometer. There is no technical scientific reason to prevent us to not do that. So therefore, now there's two questions. Would NC-FET be helpful for analog? I believe yes. Would NC-FET and scaling be helpful for analog? I would say this is a different question, because we already in technology face this, and the answer is we prefer, as you said, that we stay at an older technology for analog applications.
Thanks for your wonderful session, Professor Amroch. We thank you once again for coming and sharing in your extensive knowledge with our participants.
Sure. And my pleasure.
My thanks a lot. We will now come to the next presenter, Professor Jiajing Chen. We will share his video, and after that, we'll have a Q&A session.
Good afternoon and good evening for the participants from the global. Welcome to the tutorial of full system level non-volatile memory simulation and optimization. My name is Zhenjia Chen. I'm professor at TU Dortmund from Germany. This is a joint tutorial with my PhD student, Christian Hacker, who has recorded a YouTube video, which you can find at the end of today's talk. So what is our motivation about full system simulation? We would like to analyze the memory access patterns of certain applications. So we here look at a concrete example. We would like to query some data entries from the database. So it goes, if we would like to analyze the access to the memory, we would basically run some benchmarks and then look at the memory trace and then use the memory trace to be analyzed or parsed by some tools like Python. And in the end, we can analyze the statistical behavior of the memory traces. So all in all, it depends on how we actually get the data before we can analyze the trace. So it's really less simple. What we need to look is, if we look at this more seriously, we would understand that inside the computing system, there are many things taking place. Those include the applications. I use a database as example, so it also involves the SQL layer, and of course, high-file system, the runtime libraries, and sometimes, which is often forgotten in the analysis of embedded systems, is the kernel and the drivers. To analyze the system behavior regarding memory, what has been typically done is to analyze the behavior based on typical benchmark applications on the target hardware. Since we are interested to look at the bioaddressable non-volatile memory as a replacement of DRAM, it means that we would like to change the target hardware from DRAM to non-volatile memories. Since the benchmark applications are not usually run as a standalone application, we do also need to investigate the impact due to environment, including operating systems and runtime libraries, as I mentioned earlier. And of course, this implies that we would also have to look at the maintenance strategies, which are usually done in the hardware. However, what has been typically forgotten is that if we only simulate the behavior of benchmark applications, we sometimes apply high-level simulations to run the benchmark directly on the hardware using simulators. And that means that the environment is not simulated and not analyzed. And such maintenance strategies can be implemented in the high-level simulators, but those do not involve the operating systems or runtime libraries. So therefore, it's always questionable whether the maintenance strategies may destroy some behavior of the environment or even lead to certain side effects. So what I've illustrated is the problem that when we look at the high-level simulations applied on an application trace to an in-house model, we usually would have problems that we could not capture side effects, as I mentioned earlier. Therefore, it's really necessary to use a precise simulation for the maintenance strategy. And this is what we are going to talk today, how to perform such full system and precise simulation so that we can use them to analyze the non-volatile memory in a better manner. So our target here as use cases would be memory domain remapping for where labeling. And of course, this is our tutorial. Our platforms are not limited to such optimization goal. Why are simulations not equal to a system call emulation? Let's look at the details. When we are interested to perform full system simulation, the processing hardware and the peripherals are simulated. And all exception levels are also simulated. The operating system is simulated. The operating system and application, therefore, can be analyzed with the concrete behavior of the simulation. The typical way to emulate the system code or the simulation by system code emulation is slightly different. The processing hardware is, of course, simulated. The peripherals are usually only partially simulated. What's most problematic is that the operating system is shared with the host and operating system is not simulated. And the system calls are handled out of the simulation. You do not actually handle system calls in the simulator. So any behavior regarding the system call would be problematic. With that, I would like to give you the honor of today's talk. First, I will give you a short introduction about the simulation architecture, and we will look at the case study regarding wire leveling. And then I'm going to look into a specific operating system called unikernel, and we will explain why such a kernel is useful and what it is. And then we would I will present the semantic memory tracing for static memory regions and dynamic memory regions. And at the end, I will conclude today's tutorial using a database benchmark of SQLite. To answer those questions, we first need a cycle-accurate simulator, which simulates the architecture of a computing system. The cycle-accurate simulator should provide the accurate simulation of the functional units of the processors and controllers on the chip and also peripherals. Do we have such cycle-accurate simulators? Yes, there have been a few cycle-accurate simulators available in the research community and also in the industry. In this research, we will use Gen 5 as our cycle-accurate simulator, and the timing is simulated inherently. How do we simulate non-volatile memories in a cycle-accurate simulator? So we first should set up a realistic system. In this case, we consider embedded processors, and we should capture the process memory accesses, and we should make applications accesses separately analyzable from the operating systems. What we have done is to look at a realistic setup of concrete system. We use Linux as our host system, and then on top of that, the cycle-accurate simulator Gen 5 is employed, and also we use the non-volatile memory simulator NVMe 2.0 to simulate the memory behavior of the DRAM when it's replaced with non-volatile memory. On top of that, we have to put a runtime system, and then we run certain application benchmarks to evaluate and test those the behavior in the system. All in all, we can look at that applications may require system services, and such system services will be provided by the runtime system. And then the runtime system would provide the hardware initialization, and this will be further pushed from Gen 5 to be simulated. And at the end, all the memory accesses are actually passed back to non-NVMe 2.0, and then this is later stored as a memory trace file in Linux. To do so, we first have to find the separation of the memory access patterns. I would assume that you have some basic knowledge about the memory layout in modern computing systems. It's well known that we can separate the memory accesses into different layers. We have the text region for storing the instructions. We have the stack region for storing the stack information. And we have the data region for storing the heap, BSS, and uninitialized and constants and non-initialized data. With such static separation and ordering during compilation, we are able to identify the access behavior of such regions. And then we could use the data get from Gen 5 and NVMe 2.0 to a filter, and then we can use analysis scripts to analyze the aggregate behavior of those memory access patterns. With this, we are able to analyze the applications in many cases. Of course, we are also interested to analyze the behavior between in the operating systems. Therefore, additional separation between operating system and application is done carefully. We performed two isolations to make sure that we are able to identify whether a specific access is from operating systems or from an application. We had a spatial isolation. That means that we look at the distinct memory locations. So in this example, we have the application marked in red, and we have the operating systems marked in green. And what we see here is that from the virtual memory mapping to the physical memory, we are able to actually capture the behavior in the physical memory based on the memory mapping table. And we can use this for the analysis later on. We also need to look at the interrupt isolation to make sure that the interrupt is correctly handled by the corresponding routines. What we have done is to let operating system interrupts target a distinct stack so that we do not actually change the stack behavior of applications. Whenever there's an interrupt in operating systems, this interrupt would have its behavior on the stack. With this concept, I'm now going to introduce you how we can use this to analyze the wear leveling behavior in a full system stack. So we have two passes, right? First part is to understand the behavior of an application operating system libraries and the cache behavior. And the end, what we can do is to understand how each of the layers behave regarding the memory access pattern. And this is only for the analysis. Only after we are able to understand how each layer plays a specific role in the wear leveling to reduce the number of writes in non-volatile memory, then we are able to perform the design from the other level to reduce the wear levels of those non-volatile memory cells. So what we can see here is that its design is from the opposite level. That means that the hardware should have access objective, and then the cache should be the design should be cache aware, and then operating system should provide wear level services, and then at the end, the applications can provide wear level hints so that specific routines may have significant impact on the wear leveling, and this should be provided from operating systems, so from the application, so that the whole system level, all the layers in the system can react according to such hints. This is one case study that I'm going to present here for today's tutorial. In our recent result, we have more case studies available. So this is a benchmark from SHA. Let's look at the baseline analysis of this program. So the axis here is the memory, main memory address. It starts from the address. It has in total 52 kilobytes, and we can look at the three segments: the text, data, and stack. The y-axis here is the write count. I would like to remind you that the y-axis here is in log scale. What we can see here is that the maximum access happens on the stack. So this program has a heavy access in the stack with a lot of writes. And it implies that if you look at the non-volatile memory behavior, specifically for this region, you would have a lot of writes. And that means that if your non-volatile memory is not aware of this behavior, then you would always write to the same place again, and again. And this memory will die out due to the frequent writes of this area. To reduce the impact of such frequent writes, wear leveling mechanisms have been introduced. Such mechanisms have been implemented as operating system libraries using hardware controllers. They need cooperations with the application about the memory layout. They should be aware of the cache and MMU models, and typically they need certain approximations of write rates and the information regarding the remapping of virtual memory pages. And they can be implemented in a simulator, in a high-level simulation. And this is what you can see from typical classical evaluation results in the literature, based on simple Howell abstractions. You need roughly less than 100 lines of code to implement such evaluations. The evaluations here provides a real implementation and simulation. Since we have to simulate the complete runtime system and operating systems, including libraries, we need much more lines of code, but those are more related to the system runtime and the operating systems. If you are interested to extend from this point on, then you don't need to implement so many lines of code, of course. Now let's look at the difference between these two results. Since the classical evaluations are based on simple Howell abstractions, only can look at the high-level simulation. They are not able to get the detailed information regarding the operating systems. And what you see here is that they do not capture many writes that could potentially take place, as you see in the right-hand side. What we see in the right-hand side is that we get more detailed information. We also get many more writes in certain areas. If you compare this area with this area, you see that their behaviors are very different. We do not challenge that such classical evaluations are not useful. We want to just emphasize that if you are interested in the detailed information regarding the full system, then you need to actually evaluate not only the benchmark applications, but also the runtime systems. And this is, of course, a more representative manner to evaluate whether the proposed well-leveling mechanisms or the proposed handling mechanisms for the long-term memory actually work or not. With this, I hope I have convinced you that high-level simulations are not sufficient to get the detailed information regarding memory access patterns, especially when we would like to do memory management for non-volatile memories. It can be done with real implementation with the full system simulation. And we have actually published our source code and the manuals in this GitHub repository. You can check it out, and if you have any questions, also feel free to contact us. With this, I hope I have convinced you that it is possible to perform full system simulations to get the memory access patterns. We can include the runtime library and operating systems in the full system simulations. The next question we should answer is that which operating systems should be simulated? Is it possible to simulate a full operating system? Is it possible to simulate a big operating system like Linux? Unfortunately, simulating Linux would take a drastic amount of time on the cycle-accurate simulator. What we would like to pursue is to have a fast, small, and configurable kernel so that we can simulate the memory access patterns by looking at the libraries and also the runtime services and also the operating system service routines that are needed to accomplish the application. Towards this, we have identified and we have adopted the unit kernels as part of the UniQuest project supported by HS 2020 from European Union. The unit kernels provide a very flexible configuration of the kernels, such that we only run the applications in one. We only run one application in one address space, and that address space is designed for the specific task. If you have multiple applications, you just need multiple different separate address spaces to actually achieve this goal. What's required is the components as libraries tailored for the kernel. Here's one example. We can select some libraries from the library pool. For example, if we are interested in Python, we can select Python. If we're interested in database, we can select SQLite. And after this, you can configure the kernel that is the libraries that are needed in the kernel, and you obtain a Taylor source tree and just build the source, build the kernel that is flexible for you to use for the application. So to build a unit kernel, it's also not very complicated. What we need to do is to build the libraries first and then link them separately. So this is a standard procedure to build C applications. This is also similar when we build unit kernel. First, we have the source code, and the source code are built for function, and then you get the corresponding object files. And then you merge those object files, and at the end, you link those object files, and by reordering of memory segments, and you will get the corresponding precompiled libraries as the kernel. Now let's assume that we have the kernel already, and we like to perform the memory tracing. So this is a typical memory trace. We see the timestamp, and then we see the corresponding memory access address. We have a sequence of those memory access sequences. How can we know which library caused the access if all libraries are merged in one memory space? Fortunately, we can apply the compiler naming scheme. So specifically, this is one example. For example, in this case, we have one pointer, and this pointer is stored in the corresponding memory address. And if this pointer is always a static address, then we are able to trace this memory access directly. So what we need to do is to make sure that the names of the variables are preserved through the whole compilation. So the compiler first generates unique names for variables. Those names should be actually preserved while linking the libraries. And then after that, what we need to do is to simply compare the symbols in the kernel and also the symbols in the libraries, and then we could get the corresponding memory address for the specific kernel that is needed. To analyze the memory tracing, we also have to consider different regions of different segments of our memories. So as we know that we have static memory segments for data, BSS, and text, and we also have dynamic segments for heap and stack. For the static segments, they are allocated at the compile time, so we do not actually have to worry about their memory regions. What we need to do is to record the corresponding memory region, and then we just have to generate the library memory map to get the corresponding list of labels and their corresponding memory addresses. So for the static memory tracing, we can just use a spatial separation, and then we can then directly investigate the write counts, the access right per library. For dynamic memory tracing, it's more complicated because the data items are allocated at runtime in stack and heap. As they are allocated at runtime, it's not possible to have spatial separation among those memory accesses. That means that the access to a specific memory address could be due to different variables. Luckily, the memory accesses are always done by certain instructions. So here's one example. We see that the two instructions, STP and STP here, would result in a memory access to the corresponding memory address. So therefore, what we need to do is to actually identify which instructions actually result in such memory accesses. And this can be done by tracking the program counter. And indeed, the program counter points to the static allocated text. Therefore, what we can do is to track back the corresponding instruction, which results in this memory access. And what we can do is to just identify the specific instruction and then get a corresponding behavior over there. To achieve this, what we need to do is to add one additional item to the memory traces. We do not only need the memory accesses, we also need the program counters of the accesses. So this requires us to modify the simulator to add the program counter in the trace file. With this, we have the library on hand and the memory trace we derive from the simulation. We can just compare them and then get a corresponding behavior per library. And then we can analyze the statistic performance and statistical data per library. To demonstrate how this works, I would like to present a case study based on the SQLite database simulation. This was implemented in Gen 5 together with NVM, and the post-processing was done in R. The benchmark was for SQLite database. So it consists of the high-level application to perform a query, and of course the SQLite library, and several additional necessary libraries, including PeaceWrite, file system, and C library. In addition to those libraries, we also had to support the Gen 5 platform library for Unikernel. We only look at the analysis on the total amount of write accesses here, but of course you can also use the memory access traces to perform other analyses. The first result I'm going to show here is the static memory tracing. This is based on the data queried for the SQL database. The x-axis here is the memory address in the main memory. The y-axis here is the write count. I would like to emphasize again that the y-axis here is in log scale. The x-axis here is just the unit of the main memory. We can clearly identify different regions of the memory and the libraries. We can clearly identify different regions of libraries, and we can also identify the peak of writes. Specifically, we see that the SQLite library and the file system libraries use a lot of writes in the static memory access region. For a dynamic memory tracing for a static memory region, we are not able to clearly distinguish the libraries anymore due to the fact that they will share potentially the same physical memory for the stack. You can also use this to analyze the corresponding access to the memories for different libraries. With the data here, we can use them for certain analysis. One example here I would like to present is the achieved endurance of the mechanism. So here I do not present any mechanism, but you can use that to analyze the percentage of achievements depending on the mechanisms you are interested to simulate. So achieved endurance is defined as the mean write counts divided by the maximum write counts within a library. So this means that if this achieved endurance is lower, then you have more deviation regarding the counts within the write counts within the library. If you have a lower achieved endurance, that means that the potential to improve the mechanism is much higher. If you have higher achieved endurance, that means that the mechanism is potentially already very good. What we see here is that, for example, the SQLite library has a pretty good achieved endurance in the stack, but pretty low performance in terms of the data segment. It means that with such information, we can use we can also design different mechanisms to handle different libraries to achieve better endurance. With this, I've presented automatic segmented memory tracing mechanism. The unit kernel by default properly isolates the software components, and the analysis automatically operates on the compiler output. Therefore, it can be used to analyze the corresponding behavior of the underlying libraries and also the operating service routines. I would recommend you to try yourself, and in case you have questions, feel free to contact us. For those who are interested in more details, Christian Hacker has prepared a demo video, which can be found in this YouTube video clip. You can also check it out.
Thank you, Professor Chen, for your wonderful presentation. I have few queries which maybe we can discuss.
Okay, no problem.
Right. So, how do you think this methodology can be applied to your computing memory sort of architecture?
Yeah, so we are actually currently working on that. One thing that is needed is to actually allow some compatibility in MBMAN. So currently the model from NCFAT and FEFAT is not part of the MBM library. But the operating system concepts, in our opinions, would be similar. The runtime libraries would be also similar as well. So we intended to first develop the full system simulation. And in that case, we are able to plug into different hardware features, but we are not there yet.
Right. Thank you. Further, in this case, in the work which you had presented just now, in this work which you had presented, how do you think? How can you enhance the system throughput?
We haven't looked into the system throughput. I'm not sure whether I understand the question. Is the question about the simulator throughput or the throughput of the simulated hardware?
So I wish to ask for the simulator.
Okay.
With lower number of CPU cycles, how can you get the highest amount of computation?
Yeah, so this is a nice question, and this is the typical problem for full system simulation. Actually, what we are also working on is the simulation under different granularities. So you don't actually need to simulate everything, right? So what we wanted to demo and also evaluate is the importance of system runtime library. So if you are not interested to know the details of the runtime library, then you have the choice to only look at the high-level simulations. But if you're interested in the runtime library, you have the choice to simulate the runtime library. If you are interested in the full system, then you have the choice to simulate a complete operating system as well. So this is in different granularity, and of course, it's up to the designer's choice to choose the most proper label.
Thank you, Professor Chen, for a nice presentation and answering the queries. We now move to the next presenter, Professor Hao Chang. We will play the video now, followed by question answer. Thank you.
Okay, thank you. Okay, thank you.
Hi, everyone. This is Hao Chang from Academia Sinica Taiwan. Today, I'm going to talk about the random forest techniques for systems with non-volatile memories. First, I will have some introduction to random forest and non-volatile memories, and then I will talk about some random forest techniques for systems with non-volatile memories, and finally, I will give a conclusion. In the big data era, the data volume is skyrocketing, and data are loaded into main memory for better efficiency, but in this way, big memory is needed to process big data. Due to the lower unit cost, non-volatile memory has the great potential to meet the demand for big memory. And in this figure, we can find that more and more data are placed in non-volatile memory. The rate of data generation surpasses the growth of memory capacity, so MVM is not big enough in practice. it is impractical to load all the data into NVM in advance. So intensive data movements still exist and are harmful to non-volatile memory. A decision tree is to predict the target result by learning simple decision rules inferred from the data features. For example, should we go for a sightseeing to the lake? And we can use the decision tree to consider the weather and then decide whether we want to go to the lake. However, a single decision tree often shows low reliability because of the overfitting problem. A random forest is a collection of weaker decision trees. To avoid the overfitting, each decision tree is randomly generated by a subset of training data, and altogether they can build an ensemble of decision makers by voting for the result. And there are several advantages. First, it has very high prediction accuracy, high efficiency over the large data set, and a low training cost compared with the neural networks. First, I will talk about the backend strategy for NVM. In the backend phase, we will randomly select data samples to train the decision tree and run for several rounds to form a decision tree forest. And in the ensemble phase, we'll take a majority vote or an average over the results of decision trees. Due to the random selection process of backend, the probability to select any sample data from the dataset is about 63% in a single round of backend. That is about 63% of data in the training dataset will be sampled by each backend round to train the decision tree. In this way, some data may be resampled to form decision trees in any 2 consecutive rounds of backend. And about 63% of data are resampled from the previous backend round. Therefore, it will introduce a lot of unnecessary data movements. Based on the above observation, we propose an NVM-friendly backend strategy to reuse the active data for a random forest. The main idea is to treat the randomness of the random forest for endurance and performance improvement for NVM memory. And our contribution is to keep the prediction accuracy while achieving good well-leveling on NVM memory. The main idea of the active data reusing is to pin some data in the main memory for the next runs. For example, the blue ones are pinned in main memory for the next run. But it will cause the wear-unleveling issue because the blue ones will endure fewer writes than the green ones. To resolve the wear-unleveling issue, we propose a margin-based reusing policy by combining the active data reusing and wear-leveling. By properly selecting the reused data with the margin pivot, that is, we will move the margin pivot forward on each round. For example, in the second round, we will reuse the first 4 frames. And in the third round, the pivot is moved forward. Therefore, the next 4 frames are reused to achieve the wear leveling. 3 traces were used for evaluation, and 70% of data were used for training, and 30% of data were used for validation. And the first size is defined as the total size of random forest to the dataset. The following figures are used to show the right reduction of effectiveness of the proposed strategy, and the x-axis is the forest size. The y-axis is the number of right axes. And we can find that the amount of right reduction is positively related to the reused ratio. In this figure, we find that the reusing ratio has less impact on the error rate, and the error rate drops more significantly when the forest size grows. This means that the forest size is more dominant than the reusing ratio. In summary, the proposed NVM-friendly backend strategy can achieve both the right reduction and wear leveling, and by reusing data samples during the backend, the proposed strategy can save the right axis with nearly no degradation on the prediction accuracy. Now we shift our focus to the pruning stage of the random forest construction, and we propose the dual-phase pruning to increase the energy efficiency and reduce the write latency. Decision tree is the base element of the random forest algorithm. A tree-based structure consists of the three major components. Internal node is the taste and the attribute. Branch is the outcome of a taste, and the leaf node is the result for a prediction process. On the right-hand side is an example. The internal node is the taste and the attribute age, and it will generate two branches. And on the second level is the taste and the attribute sex, and the outcome has two branches, that is female and the male. And in the leaf node, female is the result. In general, a decision tree is a fully grown decision tree, and it will stop growing when there's only single one class in the node, or there's no attribute for node splitting. But a fully grown decision tree usually have the overfitting problem. To avoid or solve this problem, the post-pruning strategy are usually used to cut the redundant nodes off. For example, on the right-hand side figure, the green nodes are cutting off by the post-pruning strategies to avoid the overfitting problem. After the post-pruning, the redundant nodes are cut off. On the other hand, phase change memory is the very famous non-volatile memory. It has some nice features such as the high cell density, non-volatility, and faster read performance. But it also has some drawbacks such as the expensive writing cost. Therefore, the multi-level cell PCM supports multi-write mode. The high-cost writing mode, it takes longer write latency and higher energy consumption, but it can retain data for a long time. And the other is the low-cost writing mode, but it can only retain data for a shorter time. On the other hand side, there's a figure to illustrate the retention time of the two modes. The upper figures shows the high-cost writing mode because the blank space between each state is wider. Therefore, the data can be retained for a longer time. The bottom figure, each state has a narrower blank space. Therefore, the retention time is shorter. Based on our observations, we find that the redundant nodes will be pruned by the post-pruning strategy, and the nodes will become the unnecessary writes to the non-volatile memory because during the training process, data read into non-volatile memory are persistent. Therefore, our goal is to reduce the writing cost, including the energy consumption and the latency resulting from the unnecessary writes. Therefore, by utilizing the multi-write mode of the PCM, we are trying to hybrid the low-cost writing mode and the high-cost writing mode. That is to use the low-cost writing mode for the unnecessary writes and the high-cost writing mode for the persistent decision tree nodes. But how to have an accurate prediction is the quick question. To answer this question, we propose the dual-phase pruning framework that combines the pre-pruning and the post-pruning strategies. The dual-phase pruning framework is composed of three major components. The first one is the pre-pruning checker. This checker is to identify the to-be pruned nodes in the decision tree and mark these to be pruned nodes as the high light write nodes because they are going to be pruned. Therefore, we don't need to spend too much energy to maintain those data. And the second component is the node tracker. It is to track the head of the light write subtrees. Therefore, we will know which is the starting node for the pruning. And the third component is the planer. That is to rewrite the light write nodes in the normal writing mode. If the light write node is not pruned in the post-pruning phase. The main goal of the pre-pruning phase is to conserve the energy consumption for writing the unnecessary nodes. But how to identify the unnecessary nodes? We include the two parts. The first part is to combine the pre-pruning strategy, such as the chi-square test and early stopping. The second one is to identify which node should be written in the low-cost writing mode. For example, the secondary checker can be used as the test to see whether this node will be possibly pruned in the post-pruning phase. Therefore, we can use the light write mode to write it. The main goal of the node tracker is to keep the information of light writing nodes for checking those nodes in the post-pruning phase. And the node tracker includes the tracking list to point to the head of the light write subtrees. For example, on the right-hand side figure, F32 is the root node, and F16, F20, F33, and F18 are the head of the light write subtrees, and they are possibly will be pruned in the post-pruning phase. Therefore, they are written with the light write mode. The main goal of the post-pruning phase is to maintain the prediction accuracy in the proposed framework. However, during the post-prune decision tree, some tree nodes in the tracker will not be pruned. For example, on the right-hand side figure, there's one node that is not pruned. Therefore, we need to rewrite it with the high-cost write mode because if we do not rewrite it, the data will be lost. And for the other nodes that in the tracker, that will be pruned, and we will just skip it and ignore it. The proposed framework was integrated into the famous Ranger, and we collect the amount of read-write traffic to memory and simulated the energy consumption and I/O performance on the ambient device. And the evaluated metrics are the energy consumption and the latency. And when the proposed framework was compared with the pre-pruned tree, a post-pruned tree, and the foreground tree. As shown in this table, we can find that the dual pruning achieves the highest prediction accuracy, which is the same as the post-pruning. However, the pre-pruning has a very low accuracy, which is unacceptable for most traces. As for the energy consumption, compared to the post-pruning strategy, the proposed dual-phase pruning can reduce a lot of energy. For example, it only consumes 87% of the energy under the digit minutes trace, and only consumes 69% of energy under the critical trace, and only 69% of energy under the facial minutes trace. Therefore, it can reduce the energy consumption up to 30%. As for the latency, the proposed dual-phase pruning can reduce the latency for tree construction by up to 16.7%. In summary, the proposed dual-phase pruning framework can reduce the energy consumption of the decision tree construction because it can correctly track in the unnecessary nodes and write them in the low-cost writing mode. Therefore, it can save the energy consumption for up to 30%. In conclusion, in this talk, we demonstrate some approaches to tackle the random forest issues over ambient-based systems. By using the data samples during bagging, we proposed an ambient-friendly bagging strategy to save the write access with nearly no degradation on the accuracy. And by utilizing the multi-write mode and the pruning feature of random forest, a dual-phase pruning framework was proposed to reduce the energy consumption of the tree construction over MLC PCM. Thank you. Proposed to reduce the energy consumption.
Thank you thank you for the nice presentation. So so right now, I'll ask one question. So this you have targeted the your thing for phase change memories. So can a similar strategy be applied for? Have you applied a similar strategy for other non-volatile memory options also?
It's a good question. Actually, we evaluate the strategy for other non-volatile memories, and it has a similar results. But because phase-changing memory is more mature, therefore we present the results over phase-changing memory. Thank you. Yes.
Thank you. So today we will be closing the session now. All the tutorials for today are over. And tomorrow we would meet again for tutorials at 9 a.m. in the morning, Indian time. So, bye for today, and we welcome all of you for tomorrow's sessions.
Okay.
At 9 a.m. Indian time. Thank you very much for the nice presentation.
Bye-bye.
Bye.
Bye.